and other similar rules. In reference to the process of their induction, it is worthy of notice that they founded their reasonings upon Prevost's law of exchanges, and that, in this way, the second of their laws above stated, respecting the quickness of cooling, was a mathematical consequence of the first. It may be observed also that their temperatures are measured by means of the air thermometer, and that if they were estimated on another scale, the remarkable simplicity and symmetry of their results would disappear. This is a strong argument for believing such a measure of temperature to have a natural prerogative of simplicity. This belief is confirmed by other considerations, but these, depending on the laws of expansion by heat, cannot be here referred to, and we must proceed to finish our survey of the mathematical theory of heat, as founded on the phenomena of radiation and conduction, which alone have as yet been traced up to general principles. We may observe, before we quit this subject, that this correction of 151 Newton's law will materially affect the mathematical calculations on the subject, which were made to depend on that law both by Fourier, Laplace, and Poisson. Probably, however, the general features of the results will be the same as on the old supposition. M. Libri, an Italian mathematician, has undertaken one of the problems of this kind, that of the Armel, with Dulong and Petit's law for his basis, in a memoir read to the Institute of France in 1825, and since published at Florence. Sect. 6 Other laws of phenomena with respect to radiation. The laws of radiation as depending upon the surface of radiating bodies, and as affecting screens of various kinds interposed between the hot body and the thermometer, were examined by several inquirers. I shall not attempt to give an account of the latter course of research, and of the different laws which luminous and non-luminous heat have been found to follow in reference to bodies, whether transparent or opaque, which intercept them. But there are 2 or 3 laws of the phenomena, depending upon the effects of the surfaces of bodies, which are important. 1. In the first place, the powers of bodies to emit and to absorb heat, as far as depends upon their surface, appear to be in the same proportion. If we blacken the surface of a canister of hot water, it radiates heat more copiously, and in the same measure, it is more readily heated by radiation. 2. In the next place, as the radiative power increases, the power of reflection diminishes, and the contrary. A bright metal vessel reflects much heat. On this very account it does not emit much, and hence a hot fluid which such a vessel contains remains hot longer than it does in an unpolished case. 3. The heat is emitted from every point of the surface of a hot body in all directions, but by no means in all directions with equal intensity. The intensity of the heating ray is as the sine of the angle which it makes with the surface. The last law is entirely, the 2 former in a great measure, due to the researches of Leslie, whose experimental inquiry into the nature and propagation of heat, published in 1804, contains a great number of curious and striking results and speculations. The laws now just 152 stated bear, in a very important manner, upon the formation of the theory, and we must now proceed to consider what appears to have been done in this respect. Taking into account, it must still be borne in mind, only the phenomena of conduction and radiation. Sect. 7 Fourier's theory of radiant heat. The above laws of phenomena being established, it was natural that philosophers should seek to acquire some conception of the physical action by which they might account, both for these laws and for the general fundamental facts of thermotics. As, for instance, the fact that all bodies placed in an enclosed space assume, in time, the temperature of the enclosure. Fourier's explanation of this class of phenomena must be considered as happy and successful, for he has shown that the supposition to which we are led by the most simple and general of the facts will explain, moreover, the less obvious laws. It is an obvious and general fact that bodies which are included in the space tend to acquire the same temperature. And this identity of temperature of neighboring bodies requires an hypothesis, which it is found also accounts for Leslie's law of the sine in radiation. This hypothesis is that the radiation takes place, not from the surface alone of the hot body, but from all particles situated within a certain small depth of the surface. It is easy to see that, on this supposition, a ray emitted obliquely from an internal particle will be less intense than one sent forth perpendicular to the surface, because the former will be intercepted in a greater degree, having a greater length of path within the body. And Fourier shows that whatever be the law of this intercepting power, the result will be that the radiative intensity is as the sine of the angle made by the ray with the surface. But this law is, as I have said, likewise necessary, in order that neighboring bodies may tend to assume the same temperature. For instance, in order that a small particle placed within a spherical shell should finally assume the temperature of the shell. If the law of the sines did not obtain, the final temperature of such a particle would depend upon its place in the enclosure. And within a shell of ice we should have, at certain points, the temperature of boiling water and of melting iron. This proposition may at first appear strange and unlikely, but it may, 153, be shown to be a necessary consequence of the assumed principle, by very simple reasoning, which I shall give in a general form in a note. Note 24/10. The following reasoning may show the connection of the law of the sines in radiant heat with the general principle of ultimate identity of neighboring temperatures. The equilibrium and identity of temperature between an including shell and an included body cannot obtain upon the whole, except it obtain between each pair of parts of the two surfaces of the body and of the shell. That is, any part of the one surface, in its exchanges with any part of the other surface, must give and receive the same quantity of heat. Now the quantity exchanged, so far as it depends on the receiving surface, will, by geometry, be proportional to the sine of the obliquity of that surface. And as, in the exchanges, each may be considered as receiving, the quantity transferred must be proportional to the sines of the two obliquities. That is, to that of the giving as well as of the receiving surface. Nor is this conclusion disturbed by the consideration that all the rays of heat which fall upon a surface are not absorbed, some being reflected according to the nature of the surface. For by the other above-mentioned laws of phenomena, we know that, in the same measure in which the surface loses the power of admitting, it loses the power of emitting heat, and the superficial parts gain, by absorbing their own radiation, as much as they lose by not absorbing the incident heat, so that the result of the preceding reasoning remains unaltered. This reasoning is capable of being presented in a manner quite satisfactory, by the use of mathematical symbols, and proves that Leslie's law of the sines is rigorously and mathematically true on Fourier's hypothesis. And thus Fourier's theory of molecular extraradiation acquires great consistency. Sect 8. Discovery of the polarization of heat. The laws of which the discovery is stated in the preceding sections of this chapter, and the explanations given of them by the theories of conduction and radiation, all tended to make the conception of a material heat, or caloric, communicated by an actual flow and emission, familiar to men's minds, and, till lately, had led the greater part of thermotical philosophers to entertain such a view as the most probable opinion concerning the nature of heat. But some steps have recently been made in thermotics, which appear to be likely to overturn this belief and to make the doctrine of emission as untenable with regard to heat as it had been found to be with regard to light. I speak of the discovery of the polarization of heat. It being ascertained that rays of heat are polarized in the same manner as rays of 154 light, we cannot retain the doctrine that heat radiates by the emanation of material particles, without supposing those particles of caloric to have poles, an hypothesis which probably no one would embrace. For, besides that the ill fortune which attended that hypothesis in the case of light must deter speculators from it, the intimate connection of heat and light would hardly allow us to suppose polarization in the two cases to be produced by two different kinds of machinery. But without here tracing further the influence which the polarization of heat must exercise upon the formation of our theories of heat, we must briefly notice this important discovery as a law of phenomena. The analogies and connections between light and heat are so strong that when the polarization of light had been discovered, men were naturally led to endeavor to ascertain whether heat possessed any corresponding property. But partly from the difficulty of obtaining any considerable effect of heat separated from light, and partly from the want of a thermometrical apparatus sufficiently delicate, these attempts led, for some time, to no decisive result. M. Berard took up the subject in 1813. He used Malis's apparatus, and conceived that he found heat to be polarized by reflection at the surface of glass in the same manner as light and with the same circumstances. But when Professor Powell of Oxford, a few years later, 1830, repeated these experiments with a similar apparatus, he found that though the heat which is conveyed along with light is, of course, polarizable, simple radiant heat, as he terms it, did not offer the smallest difference in the two rectangular azimuths of the second glass, and thus showed no trace of polarization. Thus, with the old thermometers, the point remained doubtful. But soon after this time, Melloni and Nobili invented an apparatus, depending on certain galvanic laws, of which we shall have to speak hereafter, which they called a thermomultiplier, and which was much more sensitive to changes of temperature than any previously known instrument. Yet even with this instrument, Melloni failed, and did not at first detect any perceptible polarization of heat by the tourmaline, nor did Nobili in repeating Berard's experiment. But in this experiment, the attempt was made to polarize heat by reflection from glass, as light is polarized. And the quantity, 155, reflected is so small that the inevitable errors might completely disguise the whole difference in the two opposite positions. When Prof. Forbes of Edinburgh, in 1834, employed mica in the like experiments, he found a very decided polarizing effect. First, when the heat was transmitted through several films of mica at a certain angle, and afterwards when it was reflected from them. In this case, he found that with non-luminous heat, and even with the heat of water below the boiling point, the difference of the heating power in the two positions of opposite polarity, parallel and crossed, was manifest. He also detected by careful experiments the polarizing effect of tourmaline. This important discovery was soon confirmed by Melloni. Doubts were suggested whether the different effect in the opposite positions might not be due to other circumstances, but Professor Forbes easily showed that these suppositions were inadmissible, and the property of a difference of sides, which at first seemed so strange when ascribed to the rays of light, also belongs, it seems to be proved, to the rays of heat. Professor Forbes also found, by interposing a plate of mica to intercept the ray of heat in an intermediate point, an effect was produced in certain positions of the mica analogous to what was called depolarization in the case of light. Namely, a partial destruction of the differences which polarization establishes. Note 29/10, ed., RS Transactions, Volume Roman 14, and Phil, Mag. 1835, Volume VP 209. Ib. Volume Roman 7, p. 349. Before this discovery, Melloni had already proved by experiment that heat is refracted by transparent substances as light is. In the case of light, the depolarizing effect was afterwards found to be really, as we have seen, a depolarizing effect, the ray being divided into two rays by double refraction. We are naturally much tempted to put the same interpretation upon the depolarizing effect in the case of heat. But perhaps the assertion of the analogy between light and heat to this extent is as yet insecure. It is the more necessary to be cautious in our attempt to identify the laws of light and heat, inasmuch as along with all the resemblances of the two agents, there are very important differences. The power of transmitting light, the diaphaneity of bodies, is very distinct from their power of transmitting heat, which has been called diathermancy by Melloni. Thus both a plate of alum and a plate of rock salt transmit nearly the whole light, but while the first stops nearly the whole heat, the second stops very little of it. And a plate of epochs, 156, quartz, nearly impenetrable by light, allows a large portion of the heat to pass. By passing the rays through various media, the heat may be, as it were, sifted from the light which accompanies it. The diathermancy of bodies is distinct from their diaphaneity, in so far that the same bodies do not exercise the same powers of selection and suppression of certain rays on heat and on light. But it appears to be proved by the investigations of modern thermotical philosophers, de la Roche, Powell, Melloni, and Forbes, that there is a close analogy between the absorption of certain colors by transparent bodies and the absorption of certain kinds of heat by diathermanous bodies. Dark sources of heat emit rays which are analogous to blue and violet rays of light, and highly luminous sources emit rays which are analogous to red rays. And by measuring the angle of total reflection for heat of different kinds, it has been shown that the former kind of calorific rays are really less refrangible than the latter. Note 30/10. See Prof. Forbes' third series of researches on heat, EDINB, RS trans, volume Roman 14. M. Melloni has assumed this analogy as so completely established that he has proposed for this part of thermotics the name thermocroology, chromothermotics, and along with this term, many others derived from the Greek and founded on the same analogy. If it should appear, in the work which he proposes to publish on this subject, that the doctrines which he has to state cannot easily be made intelligible without the use of the terms he suggests, his nomenclature will obtain currency. But so large a mass of etymological innovations is in general to be avoided in scientific works. M. Melloni's discovery of the extraordinary power of rock salt to transmit heat, and Professor Forbes' discovery of the extraordinary power of mica to polarize and depolarize heat, have supplied thermotical inquirers with two new and most valuable instruments. Note 31/10. For an account of many thermotical researches, which I have been obliged to pass unnoticed here, see two reports by Prof. Powell on the present state of our knowledge respecting radiant heat in the reports of the British Association for 1832 and 1840. Moreover, besides the laws of conduction and radiation, many other laws of the phenomena of heat have been discovered by philosophers, and these must be taken into account in judging any theory of heat. To these other laws we must now turn our attention. 157. Chapter 2. The laws of changes occasioned by heat. Sect 1. Expansion by heat. The law of Dalton and Gay-Lussac for gases. Almost all bodies expand by heat, solids as metals in a small degree, fluids as water, oil, alcohol, mercury in a greater degree. This was one of the facts first examined by those who studied the nature of heat, because this property was used for the measure of heat. In the Philosophy of the Inductive Sciences, Book 4, Chapter Roman 4, I have stated that secondary qualities, such as heat, must be measured by their effects, and in sect 4 of that chapter 1 have given an account of the successive attempts which have been made to obtain measures of heat. I have there also spoken of the results which were obtained by comparing the rate at which the expansion of different substances went on, under the same degrees of heat, or as it was called, the different thermometrical march of each substance. Mercury appears to be the liquid which is most uniform in its thermometrical march, and it has been taken as the most common material of our thermometers, but the expansion of mercury is not proportional to the heat. Deluc was led, by his experiments, to conclude that the dilatations of mercury follow an accelerated march for equal augmentations of heat. Dalton conjectured that water and mercury both expand as the square of the real temperature from the point of greatest contraction, the real temperature being measured so as to lead to such a result. But none of the rules thus laid down for the expansion of solids and fluids appear to have led, as yet, to any certain general laws. With regard to gases, thermotical inquirers have been more successful. Gases expand by heat, and their expansion is governed by a law which applies alike to all degrees of heat and to all gaseous fluids. The law is this, that for equal increments of temperature they expand by the same fraction of their own bulk, which fraction is 3/8, 158, in proceeding from freezing to boiling water. This law was discovered by Dalton and M. Gay-Lussac independently of each other, and is usually called by both their names, the law of Dalton and Gay-Lussac. The latter says, the experiments which I have described, and which have been made with great care, prove incontestably that oxygen, hydrogen, azotic acid, nitrous acid, ammoniacal acid, muriatic acid, sulfurous acid, carbonic acid, gases, expand equally by equal increments of heat. Therefore, he adds with a proper inductive generalization, the result does not depend upon physical properties, and I collect that all gases expand equally by heat. He then extends this to vapors, as ether. This must be one of the most important foundation stones of any sound theory of heat. Note 32/10, Manch, Mem, Volume V 1802, and Ann, Chim, Roman 43 p. 137. Yet Magnus and Rignault conceive that they have overthrown this law of Dalton and Gay-Lussac, and shown that the different gases do not expand alike for the same increment of heat. Magnus found the ratio to be for atmospheric air, 1,366, for hydrogen, 1,365, for carbonic acid, 1,369, for sulfurous acid gas, 1,385. But these differences are not greater than the differences obtained for the same substances by different observers. And as this law is referred to in Laplace's hypothesis, hereafter to be discussed, I do not treat the law as disproved. Yet that the rate of expansion of gas in certain circumstances is different for different substances must be deemed very probable, after Dr. Faraday's recent investigations on the liquefaction and solidification of bodies generally existing as gases, by which it appears that the elasticity of vapors in contact with their fluids increases at different rates in different substances. That the force, he says, of vapor increases in a geometrical ratio for equal increments of heat is true for all bodies, but the ratio is not the same for all. For an increase of pressure from 2 to 6 atmospheres, the following number of degrees require to be added to the bodies named: water 69 degrees, sulfurious acid 63 degrees, cyanogen 64 degrees 5, ammonia 60 degrees, arseniuretted hydrogen 54 degrees, sulfuretted hydrogen 56 degrees 5, muriatic acid 43 degrees, carbonic acid 32 degrees 5, nitrous oxide 30 degrees. We have already seen that the opinion that the air thermometer is a true measure of heat is strongly countenanced by the symmetry which, by using it, we introduce into the laws of radiation. If we, 159, accept the law of Dalton and Gay-Lussac, it follows that this result is independent of any peculiar properties in the air employed. And thus this measure has an additional character of generality and simplicity, which make it still more probable that it is the true standard. This opinion is further supported by the attempts to include such facts in a theory. But before we can treat of such theories, we must speak of some other doctrines which have been introduced. Sect 2. Specific heat change of consistence. In the attempts to obtain measures of heat, it was found that bodies had different capacities for heat. For the same quantity of heat, however measured, would raise, in different degrees, the temperature of different substances. The notion of different capacities for heat was thus introduced, and each body was thus assumed to have a specific capacity for heat, according to the quantity of heat which it required to raise it through a given scale of heat. The term capacity for heat was introduced by Dr. Irvine, a pupil of Dr. Black. For this term, Wilck, the Swedish physicist, substituted specific heat in analogy with specific gravity. Note 35/10. See Crawford on heat for the history of specific heat. It was found, also, that the capacity of the same substance was different in the same substance at different temperatures. It appears from experiments of Dulong and Petty that, in general, the capacity of liquids and solids increases as we ascend in the scale of temperature. But one of the most important thermotic facts is that by the sudden contraction of any mass, its temperature is increased. This is peculiarly observable in gases, as, for example, common air. The amount of the increase of temperature by sudden condensation or of the cold produced by sudden rarefaction is an important datum, determining the velocity of sound, as we have already seen, and affecting many points of meteorology. The coefficient which enters the calculation in the former case depends on the ratio of two specific heats of air under different conditions, one belonging to it when, varying in density, the pressure is constant by which the air is contained. The other, when, varying in density, it is contained in a constant space. A leading fact also with regard to the operation of heat on bodies, 160, is that it changes their form, as it is often called, that is, their condition as solid, liquid, or air. Since the term form is employed in too many and various senses to be immediately understood when it is intended to convey this peculiar meaning, I shall use instead of it the term consistence, and shall hope to be excused, even when I apply this word to gases, though I must acknowledge such phraseology to be unusual. Thus there is a change of consistence when solids become liquid or liquids gaseous, and the laws of such changes must be fundamental facts of our thermotical theories. We are still in the dark as to many of the laws which belong to this change, but one of them, of great importance, has been discovered, and to that we must now proceed. Sect 3. The doctrine of latent heat. The doctrine of latent heat refers to such changes of consistence as we have just spoken of. It is to this effect that during the conversion of solids into liquids or of liquids into vapors, there is communicated to the body heat which is not indicated by the thermometer. The heat is absorbed or becomes latent, and on the other hand, on the condensation of the vapor to a liquid or the liquid to a solid consistency, this heat is again given out and becomes sensible. Thus, a pound of ice requires 20 times as long a time in a warm room to raise its temperature 7 degrees as a pound of ice-cold water does. A kettle placed on a fire in 4 minutes had its temperature raised to the boiling point, 212 degrees, and this temperature continued stationary for 20 minutes when the whole was boiled away. Dr. Black inferred from these facts that a large quantity of heat is absorbed by the ice in becoming water and by the water in becoming steam. He reckoned from the above experiments that ice, in melting, absorbs as much heat as would raise ice-cold water through 140 degrees of temperature, and that water, in evaporating, absorbs as much heat as would raise it through 940 degrees. That snow requires a great quantity of heat to melt it, that water requires a great quantity of heat to convert it into steam, and that this heat is not indicated by a rise in the thermometer, are facts which it is not difficult to observe. But to separate these from all extraneous conditions, to group the cases together, and to seize upon the general law by which they are connected, was an effort of inductive insight, which has been considered, and deservedly, as one of the most striking, 161 events in the modern history of physics. Of this step the principal merit appears to belong to Black. In the first edition, I had mentioned the names of Deluc and of Wilk in connection with the discovery of latent heat, along with the name of Black. Deluc had observed in 1755 that ice, in melting, did not rise above the freezing point of temperature till the whole was melted. Deluc has been charged with plagiarizing Black's discovery, but I think without any just ground. In his Idées sur la météorologie, 1787, he spoke of Dr. Black as the first who had attempted the determinations of the quantities of latent heat. And when Mr. Watt pointed out to him that from this expression it might be supposed that Black had not discovered the fact itself, he acquiesced and redressed the equivocal expression in an appendix to the volume. Note 36/10, see his letter to the editors of the Edinburgh Review, No. Roman 12, p. 502 of the Review. Black never published his own account of the doctrine of latent heat, but he delivered it every year after 1760 in his lectures. In 1770, a surreptitious publication of his lectures was made by a London bookseller, and this gave a view of the leading points of Dr. Black's doctrine. In 1772, Wilk of Stockholm read a paper to the Royal Society of that city, in which the absorption of heat by melting ice is described. And in the same year, Deluc of Geneva published his Recherches sur les modifications de l'atmosphère, which has been alleged to contain the doctrine of latent heat, and which the author asserts to have been written in ignorance of what Black had done. At a later period, Deluc, adopting, in part, Black's expression, gave the name of latent fire to the heat absorbed. It appears that Cavendish determined the amount of heat produced by condensing steam and by thawing snow as early as 1765. He had perhaps already heard something of Black's investigations, but did not accept his term, latent heat. Note 38/10, see Mr. V. Harcourt's address to the Brit, a sock, in 1839 and the appendix. The consequences of Black's principle are very important, for upon it is founded the whole doctrine of evaporation, besides which the principle of latent heat has other applications. But the relations of aqueous vapor to air are so important and have been so long 162 subject of speculation that we may with advantage dwell a little upon them. The part of science in which this is done may be called, as we have said, etymology, and to that division of thermotics the following chapters belong. 163. Etymology. Chapter 3. The relation of vapor and air. Sect 1. The Boylean law of the air's elasticity. In the 6th book, chapter Roman 4. Sect 1. We have already seen how the conception on the laws of fluid equilibrium was, by Pascal and others, extended to air as well as water. But though air presses and is pressed as water presses and is pressed, pressure produces upon air an effect which it does not, in any obvious degree, produce upon water. Air which is pressed is also compressed, or made to occupy a smaller space, and is consequently also made more dense or condensed. And on the other hand, when the pressure upon a portion of air is diminished, the air expands or is rarefied. These broad facts are evident. They are expressed in a general way by saying that air is an elastic fluid, yielding in a certain degree to pressure, and recovering its previous dimensions when the pressure is removed. But when men had reached this point, the questions obviously offered themselves: in what degree and according to what law air yields to pressure? When it is compressed, what relation does the density bear to the pressure? The use which had been made of tubes containing columns of mercury, by which the pressure of portions of air was varied and measured, suggested obvious modes of devising experiments by which this question might be answered. Such experiments accordingly were made by Boyle about 1650, and the result at which he arrived was that when air is thus compressed, the density is as the pressure. Thus, if the pressure of the atmosphere in its common state be equivalent to 30 inches of mercury, as shown by the barometer, if air included in a tube be pressed by 30 additional inches of 164 mercury, its density will be doubled, the air being compressed into 1/2 the space. If the pressure be increased threefold, the density is also trebled, and so on. The same law was soon afterwards, in 1676, proved experimentally by Marriott. And this law of the air's elasticity, that the density is as the pressure, is sometimes called the Boylean law, and sometimes the law of Boyle and Marriott. Air retains its aerial character permanently, but there are other aerial substances which appear as such, and then disappear or change into some other condition. Such are termed vapors, and the discovery of their true relation to air was the result of a long course of researches and speculations. It was found by M. Cagnier de la Tour in 1823 that at a certain temperature, a liquid under sufficient pressure becomes clear transparent vapor or gas, having the same bulk as the liquid. This condition Dr. Faraday calls the Cagnier de la Tour state, the Turian state. It was also discovered by Dr. Faraday that carbonic acid gas and many other gases, which were long conceived to be permanently elastic, are really reducible to a liquid state by pressure. And in 1835, M. Thilerier found the means of reducing liquid carbonic acid to a solid form, by means of the cold produced in evaporation. More recently, Dr. Faraday has added several substances usually gaseous to the list of those which could previously be shown in the liquid state, and has reduced others, including ammonia, nitrous oxide, and sulfurated hydrogen, to a solid consistency. After these discoveries, we may, I think, reasonably doubt whether all bodies are not capable of existing in the three consistencies of solid, liquid, and air. We may note that the law of Boyle and Marriott is not exactly true near the limit at which the air passes to the liquid state in such cases as that just spoken of. The diminution of bulk is then more rapid than the increase of pressure. The transition of fluids from a liquid to an airy consistence appears to be accompanied by other curious phenomena. See Prof. Forbes's papers on the color of steam under certain circumstances and on the colors of the atmosphere in the Eden. Trans Volume Roman 14. 165. Sect 2. Prelude to Dalton's doctrine of evaporation. Visible clouds, smoke, distillation gave the notion of vapor. Vapor was at first conceived to be identical with air, as by Bacon. It was easily collected that by heat, water might be converted into vapor. It was thought that air was thus produced, in the instrument called in which a powerful blast is caused by a boiling fluid, but Wolff showed that the fluid was not converted into air by using camphorated spirit of wine and condensing the vapor after it had been formed. We need not enumerate the doctrines, if very vague hypotheses may be so termed, of Descartes, de Chales, Borelli. The latter accounted for the rising of vapor by supposing it a mixture of fire and water, and thus, fire being much lighter than air, the mixture also was light. Boyle endeavored to show that vapors do not permanently float in vacuo. He compared the mixture of vapor with air to that of salt with water. He found that the pressure of the atmosphere affected the heat of boiling water, a very important fact. Boyle proved this by means of the air pump, and he and his friends were much surprised to find that when air was removed, water only just warm-boiled violently. Huygens mentions an experiment of the same kind made by Papin about 1673. Note 42/10, they may be seen in Fischer, Geschichte der Physik, Volume Roman II, p. 175. The ascent of vapor was explained in various ways in succession, according to the changes which physical science underwent. It was a problem distinctly treated of, at a period when hydrostatics had accounted for many phenomena, and attempts were naturally made to reduce this fact to hydrostatical principles. An obvious hypothesis, which brought it under the dominion of these principles, was to suppose that the water, when converted into vapor, was divided into small hollow globules, thin pellicles including air or heat. Halley gave such an explanation of evaporation. Leibniz calculated the dimensions of these little bubbles. Durham managed, as he supposed, to examine them with a magnifying glass. Wolff also examined and calculated on the same subject. It is curious to see so much confidence in so lame a theory. For if water became hollow globules in order to rise as vapor, we require, in order to explain the formation of these globules, new laws of nature, which are not even hinted at by 166. The supporters of the doctrine, though they must be far more complex than the hydrostatical law by which a hollow sphere floats. Newton's opinion was hardly more satisfactory. He explained evaporation by the repulsive power of heat. The parts of vapors, according to him, being small, are easily affected by this force, and thus become lighter than the atmosphere. Muschenbroek still adhered to the theory of globules as the explanation of evaporation, but he was manifestly discontented with it, and reasonably apprehended that the pressure of the air would destroy the frail texture of these bubbles. He called to his aid a rotation of the globules, which Descartes also had assumed, and not satisfied with this, threw himself on electrical action as a reserve. Electricity, indeed, was now in favor, as hydrostatics had been before, and was naturally called in all cases of difficulty. De Seguliers also uses this agent to account for the ascent of vapor, introducing it into a kind of sexual system of clouds. According to him, the male fire, heat, does a part, and the female fire, electricity, performs the rest. These are speculations of small merit and no value. In the meantime, chemistry made great progress in the estimation of philosophers, and had its turn in the explanation of the important facts of evaporation. Bouillet, who, in 1742, placed the particles of water in the interstices of those of air, may be considered as approaching to the chemical theory. In 1748, the Academy of Sciences of Bordeaux proposed the ascent of vapors as the subject of a prize, which was adjudged in a manner very impartial as to the choice of a theory, for it was divided between Kratzenstein, who advocated the bubbles, the code of which he determined to be 1/50,000th of an inch thick, and Hamburger, who maintained the truth to be the adhesion of particles of water to those of air and fire. The latter doctrine had become much more distinct in the author's mind when 7 years afterwards, 1750, he published his Elementa Physics. He then gave the explanation of evaporation in a phrase which has since been adopted: the solution of water in air, which he conceived to be of the same kind as other chemical solutions. This theory of solution was further advocated and developed by Leroy, and in his hands assumed a form which has been extensively adopted up to our times, and has, in many instances, tinged the language commonly used. He conceived that air, like other solvents, 167, might be saturated, and that when the water was beyond the amount required for saturation, it appeared in a visible form. The saturating quantity was held to depend mainly on warmth and wind. This theory was by no means devoid of merit, for it brought together many of the phenomena and explained a number of the experiments which Leroy made. It explained the facts of the transparency of vapor, for perfect solutions are transparent, the precipitation of water by cooling, the disappearance of the visible moisture by warming it again, the increased evaporation by rain and wind, and other observed phenomena. So far, therefore, the introduction of the notion of the chemical solution of water in air was apparently very successful. But its defects are of a very fatal kind, for it does not at all apply to the facts which take place when air is excluded. In Sweden, in the meantime, the subject had been pursued in a different and in a more correct manner. Wallerius Ericsson had, by various experiments, established the important fact that water evaporates in a vacuum. His experiments are clear and satisfactory, and he inferred from them the falsity of the common explanation of evaporation by the solution of water in air. His conclusions are drawn in a very intelligent manner. He considers the question whether water can be changed into air, and whether the atmosphere is, in consequence, a mere collection of vapors, and on good reasons decides in the negative and concludes the existence of permanently elastic air different from vapor. He judges, also, that there are two causes concerned, one acting to produce the first ascent of vapors, the other to support them afterwards. The first, which acts in a vacuum, he conceives to be the mutual repulsion of the particles. And since this force is independent of the presence of other substances, this seems to be a sound induction. When the vapors have once ascended into the air, it may readily be granted that they are carried higher and driven from side to side by the currents of the atmosphere. Wallerius conceives that the vapor will rise till it gets into air of the same density as itself, and being then in equilibrium, will drift to and fro. The two rival theories of evaporation, that of chemical solution and that of independent vapor, were in various forms advocated by the next generation of philosophers. De Saussure may be considered as the leader on one side and de Luc on the other. The former maintained the solution theory, with some modifications of his own. De 168, Luc denied all solution and held vapor to be a combination of the particles of water with fire, by which they became lighter than air. According to him, there is always fire enough present to produce this combination, so that evaporation goes on at all temperatures. This mode of considering independent vapor as a combination of fire with water led the attention of those who adopted that opinion to the thermometrical changes which take place when vapor is formed and condensed. These changes are important, and their laws curious. The laws belong to the induction of latent heat, of which we have just spoken, but a knowledge of them is not absolutely necessary in order to enable us to understand the manner in which steam exists in air. De Luc's views led him also to the consideration of the effect of pressure on vapor. He explains the fact that pressure will condense vapor by supposing that it brings the particles within the distance at which the repulsion arising from fire ceases. In this way, he also explains the fact that though external pressure does thus condense steam, the mixture of a body of air, by which the pressure is equally increased, will not produce the same effect, and therefore, vapors can exist in the atmosphere. They make no fixed proportion of it, but at the same temperature we have the same pressure arising from them, whether they are in air or not. As the heat increases, vapor becomes capable of supporting a greater and greater pressure, and at the boiling heat, it can support the pressure of the atmosphere. Note 46/10, Fisher, Volume Roman 7, p. 453, Nouvelles idées sur la météorologie, 1787. De Luc also marked very precisely, as Wallerius had done, the difference between vapor and air, the former being capable of change of consistence by cold or pressure, the latter not so. Pictet, in 1786, made a hygrometrical experiment, which appeared to him to confirm de Luc's views, and de Luc, in 1792, published a concluding essay on the subject in the Philosophical Transactions. Pictet's essay on fire, in 1791, also demonstrated that all the train of hygrometrical phenomena takes place just as well, indeed rather quicker, in a vacuum than in air, provided the same quantity of moisture is present. This essay, and de Luc's paper, gave the death blow to the theory of the solution of water in air. Yet this theory did not fall without an obstinate struggle. It was taken up by the new school of French chemists and connected with their views of heat. Indeed, it long appears as the prevalent opinion. 169 Gertner, in his Grounds of the Antiphlogistic Theory, may be considered as one of the principal expounders of this view of the matter. Hube, of Warsaw, was, however, the strongest of the defenders of the theory of solution, and published upon it repeatedly about 1790. Yet he appears to have been somewhat embarrassed with the increase of the air's elasticity by vapor. Parrot, in 1801, proposed another theory, maintaining that de Luc had by no means successfully attacked that of solution, but only de Saussure's superfluous additions to it. it is difficult to see what prevented the general reception of the doctrine of independent vapor, since it explained all the facts very simply, and the agency of air was shown over and over again to be unnecessary. Yet, even now, the solution of water in air is hardly exploded. M. Gay-Lussac in 1800 talks of the quantity of water held in solution by the air, which, he says, varies according to its temperature and density by a law which has not yet been discovered. And Professor Robison, in the article Steam, in the Encyclopaedia Britannica, published about 1800, says, many philosophers imagine that spontaneous evaporation, at low temperatures, is produced in this way by elasticity alone. But we cannot be of this opinion, and must still think that this kind of evaporation is produced by the dissolving power of the air. He then gives some reasons for his opinion. When moist air is suddenly rarefied, there is always a precipitation of water. But by this new doctrine, the very contrary should happen, because the tendency of water to appear in the elastic form is promoted by removing the external pressure. Another main difficulty in the way of the doctrine of the mere mixture of vapor and air was supposed to be this, that if they were so mixed, the heavier fluid would take the lower part, and the lighter the higher part, of the space which they occupied. The former of these arguments was repelled by the consideration that in the rarefaction of air, its specific heat is changed, and thus its temperature reduced below the constituent temperature of the vapor which it contains. The latter argument is answered by a reference to Dalton's law of the mixture of gases. We must consider the establishment of this doctrine in a new section as the most material step to the true notion of evaporation. 170. Sect 3. Dalton's doctrine of evaporation. A portion of that which appears to be the true notion of evaporation was known, with greater or less distinctness, to several of the physical philosophers of whom we have spoken. They were aware that the vapor which exists in air, in an invisible state, may be condensed into water by cold, and they had noticed that in any state of the atmosphere, there is a certain temperature lower than that of the atmosphere, to which, if we depress bodies, water forms upon them in fine drops like dew. This temperature is thence called the dew point. The vapor of water which exists anywhere may be reduced below the degree of heat which is necessary to constitute it vapor, and thus it ceases to be vapor. Hence this temperature is also called the constituent temperature. This was generally known to the meteorological speculators of the last century, although, in England, attention was principally called to it by Dr. Wells's essay on dew in 1814. This doctrine readily explains how the cold produced by rarefaction of air, descending below the constituent temperature of the contained vapor, may precipitate a dew, and thus, as we have said, refutes one obvious objection to the theory of independent vapor. The other difficulty was first fully removed by Mr. Dalton. When his attention was drawn to the subject of vapor, he saw insurmountable objections to the doctrine of a chemical union of water and air. In fact, this doctrine was a mere nominal explanation, for, on closer examination, no chemical analogies supported it. After some reflection, and in the sequel of other generalizations concerning gases, he was led to the persuasion that when air and steam are mixed together, each follows its separate laws of equilibrium, the particles of each being elastic with regard to those of their own kind only, so that steam may be conceived as flowing among the particles of air, like a stream of water among pebbles. And the resistance which air offers to evaporation arises, not from its weight, but from the inertia of its particles. It will be found that the theory of independent vapor, understood with these conditions, will include all the facts of the case gradual evaporation in air, sudden evaporation in a vacuum, the increase of 171 the air's elasticity by vapor, condensation by its various causes, and other phenomena. But Mr. Dalton also made experiments to prove his fundamental principle that if two different gases communicate, they will diffuse themselves through each other, slowly, if the opening of communication be small. He observes also that all the gases had equal solvent powers for vapor, which could hardly have happened had chemical affinity been concerned. Nor does the density of the air make any difference. Taking all these circumstances into the account, Mr. Dalton abandoned the idea of solution. In the autumn of 1801, he says, I hit upon an idea which seemed to be exactly calculated to explain the phenomena of vapor. It gave rise to a great variety of experiments, which ended in fixing it in his mind as a true idea. But, he adds, the theory was almost universally misunderstood and consequently reprobated. Mr. Dalton answers various objections. Berthollet had urged that we can hardly conceive the particles of an elastic substance added to those of another without increasing its elasticity. To this, Mr. Dalton replies by adducing the instance of magnets, which repel each other, but do not repel other bodies. One of the most curious and ingenious objections is that of Emgo, who argues that if each gas is elastic with regard to itself alone, we should hear, produced by one stroke, 4 sounds, namely, first, the sound through aqueous vapor, second, the sound through azotic gas, third, the sound through oxygen gas, fourth, the sound through carbonic acid. Mr. Dalton's answer is that the difference of time at which these sounds would come is very small, and that, in fact, we do hear sounds double and treble. In his new system of chemical philosophy, Mr. Dalton considers the objections of his opponents with singular candor and impartiality. He there appears disposed to abandon that part of the theory which negatives the mutual repulsion of the particles of the two gases, and to attribute their diffusion through one another to the different size of the particles, which would, he thinks, produce the same effect. In selecting, as of permanent importance, the really valuable part of this theory, we must endeavor to leave out all that is doubtful or unproved. I believe it will be found that in all theories hitherto, 172, promulgated, all assertions respecting the properties of the particles of bodies, their sizes, distances, attractions, and the like, are insecure and superfluous. Passing over, then, such hypotheses, the inductions which remain are these: that two gases which are in communication will, by the elasticity of each, diffuse themselves in one another, quickly or slowly. And that the quantity of steam contained in a certain space of air is the same, whatever be the air, whatever be its density, and even if there be a vacuum. These propositions may be included together by saying that one gas is mechanically mixed with another, and we cannot but assent to what Mr. Dalton says of the latter fact. This is certainly the touchstone of the mechanical and chemical theories. This doctrine of the mechanical mixture of gases appears to supply answers to all the difficulties opposed to it by Berthollet and others, as Mr. Dalton has shown, and we may, therefore, accept it as well established. This doctrine, along with the principle of the constituent temperature of steam, is applicable to a large series of meteorological and other consequences. But before considering the applications of theory to natural phenomena which have been made, it will be proper to speak of researches which were carried on, in a great measure, in consequence of the use of steam in the arts. I mean the laws which connect its elastic force with its constituent temperature. Sect. 4. Determination of the laws of the elastic force of steam. The expansion of aqueous vapor at different temperatures is governed, like that of all other vapors, by the law of Dalton and Gay-Lussac, already mentioned. And from this, its elasticity, when its expansion is resisted, will be known by the law of Boyle and Marriott, namely, by the rule that the pressure of airy fluids is as the condensation. But it is to be observed that this process of calculation goes on the supposition that the steam is cut off from contact with water, so that no more steam can be generated, a case quite different from the common one, in which the steam is more abundant as the heat is greater. The examination of the force of vapor, when it is in contact with water, must be briefly noticed. During the period of which we have been speaking, the progress of the investigation of the laws of aqueous vapor was much accelerated. 173, by the growing importance of the steam engine, in which those laws operated in a practical form. James Watts, the main improver of that machine, was thus a great contributor to speculative knowledge, as well as to practical power. Many of his improvements depended on the laws which regulate the quantity of heat which goes to the formation or condensation of steam, and the observations which led to these improvements enter into the induction of latent heat. Measurements of the force of steam, at all temperatures, were made with the same view. Watts's attention had been drawn to the steam engine in 1759, by Robison, the former being then an instrument maker, and the latter a student at the University of Glasgow. In 1761 or 1762, he tried some experiments on the force of steam in a Papin's digester, and formed a sort of working model of a steam engine, feeling already his vocation to develop the powers of that invention. His knowledge was at that time principally derived from Dissiguliers and Belidor, but his own experiments added to it rapidly. In 1764 and 1765, he made a more systematical course of experiments, directed to ascertain the force of steam. He tried this force, however, only at temperatures above the boiling point, and inferred it at lower degrees from the supposed continuity of the law thus obtained. His friend Robison, also, was soon after led, by reading the account of some experiments of Lord Charles Cavendish and some others of Mr. Nairn, to examine the same subject. He made out a table of the correspondence of the elasticity and the temperature of vapor, from 32 to 280 degrees of Fahrenheit's thermometer. The thing here to be remarked is the establishment of a law of the pressure of steam, down to the freezing point of water. Ziegler of Basel, in 1769, and Achard of Berlin, in 1782, made similar experiments. The latter examined also the elasticity of the vapor of alcohol. Badencourt, in 1792, published his memoir on the expansive force of vapors, and his tables were for some time considered the most exact. 174 Prony, in his Architecture Hydraulique, 1796, established a mathematical formula on the experiments of Badencourt, who began his researches in the belief that he was first in the field, although he afterwards found that he had been anticipated by Ziegler. Gren compared the experiments of Badencourt and Deluc with his own. He ascertained an important fact, that when water boils, the elasticity of the steam is equal to that of the atmosphere. Schmidt at Gießen endeavored to improve the apparatus used by Badencourt, and Bijker, of Rotterdam, in 1800, made new trials for the same purpose. Note 55/10. Denis Papin, who made many of Boyle's experiments for him, had discovered that if the vapor be prevented from rising, the water becomes hotter than the usual boiling point, and had hence invented the instrument called Papin's digester. It is described in his book, La manière d'améliorer les assiettes de faire cuire toutes sortes de viandes en fort peu de temps et à peu de frais. Paris, 1682. Note 56/10. These were afterwards published in the Encyclopaedia Britannica, in the article Steam, written by Robison. In 1801, Mr. Dalton communicated to the Philosophical Society of Manchester his investigations on this subject, observing truly that though the forces at high temperatures are most important when steam is considered as a mechanical agent, the progress of philosophy is more immediately interested in accurate observations on the force at low temperatures. He also found that his elasticities for equidistant temperatures resembled a geometrical progression, but with a ratio constantly diminishing. Dr. Ure, in 1818, published in the Philosophical Transactions of London experiments of the same kind, valuable from the high temperatures at which they were made, and for the simplicity of his apparatus. The law which he thus obtained approached, like Dalton's, to a geometrical progression. Dr. Ure says that a formula proposed by M. Biot gives an error of near 9 inches out of 75, at a temperature of 266 degrees. This is very conceivable, for if the formula be wrong at all, the geometrical progress rapidly inflames the error in the higher portions of the scale. The elasticity of steam, at high temperatures, has also been experimentally examined by Mr. Southern, of Soho, and Mr. Sharp, of Manchester. Mr. Dalton has attempted to deduce certain general laws from Mr. Sharp's experiments, and other persons have offered other rules, as those which govern the force of steam with reference to the temperature. But no rule appears yet to have assumed the character of an established scientific truth. Yet the law of the expansive force of steam is not only required in order that the steam engine may be employed with safety and to the best advantage, but must also be an important point in every consistent thermotical theory. To the experiments on steam made by private physicists are to be added the experiments made on a grand scale by order of the governments of France and of America, with a view to 175 legislation on the subject of steam engines. The French experiments were made in 1823, under the direction of a commission consisting of some of the most distinguished members of the Academy of Sciences, namely, de Prony, Arago, Gerard, and Dulong. The American experiments were placed in the hands of a committee of the Franklin Institute of the State of Pennsylvania, consisting of Prof. Bach and others, in 1830. The French experiments went as high as 435 degrees of Fahrenheit's thermometer, corresponding to a pressure of 60 feet of mercury, or 24 atmospheres. The American experiments were made up to a temperature of 346 degrees, which corresponded to 274 inches of mercury, more than 9 atmospheres. The extensive range of these experiments affords great advantages for determining the law of the expansive force. The French Academy found that their experiments indicated an increase of the elastic force according to the fifth power of a binomial 1 plus mt, where T is the temperature. The American Institute were led to a sixth power of a like binomial. Other experimenters have expressed their results, not by powers of the temperature, but by geometrical ratios. Dr. Dalton had supposed that the expansion of mercury being as the square of the true temperature above its freezing point, the expansive force of steam increases in geometrical ratio for equal increments of temperature. And the author of the article Steam in the 7th edition of the Encyclopaedia Britannica, Mr. J. S. Russell, has found that the experiments are best satisfied by supposing mercury, as well as steam, to expand in a geometrical ratio for equal increments of the true temperature. It appears by such calculation that while dry gas increases in the ratio of 8 to 11 by an increase of temperature from freezing to boiling water, steam in contact with water, by the same increase of temperature above boiling water, has its expansive force increased in the proportion of 1 to 12. By an equal increase of temperature, mercury expands in about the ratio of 8 to 9. Recently, Magnus of Berlin, Halsman, and Rignault have made series of observations on the relation between temperature and elasticity of steam. Note 58/10, see Taylor's Scientific Memoirs, Aug. 1845, Volume Roman 4, Part 14, and Anne de Chimie. Prof. Magnus measured his temperatures by an air thermometer, a process which, I stated in the first edition, seemed to afford the best promise of simplifying the law of expansion. His result is that the 176 elasticity proceeds in a geometric series when the temperature proceeds in an arithmetical series nearly. The differences of temperature for equal augmentations of the ratio of elasticity being somewhat greater for the higher temperatures. The forces of the vapors of other liquids in contact with their liquids, determined by Dr. Faraday, as mentioned in Chapter Roman 2. Sect. 1, are analogous to the elasticity of steam here spoken of. Sect. 5, consequences of the doctrine of evaporation, explanation of rain, dew, and clouds. The discoveries concerning the relations of heat and moisture which were made during the last century were principally suggested by meteorological inquiries and were applied to meteorology as fast as they rose. Still, there remains, on many points of this subject, so much doubt and obscurity that we cannot suppose the doctrines to have assumed their final form, and therefore we are not here called upon to trace their progress and connection. The principles of atmology are pretty well understood, but the difficulty of observing the conditions under which they produce their effects in the atmosphere is so great that the precise theory of most meteorological phenomena is still to be determined. We have already considered the answers given to the question, according to what rules does transparent aqueous vapor resume its form of visible water? This question includes not only the problems of rain and dew, but also of clouds. For clouds are not vapor, but water, vapor being always invisible. An opinion which attracted much notice in its time was that of Hutton, who, in 1784, endeavored to prove that if two masses of air saturated with transparent vapor at different temperatures are mixed together, the precipitation of water in the form either of cloud or of drops will take place. The reason he assigned for the opinion was this: that the temperature of the mixture is a mean between the two temperatures, but that the force of the vapor in the mixture, which is the mean of the forces of the two component vapors, will be greater than that which corresponds to the mean temperature, since the force increases faster than the temperature, and hence some part of the vapor will be precipitated. This doctrine, it will be seen, speaks of vapor as saturating air and is, 177 therefore, in this form, inconsistent with Dalton's principle. But it is not difficult to modify the expression so as to retain the essential part of the explanation. Due the principle of a constituent temperature of steam and the explanation of the dew point were known, as we have said, chapter Roman 3. Sect. 3. To the meteorologists of the last century, but we perceive how incomplete their knowledge was by the very gradual manner in which the consequences of this principle were traced out. We have already noticed, as one of the books which most drew attention to the true doctrine, in this country at least, Dr. Wells's essay on dew, published in 1814. In this work, the author gives an account of the progress of his opinions. I was led, he says, in the autumn of 1784, by the event of a rude experiment, to think it probable that the formation of dew is attended with the production of cold. This was confirmed by the experiments of others. But some years after, upon considering the subject more closely, I began to suspect that Mr. Wilson, Mr. Six, and myself had all committed an error in regarding the cold which accompanies the dew, as an effect of the formation of the dew. He now considered it rather as the cause, and soon found that he was able to account for the circumstances of this formation, many of them curious and paradoxical, by supposing the bodies on which dew is deposited to be cooled down by radiation into the clear night sky to the proper temperature. The same principle will obviously explain the formation of mists over streams and lakes when the air is cooler than the water, which was put forward by Davy even in 1810 as a new doctrine, or at least not familiar. Hygrometers, according as air has more or less of vapor in comparison with that which its temperature and pressure enable it to contain, it is more or less humid, and an instrument which measures the degrees of such a gradation is a hygrometer. The hygrometers which were at first invented were those which measured the moisture by its effect in producing expansion or contraction in certain organic substances. Thus de Saussure devised a hair hygrometer, De Luca a whalebone hygrometer, and Dalton used a piece of whipcord. All these contrivances were variable in the amount of their indications under the same circumstances, and, moreover, it was not easy to know the physical meaning of the degree indicated. The dew point, or constituent temperature of the vapor which exists in the air, is on 178 the other hand, both constant and definite. The determination of this point as a datum for the moisture of the atmosphere was employed by Leroy and by Dalton 1802, the condensation being obtained by cold water. And finally, Mr. Daniel 1812 constructed an instrument where the condensing temperature was produced by evaporation of ether in a very convenient manner. This invention, Daniel's hygrometer, enables us to determine the quantity of vapor which exists in a given mass of the atmosphere at any time of observation. Note 61/10, Daniel Met. S. p. 142, Manch. Mem. Volume V.P. 581. As a happy application of the atmological laws which have been discovered, I may mention the completion of the theory and use of the wet bulb hygrometer, an instrument in which, from the depression of temperature produced by wetting the bulb of a thermometer, we infer the further depression which would produce dew. Of this instrument, the history is thus summed up by Prof. Forbes. Hutton invented the method. Leslie revived and extended it, giving probably the earliest, though an imperfect theory. Gay-Lussac, by his excellent experiments and reasoning from them, completed the theory. So far as perfectly dry air is concerned, Ivory extended the theory, which was reduced to practice by August and Bohnenberger, who determined the constant with accuracy. English observers have done little more than confirm the conclusions of our industrious Germanic neighbors. Nevertheless, the experiments of Upjohn and Prinsep must ever be considered as conclusively settling the value of the coefficient near the one extremity of the scale, as those of Kiemp's have done for the other. Prof. Forbes' two reports on the recent progress and present state of meteorology, given among the reports of the British Association for 1832 and 1840, contain a complete and luminous account of recent researches on this subject. It may perhaps be asked why I have not given meteorology a place among the inductive sciences, but if the reader refers to these accounts or any other adequate view of the subject, he will see that meteorology is not a single inductive science, but the application of several sciences to the explanation of terrestrial and atmospheric phenomena. Of the sciences so applied, thermotics and atmology are the principal ones. But others also come into play, as optics in the explanation of rainbows, halos, 179. Parhelia, Coronae, glories, and the like. Electricity in the explanation of thunder and lightning, hail, aurora borealis, to which others might be added. Clouds when vapor becomes visible by being cooled below its constituent temperature. It forms itself into a very fine watery powder, the diameter of the particles of which this powder consists being very small. They are estimated by various writers, from 1/100,000th to 1/20,000th of an inch. Such particles, even if solid, would descend very slowly, and very slight causes would suffice for their suspension, without recurring to the hypothesis of vesicles, of which we have already spoken. Indeed, that hypothesis will not explain the fact, except we suppose these vesicles filled with a rarer air than that of the atmosphere. And accordingly, though this hypothesis is still maintained by some, it is asserted as a fact of observation, proved by optical or other phenomena, and not deduced from the suspension of clouds. Yet the latter result is still variously explained by different philosophers. Thus, M. Gay-Lussac accounts for it by upward currents of air, and Fresnel explains it by the heat and rarefaction of air in the interior of the cloud. Classification of clouds. A classification of clouds can then only be consistent and intelligible when it rests upon their atmological conditions. Such a system was proposed by Mr. Luke Howard in 18023. His primary modifications are cirrus, cumulus, and stratus, which the Germans have translated by terms equivalent in English to feather cloud, heap cloud, and layer cloud. The cumulus increases by accumulations on its top and floats in the air with a horizontal base. The stratus grows from below and spreads along the earth. The cirrus consists of fibers in the higher regions of the atmosphere, which grow every way. Between the simple modifications are intermediate ones, cirrocumulus and cirrostratus, and again, compound ones, the cumulostratus and the nimbus, or rain cloud. These distinctions have been generally accepted all over Europe, and have rendered a description of all the processes which go on in the atmosphere far more definite and clear than it could be made before their use. I omit a mass of facts and opinions, supposed laws of phenomena and assigned causes, which abound in meteorology more than in any other science. The slightest consideration will show us what a great 180 amount of labor, of persevering and combined observation, the progress of this branch of knowledge requires. I do not even speak of the condition of the more elevated parts of the atmosphere. The diminution of temperature as we ascend, one of the most marked of atmospheric facts, has been variously explained by different writers. Thus Dalton, 1808, refers it to a principle that each atom of air in the same perpendicular column is possessed of the same degree of heat, which principle he conceives to be entirely empirical in this case. Fourier says, 1817, this phenomenon results from several causes. One of the principal is the progressive extinction of the rays of heat in the successive strata of the atmosphere. Leaving, therefore, the application of thermotical and atmological principles in particular cases, let us consider for a moment the general views to which they have led philosophers. Chapter 4. Physical Theories of Heat. When we look at the condition of that branch of knowledge which, according to the phraseology already employed, we must call physical thermotics, in opposition to formal thermotics, which gives us detached laws of phenomena, we find the prospect very different from that which was presented to us by physical astronomy, optics, and acoustics. In these sciences, the maintainers of a distinct and comprehensive theory have professed at least to show that it explains and includes the principal laws of phenomena of various kinds. In thermotics, we have only attempts to explain a part of the facts. We have here no example of an hypothesis which, assumed in order to explain one class of phenomena, has been found also to account exactly for another. As when central forces led to the precession of the equinoxes, or when the explanation of polarization explained also double refraction, or when the pressure of the atmosphere, as measured by the barometer, gave the true velocity of sound. Such coincidences, or consiliences, as I have elsewhere called them, are the test of truth, and thermotical theories cannot yet exhibit credentials of this kind. 181. On looking back at our view of this science, it will be seen that it may be distinguished into two parts: the doctrines of conduction and radiation, which we call thermotics proper, and the doctrines respecting the relation of heat, airs, and moisture, which we have termed etymology. These two subjects differ in their bearing on our hypothetical views. Thermotical theories, the phenomena of radiant heat, like those of radiant light, obviously admit of general explanation in two different ways: by the emission of material particles or by the propagation of undulations. Both these opinions have found supporters. Probably most persons, in adopting Provost's theory of exchanges, conceive the radiation of heat to be the radiation of matter. The undulation hypothesis, on the other hand, appears to be suggested by the production of heat by friction, and was accordingly maintained by Rumford and others. Leslie appears, in a great part of his inquiry, to be a supporter of some undulatory doctrine, but it is extremely difficult to make out what his undulating medium is, or rather, his opinions wavered during his progress. In page 31, he asks, "What is this calorific and frigorific fluid?" And after keeping the reader in suspense for a moment, he replies, "Quod pedis hic est, it is merely the ambient air." But at page 150, he again asks the question, and at page 188, he answers, "It is the same subtile matter that, according to its different modes of existence, constitutes either heat or light." A person thus vacillating between two opinions, one of which is palpably false, and the other laden with exceeding difficulties, which he does not even attempt to remove, had little right to protest against the sportive freaks of some intangible aura, to rank all other hypotheses than his own with the occult qualities of the schools, and to class the prejudices of his opponents with the tenets of those who maintained the fuga vacui in opposition to Torricelli. It is worth while noticing this kind of rhetoric, in order to observe that it may be used just as easily on the wrong side as on the right. Note 68/10, An Experimental Inquiry into the Nature and Propagation of Heat, 1804. Till recently, the theory of material heat, and of its propagation by emission, was probably the one most in favor with those who had studied mathematical thermotics. As we have said, the laws of 182 conduction, in their ultimate analytical form, were almost identical with the laws of motion of fluids. Fourier's principle also, that the radiation of heat takes place from points below the surface, and is intercepted by the superficial particles, appears to favor the notion of material emission. Accordingly, some of the most eminent modern French mathematicians have accepted and extended the hypothesis of a material caloric. In addition to Fourier's doctrine of molecular extraradiation, Laplace and Poisson have maintained the hypothesis of molecular intraradiation as the mode in which conduction takes place. That is, they say that the particles of bodies are to be considered as discrete, or as points separated from each other and acting on each other at a distance, and the conduction of heat from one part to another is performed by radiation between all neighboring particles. They hold that, without this hypothesis, the differential equations expressing the conditions of conduction cannot be made homogeneous. But this assertion rests, I conceive, on an error, as Fourier has shown, by dispensing with the hypothesis. The necessity of the hypothesis of discrete molecular action in bodies is maintained in all cases by M. Poisson, and he has asserted Laplace's theory of capillary attraction to be defective on this ground, as Laplace asserted Fourier's reasoning respecting heat to be so. In reality, however, this hypothesis of discrete molecules cannot be maintained as a physical truth, for the law of molecular action, which is assumed in the reasoning, after answering its purpose in the progress of calculation, vanishes in the result. The conclusion is the same, whatever law of the intervals of the molecules be assumed. The definite integral, which expresses the whole action, no more proves that this action is actually made of the differential parts by means of which it was found, than the processes of finding the weight of a body by integration prove it to be made up of differential weights. And therefore, even if we were to adopt the emission theory of heat, we are by no means bound to take along with it the hypothesis of discrete molecules. But the recent discovery of the refraction, polarization, and depolarization of heat has quite altered the theoretical aspect of the subject, and almost at a single blow, ruined the emission theory. Since heat is reflected and refracted like light, analogy would lead us to conclude that the mechanism of the processes is the same in the two cases. And when we add to these properties the property of polarization, it is scarcely possible to believe otherwise than that heat consists in 183 transverse vibrations. For no wise philosopher would attempt an explanation by ascribing poles to the emitted particles, after the experience which optics affords of the utter failure of such machinery. But here the question occurs: if heat consists in vibrations, whence arises the extraordinary identity of the laws of its propagation with the laws of the flow of matter? How is it that, in conducted heat, this vibration creeps slowly from one part of the body to another, the part first heated remaining hottest, instead of leaving its first place and traveling rapidly to another, as the vibrations of sound and light do? The answer to these questions has been put in a very distinct and plausible form by that distinguished philosopher, M. Ampere, who published a note on heat and light considered as the results of vibratory motion in 1834 and 1835. And though this answer is an hypothesis, it at least shows that there is no fatal force in the difficulty. Note 70/10, Bibliothèque Universelle de Genève, Volume Roman 49, p. 225, and Chim, Tom, Elvi, p. 434. M. Ampere's hypothesis is this: that bodies consist of solid molecules, which may be considered as arranged at intervals in a very rare ether, and that the vibrations of the molecules, causing vibrations of the ether and caused by them, constitute heat. On these suppositions, we should have the phenomena of conduction explained. For if the molecules at one end of a bar be hot, and therefore in a state of vibration, while the others are at rest, the vibrating molecules propagate vibrations in the ether, but these vibrations do not produce heat, except in proportion as they put the quiescent molecules of the bar in vibration. And the ether being very rare compared with the molecules, it is only by the repeated impulses of many successive vibrations that the nearest quiescent molecules are made to vibrate, after which they combine in communicating the vibration to the more remote molecules. We then find necessarily, M. Ampere adds, the same equations as those found by Fourier for the distribution of heat, setting out from the same hypothesis, that the temperature or heat transmitted is proportional to the difference of the temperatures. Since the undulatory hypothesis of heat can thus answer all obvious objections, we may consider it as upon its trial to be confirmed or modified by future discoveries, and especially by an enlarged knowledge of the laws of the polarization of heat. Since the first edition was written, though analogies between light and heat have been further extended, as I have already stated. It 184 has been discovered by Biot and Melloni that quartz impresses a circular polarization upon heat, and by Prof. Forbes that mica, of a certain thickness, produces phenomena such as would be produced by the impression of circular polarization of the supposed transversal vibrations of radiant heat. And further, a rhomb of rock salt, of the shape of the glass rhomb, which verified Fresnel's extraordinary anticipation of the circular polarization of light, verified the expectation, founded upon other analogies, of the polarization of heat. By passing polarized heat through various thicknesses of mica, Prof. Forbes has attempted to calculate the length of an undulation for heat. These analogies cannot fail to produce a strong disposition to believe that light and heat, essences so closely connected that they can hardly be separated, and thus shown to have so many curious properties in common, are propagated by the same machinery. And thus, we are led to an undulatory theory of heat. Yet such a theory has not yet by any means received full confirmation. It depends upon the analogy and the connection of the theory of light, and would have little weight if those were removed. For the separation of the rays in double refraction and the phenomena of periodical intensity, the two classes of facts out of which the undulatory theory of optics principally grew, have neither of them been detected in thermotical experiments. Prof. Forbes has assumed alternations of heat for increasing thicknesses of mica, but in his experiments we find only one maximum. The occurrence of alternate maxima and minima under the like circumstances would exhibit visible waves of heat, as the fringes of shadows do of light, and would thus add much to the evidence of the theory. Even if I conceived the undulatory theory of heat to be now established, I should not venture, as yet, to describe its establishment as an event in the history of the inductive sciences. It is only at an interval of time after such events have taken place that their history and character can be fully understood, so as to suggest lessons in the philosophy of science. Atmological theories' hypotheses of the relations of heat and air almost necessarily involve a reference to the forces by which the composition of bodies is produced, and thus cannot properly be treated of till we have surveyed the condition of chemical knowledge. But we may say a few words on one such hypothesis. I mean the hypothesis on the subject of the atmological laws of heat, proposed by Laplace in the 12th book of the Mécanique Céleste, and published in 1823. 185. It will be recollected that the main laws of phenomena for which we have to account, by means of such an hypothesis, are the following. 1. The law of Boyle and Marriott that the elasticity of an air varies as its density. See chapter Roman 3, sect. 1 of this book. 2. The law of Gay-Lussac and Dalton that all airs expand equally by heat. See chapter Roman 2, sect. 1. 3. The production of heat by sudden compression. See chapter Roman 2, sect. 2. 4. Dalton's principle of the mechanical mixture of airs. See chapter Roman 3, sect. 3. 5. The law of expansion of solids and fluids by heat. See chapter Roman 2, sect. 1. 6. Changes of consistence by heat and the doctrine of latent heat. See chapter Roman 2, sect. 3. 7. The law of the expansive force of steam. See chapter Roman 3, sect. 4. Besides these, there are laws of which it is doubtful whether they are or are not included in the preceding, as the low temperature of the air in the higher parts of the atmosphere. See chapter Roman 3, sect. 5. Laplace's hypothesis is this, that bodies consist of particles, each of which gathers round it, by its attraction, a quantity of caloric. That the particles of the bodies attract each other, besides attracting the caloric, and that the particles of the caloric repel each other. In gases, the particles of the bodies are so far removed that their mutual attraction is insensible, and the matter tends to expand by the mutual repulsion of the caloric. He conceives this caloric to be constantly radiating among the particles. The density of this internal radiation is the temperature, and he proves that, on this supposition, the elasticity of the air will be as the density, and as this temperature. Hence follow the 3 first rules above stated. The same suppositions lead to Dalton's principle of mixtures, 4, though without involving his mode of conception. For Laplace says that whatever the mutual action of 2 gases be, the whole pressure will be equal to the sum of the separate pressures. Expansion, 5, and the changes of consistence, 6, are explained by supposing that in solids, the mutual attraction of the particles of the body is the greatest force. In liquids, the attraction of the particles for the caloric. In airs, the repulsion of 186, the caloric. But the doctrine of latent heat again modifies the hypothesis and makes it necessary to include latent heat in the calculation. Yet there is not, as we might suppose there would be if the theory were the true one, any confirmation of the hypothesis resulting from the new class of laws thus referred to. Nor does it appear that the hypothesis accounts for the relation between the elasticity and the temperature of steam. It will be observed that Laplace's hypothesis goes entirely upon the materiality of heat and is inconsistent with any vibratory theory. For, as Ampère remarks, it is clear that if we admit heat to consist in vibrations, it is a contradiction to attribute to heat, or caloric, a repulsive force of the particles which would be a cause of vibration. An unfavorable judgment of Laplace's theory of gases is suggested by looking for that which, in speaking of optics, was mentioned as the great characteristic of a true theory, namely, that the hypotheses, which were assumed in order to account for one class of facts, are found to explain another class of a different nature, the consilience of inductions. Thus, in thermotics, the law of an intensity of radiation proportional to the sine of the angle of the ray with the surface, which is founded on direct experiments of radiation, is found to be necessary in order to explain the tendency of neighboring bodies to equality of temperature. And this leads to the higher generalization that heat is radiant from points below the surface. But in the doctrine of the relation of heat to gases, as delivered by Laplace, there is none of this unexpected confirmation. And though he explains some of the leading laws, his assumptions bear a large proportion to the laws explained. Thus, from the assumption that the repulsion of gases arises from the mutual repulsion of the particles of caloric, he finds that the pressure in any gas is as the square of the density and of the quantity of caloric. And from the assumption that the temperature is the internal radiation, he finds that this temperature is as the density and the square of the caloric. Hence, he obtains the law of Boyle and Marriott, and that of Dalton and Gay-Lussac. But this view of the subject requires other assumptions when we come to latent heat, and accordingly, he introduces, to express the latent heat, a new quantity. Yet this quantity produces no effect on his calculations, nor does he apply his reasoning to any problem in which latent heat is concerned. 187. Without, then, deciding upon this theory, we may venture to say that it is wanting in all the prominent and striking characteristics which we have found in those great theories, which we look upon as clearly and indisputably established. Conclusion: we may observe, moreover, that heat has other bearings and effects, which, as soon as they have been analyzed into numerical laws of phenomena, must be attended to in the formation of thermotical theories. Chemistry will probably supply many such. Those which occur to us we must examine hereafter. But we may mention as examples of such, de la Rive and Marcet's law, that the specific heat of all gases is the same, and Dulong and Petty's law, that single atoms of all simple bodies have the same capacity for heat. Though we have not yet said anything of the relation of different gases, or explained the meaning of atoms in the chemical sense, it will easily be conceived that these are very general and important propositions. Thus the science of thermotics, imperfect as it is, forms a highly instructive part of our survey, and is one of the cardinal points on which the doors of those chambers of physical knowledge must turn which hitherto have remained closed. For, on the one hand, this science is related by strong analogies and dependencies to the most complete portions of our knowledge, our mechanical doctrines and optical theories. And on the other, it is connected with properties and laws of a nature altogether different those of chemistry. Properties and laws depending upon a new system of notions and relations, among which clear and substantial general principles are far more difficult to lay hold of, and with which the future progress of human knowledge appears to be far more concerned. To these notions and relations we must now proceed. But we shall find an intermediate stage in certain subjects which I shall call the mechanico-chemical sciences, viz., those which have to do with magnetism, electricity, and galvanism. 189, Book 11. The Mechanico-Chemical Sciences. History of Electricity. Parva medu primo, mox sees extolit in horas ingreditur solo, et caput inter nubila condit, Roman 4, 176. A timid breath at first, a transient touch. How soon it swells from little into much, runs o'er the ground, and springs into the air, and fills the tempest's gloom, the lightning's glare, while denser darkness than the central storm conceals the secrets of its inward form. 191. Introduction. Of the Mechanico-Chemical Sciences. Under the title of Mechanico-Chemical Sciences, I include the laws of magnetism, electricity, galvanism, and the other classes of phenomena closely related to these, as thermoelectricity. This group of subjects forms a curious and interesting portion of our physical knowledge, and not the least of the circumstances which give them their interest is that double bearing upon mechanical and chemical principles, which their name is intended to imply. Indeed, at first sight they appear to be purely mechanical sciences. The attractions and repulsions, the pressure and motion, which occur in these cases, are referable to mechanical conceptions and laws, as completely as the weight or fall of terrestrial bodies, or the motion of the moon and planets. And if the phenomena of magnetism and electricity had directed us only to such laws, the corresponding sciences must have been arranged as branches of mechanics. But we find that, on the other side, these phenomena have laws and bearings of a kind altogether different. Magnetism is associated with electricity by its mechanical analogies, and more recently has been discovered to be still more closely connected with it by physical influence. Electric is identified with galvanic agency, but in galvanism, decomposition, or some action of that kind universally appears, and these appearances lead to very general laws. Now composition and decomposition are the subjects of chemistry, and thus we find that we are insensibly but irresistibly led into the domain of that science. The highest generalizations to which we can look, in advancing from the elementary facts of electricity and galvanism, must involve chemical notions. We must, therefore, in laying out the platform of these sciences, make provision for that convergence of mechanical and chemical theory which they are to exhibit as we ascend. We must begin, however, with stating the mechanical phenomena of these sciences and the reduction of such phenomena to laws. In this point of view, the phenomena of which we have to speak are those in which bodies exhibit attractions and repulsions, peculiarly determined by their nature and circumstances, as the magnet and a 192 piece of amber when rubbed. Such results are altogether different from the universal attraction, which, according to Newton's discovery, prevails among all particles of matter, and to which cosmical phenomena are owing. But yet the difference of these special attractions and of cosmical attraction was at first so far from being recognized that the only way in which men could be led to conceive or assent to an action of one body upon another at a distance, in cosmical cases, was by likening it to magnetic attraction, as we have seen in the history of physical astronomy. And we shall, in the first part of our account, not dwell much upon the peculiar conditions under which bodies are magnetic or electric, since these conditions are not readily reducible to mechanical laws, but, taking the magnetic or electric character for granted, we shall trace its effects. The habit of considering magnetic action as the type or general case of attractive and repulsive agency explains the early writers having spoken of electricity as a kind of magnetism. Thus Gilbert, in his book De Magnete, 1600, has a chapter, De Coition Magnetica, Primunc de Sacchini Attraction, Sive Virius Corporum ad Succinum Application. The manner in which he speaks shows us how mysterious the fact of attraction then appeared, so that, as he says, the magnet and amber were called in aid by philosophers as illustrations, when our sense is in the dark in abstruse inquiries, and when our reason can go no further. Gilbert speaks of these phenomena like a genuine inductive philosopher, reproving those who before him had stuffed the booksellers' shops by copying from one another extravagant stories concerning the attraction of magnets and amber, without giving any reason from experiment. He himself makes some important steps in the subject. He distinguishes magnetic from electric forces, and is the inventor of the latter name, derived from letter 1F24 lambda epsilon capitau rho omicron U, electron, amber. He observes rightly that the electric force attracts all light bodies, while the magnetic force attracts iron only, and he devises a satisfactory apparatus by which this is shown. He gives a considerable list of bodies which possess the electric property. Not only amber and agate attract small bodies, as some think, but diamond, sapphire, carbuncle, opal, amethyst, Bristol gem, berylli, crystal, glass of antimony, spar of various kinds, sulfur, mastic, sealing wax, and other substances which he mentions. Even his speculations on the general laws of these phenomena, though vague and erroneous, as 193 at that period was unavoidable, do him no discredit when compared with the doctrines of his successors a century and a half afterwards. But such speculations belong to a succeeding part of this history. In treating of these sciences, I will speak of electricity in the first place, although it is thus separated by the interposition of magnetism from the succeeding subjects, galvanism, and C, with which its alliance seems, at first sight, the closest, and although some general notions of the laws of magnets were obtained at an earlier period than a knowledge of the corresponding relations of electric phenomena. For the theory of electric attraction and repulsion is somewhat more simple than of magnetic. Was, in fact, the first obtained, and was of use in suggesting and confirming the generalization of magnetic laws. Chapter 1. Discovery of laws of electric phenomena. We have already seen what was the state of this branch of knowledge at the beginning of the 17th century, and the advances made by Gilbert. We must now notice the additions which it subsequently received, and especially those which led to the discovery of general laws and the establishment of the theory. Events of this kind being those of which we have more peculiarly to trace the conditions and causes. Among the facts which we have thus especially to attend to are the electric attractions of small bodies by amber and other substances when rubbed. Boyle, who repeated and extended the experiments of Gilbert, does not appear to have arrived at any new general notions. But Otto Guericke of Magdeburg, about the same time, made a very material step by discovering that there was an electric force of repulsion as well as of attraction. He found that when a globe of sulfur had attracted a feather, it afterwards repelled it, till the feather had been in contact with some other body. This, when verified under a due generality of circumstances, forms a capital fact in our present subject. Hawkesby, who wrote in 1709 Physico-Mechanical Experiments, also observed various of the effects of attraction and repulsion upon threads hanging loosely. But the person who appears to have first fully seized the general law of these facts is 194 Dufay, whose experiments appear in the Memoirs of the French Academy in 1733, 1734, and 1737. I discovered, he says, a very simple principle, which accounts for a great part of the irregularities, and, if I may use the term, the caprices that seem to accompany most of the experiments in electricity. This principle is that electric bodies attract all those that are not so, and repel them as soon as they are become electric by the vicinity or contact of the electric body. Upon applying this principle to various experiments of electricity, anyone will be surprised at the number of obscure and puzzling facts which it clears up. By the help of this principle, he endeavors to explain several of Hawkesby's experiments. Note 5/11, Priestley's History of Electricity, p. 45, and the memoirs quoted. A little anterior to Dufay's experiments were those of Gray, who, in 1729, discovered the properties of conductors. He found that the attraction and repulsion which appear in electric bodies are exhibited also by other bodies in contact with the electric. In this manner, he found that an ivory ball, connected with a glass tube by a stick, a wire, or a packthread, attracted and repelled a feather, as the glass itself would have done. He was then led to try to extend this communication to considerable distances, first by ascending to an upper window and hanging down his ball, and, afterwards, by carrying the string horizontally supported on loops. As his success was complete in the former case, he was perplexed by failure in the latter. But when he supported the string by loops of silk instead of hempen cords, he found it again become a conductor of electricity. This he ascribed at first to the smaller thickness of the silk, which did not carry off so much of the electric virtue. But from this explanation, he was again driven by finding that wires of brass still thinner than the silk destroyed the effect. Thus Gray perceived that the efficacy of the support depended on its being silk, and he soon found other substances which answered the same purpose. The difference, in fact, depended on the supporting substance being electric, and therefore not itself a conductor. For it soon appeared from such experiments, and especially from those made by Dufay, that substances might be divided into electrics per se and non-electrics, or conductors. These terms were introduced by dissiguliers and gave a permanent currency to the results of the labors of Gray and others. Another very important discovery belonging to this period is that 195 of the two kinds of electricity. This also was made by Dufay. Chance, says he, has thrown in my way another principle more universal and remarkable than the preceding one, and which casts a new light upon the subject of electricity. The principle is that there are two distinct kinds of electricity, very different from one another, one of which I call vitreous, the other resinous electricity. The first is that of glass, gems, hair, wool, and sea. The second is that of amber, gumlac, silk, and sea. The characteristic of these two electricities is that they repel themselves and attract each other. This discovery does not, however, appear to have drawn so much attention as it deserved. It was published in 1735, in the Memoirs of the Academy for 1733. And yet, in 1747, Franklin and his friends at Philadelphia, who had been supplied with electrical apparatus and information by persons in England well acquainted with the then present state of the subject, imagined that they were making observations unknown to European science, when they were led to assert two conditions of bodies, which were in fact the opposite electricities of Dufay. Though the American experimenters referred them to a single element of which electrized bodies might have either excess or defect. Hence, Franklin says, have arisen some new terms among us. We say B, who receives a spark from glass, and bodies in like circumstances is electrized positively. A, who communicates his electricity to glass, negatively, or rather B is electrized plus, a minus. Dr. afterwards Sir William Watson had about the same time arrived at the same conclusions, which he expresses by saying that the electricity of A was more rare, and that of B more dense, than it naturally would have been. But that which gave the main importance to this doctrine was its application to some remarkable experiments, of which we must now speak. Electric action is accompanied in many cases by light and a crackling sound. Otto Guericke observes that his sulfur globe, when rubbed in a dark place, gave faint flashes, such as take place when sugar is crushed. And shortly after, a light was observed at the surface of the mercury in the barometer, when shaken, which was explained at first by Bernoulli on the then prevalent Cartesian principles, but afterwards more truly by Hawkesby as an electrical phenomenon. Wall in 1708 found sparks produced by rubbing amber, and Hawkesby observed the light and the snapping, as he calls it, under various modifications. But the electric spark from a living body, which, as 196 Priestley says, makes a principal part of the diversion of gentlemen and ladies who come to see experiments in electricity, was first observed by Dufay and the Abbé Nollet. Nollet says he shall never forget the surprise which the first electric spark ever drawn from the human body excited, both in M. Dufay and in himself. The drawing of a spark from the human body was practiced in various forms, one of which was familiarly known as the electrical kiss. Other exhibitions of electrical light were the electrical star, electrical rain, and the like. Note 11/11, Priestley, p. 47, Nollet, Leçons de Physique, Volume Roman 6, p. 408. As electricians determined more exactly the conditions of electrical action, they succeeded in rendering more intense those sudden actions which the spark accompanies, and thus produced the electric shock. This was especially done in the Leyden file. This apparatus received its name, while the discovery of its property was attributed to Cunius, a native of Leyden, who, in 1746, handling a vessel containing water in communication with the electrical machine, and happening thus to bring the inside and the outside into connection, received a sudden shock in his arms and breast. It appears, however, that a shock had been received under nearly the same circumstances in 1746 by von Kleist, a German prelate, at Kamen in Pomerania. The strangeness of this occurrence and the suddenness of the blow much exaggerated the estimate which men formed of its force. Muschenbroek, after taking one shock, declared he would not take a second for the kingdom of France, though Bose, with a more magnanimous spirit, wished that he might die by such a stroke, and have the circumstances of the experiment recorded in the memoirs of the Academy. But we may easily imagine what a new fame and interest this discovery gave to the subject of electricity. It was repeated in all parts of the world, with various modifications, and the shock was passed through a line of several persons holding hands. Nollet, in the presence of the King of France, sent it through a circle of 180 men of the guards, and along a line of men and wires of 900 toises. And experiments of the same kind were made in England, principally under the direction of Watson, on a scale so large as to excite the admiration of Muschenbroek, who says, in a letter to Watson, Magnificentissimus tuis experimentis supersti canatus omnium. The result was that the transmission of electricity through a length of 12,000 feet was, to sense, instantaneous. 197. The essential circumstances of the electric shock were gradually unraveled. Watson found that it did not increase in proportion either to the contents of the phial or the size of the globe by which the electricity was excited, that the outside coating of the glass, which, in the first form of the experiment, was only a film of water, and its contents might be varied in different ways. To Franklin is due the merit of clearly pointing out most of the circumstances on which the efficacy of the Leyden phial depends. He showed, in 1747, that the inside of the bottle is electrized positively, the outside negatively, and that the shock is produced by the restoration of the equilibrium when the outside and inside are brought into communication suddenly. But in order to complete this discovery, it remained to be shown that the electric matter was collected entirely at the surface of the glass, and that the opposite electricities on the two opposite sides of the glass were accumulated by their mutual attraction. Monnier, the younger, discovered that the electricity which bodies can receive depends upon their surface rather than their mass, and Franklin soon found that the whole force of the bottle and power of giving a shock is in the glass itself. This they proved by decanting the water out of an electrized into another bottle, when it appeared that the second bottle did not become electric, but the first remained so. Thus it was found that the non-electrics, in contact with the glass, served only to unite the force of the several parts. So far as the effect of the coating of the Leyden phial is concerned, this was satisfactory and complete. But Franklin was not equally successful in tracing the action of the electric matter upon itself, in virtue of which it is accumulated in the phial. Indeed, he appears to have ascribed the effect to some property of the glass. The mode of describing this action varied, accordingly as two electric fluids were supposed, with Dufay, or one, which was the view taken by Franklin. On this latter supposition, the parts of the electric fluid repel each other, and the excess in one surface of the glass expels the fluid from the other surface. This kind of action, however, came into much clearer view in the experiments of Canton, Wilk, and Epochs. It was principally manifested in the attractions and repulsions which objects exert when they are in the neighborhood of electrized bodies, or in the electrical atmosphere, using the phraseology of the time. At present, we say that bodies are electrized by induction, when they are 198, thus made electric by the electric attraction and repulsion of other bodies. Canton's experiments were communicated to the Royal Society in 1753 and show that the electricity on each body acts upon the electricity of another body, at a distance, with a repulsive energy. Wilk, in like manner, showed that parts of non-electrics, plunged in electric atmospheres, acquire an electricity opposite to that of such atmospheres. And Epochs devised a method of examining the nature of the electricity at any part of the surface of a body, by means of which he ascertained its distribution, and found that it agreed with such a law of self-repulsion. His attempt to give mathematical precision to this induction was one of the most important steps towards electrical theory, and must be spoken of shortly in that point of view. But in the meantime, we may observe that this doctrine was applied to the explanation of the Leyden jar, and the explanation was confirmed by charging a plate of air and obtaining a shock from it in a manner which the theory pointed out. Before we proceed to the history of the theory, we must mention some other of the laws of phenomena which were noticed, and which theory was expected to explain. Among the most celebrated of these were the effect of sharp points in conductors and the phenomena of electricity in the atmosphere. The former of these circumstances was one of the first which Franklin observed as remarkable. It was found that the points of needles and the like throw off and draw off the electric virtue. Thus a bodkin, directed towards an electrized ball, at 6 or 8 inches distance, destroyed its electric action. The latter subject, involving the consideration of thunder and lightning, and of many other meteorological phenomena, excited great interest. The comparison of the electric spark to lightning had very early been made, but it was only when the discharge had been rendered more powerful in the Leyden jar that the comparison of the effects became very plausible. Franklin, about 1750, had offered a few somewhat vague conjectures respecting the existence of electricity in the clouds, but it was not till Wilk and Epochs had obtained clear notions of the effect of electric matter at a distance that the real condition of the clouds could be well understood. In 1752, however, Dalibard and other French philosophers were desirous of verifying Franklin's conjecture of the analogy of thunder and electricity. This they did by erecting a pointed iron rod, 40 feet high, 199 at Marly. The rod was found capable of giving out electrical sparks when a thundercloud passed over the place. This was repeated in various parts of Europe, and Franklin suggested that a communication with the clouds might be formed by means of a kite. By these and similar means, the electricity of the atmosphere was studied by Canton in England, Mézières in France, Beccaria in Italy, and others elsewhere. These essays soon led to a fatal accident, the death of Richman at Petersburg, while he was on Aug. 6, 1753, observing the electricity collected from an approaching thundercloud, by means of a rod which he called an electrical gnomon. A globe of blue fire was seen to leap from the rod to the head of the unfortunate professor, who was thus struck dead. As an important application of the doctrines of electricity, I may mention the contrivances employed to protect ships from the effects of lightning. The use of conductors in such cases is attended with peculiar difficulties. In 1780, the French began to turn their attention to this subject, and Leroy was sent to Brest and the various seaports of France for that purpose. Chains temporarily applied in the rigging had been previously suggested, but he endeavored to place, he says, such conductors in ships as might be fixed and durable. He devised certain long-linked rods, which led from a point in the masthead along a part of the rigging, or in divided stages along the masts, and were fixed to plates of metal in the ship's sides communicating with the sea. But these were either unable to stand the working of the rigging, or otherwise inconvenient, and were finally abandoned. The conductor commonly used in the English Navy, till recently, consisted of a flexible copper chain, tied, when occasion required, to the masthead and reaching down into the sea, a contrivance recommended by Dr. Watson in 1762. But notwithstanding this precaution, the shipping suffered greatly from the effects of lightning. Mr. Snow Harris, now Sir William Snow Harris, whose electrical labors are noticed above, proposed to the Admiralty, in 1820, a plan which combined the conditions of ship conductors, so desirable yet so difficult to secure, namely that they should be permanently fixed and sufficiently large, and yet should in no way interfere with the motion of the rigging or with the sliding masts. The method which he proposed was to make the masts themselves conductors of electricity, 200, by incorporating with them, in a peculiar way, 2 laminae of sheet copper, uniting these with the metallic masses in the hull by other laminae, and giving the whole a free communication with the sea. This method was tried experimentally, both on models and to a large extent in the Navy itself, and a commission appointed to examine the result reported themselves highly satisfied with Mr. Harris's plan, and strongly recommended that it should be fully carried out in the Navy. It is not here necessary to trace the study of atmospheric electricity any further, and we must now endeavor to see how these phenomena and laws of phenomena which we have related were worked up into consistent theories. For though many experimental observations and measures were made after this time, they were guided by the theory, and may be considered as having rather discharged the office of confirming than of suggesting it. We may observe also that we have now described the period of most extensive activity and interest in electrical researches. These naturally occurred while the general notions and laws of the phenomena were becoming, and were not yet become, fixed and clear. At such a period, a large and popular circle of spectators and amateurs feel themselves nearly upon a level, in the value of their trials and speculations, with more profound thinkers. At a later period, when the subject is become a science, that is, a study in which all must be left far behind who do not come to it with disciplined, informed, and logical minds, the cultivators are far more few, and the shout of applause less tumultuous and less loud. We may add, too, that the experiments, which are the most striking to the senses, lose much of their impressiveness with their novelty. Electricity, to be now studied rightly, must be reasoned upon mathematically. How slowly such a mode of study makes its way, we shall see in the progress of the theory, which we must now proceed to narrate. A new mode of producing electricity has excited much notice lately. In October 1840, one of the workmen in attendance upon a boiler belonging to the Newcastle and Durham Railway reported that the boiler was full of fire, the fact being that when he placed his hand near it an electrical spark was given out. This drew the attention of Mr. Armstrong and Mr. Pattinson, who made the circumstance publicly known. Mr. Armstrong pursued the investigation, 201, with great zeal, and after various conjectures was able to announce that the electricity was excited at the point where the steam is subject to friction in its emission. He found, too, that he could produce a like effect by the emission of condensed air. Following out his views, he was able to construct, for the Polytechnic Institution in London, a hydroelectric machine of greater power than any electrical machine previously made. Dr. Faraday took up the investigation as the subject of the 18th series of his researches, sent to the Royal Society, Jan. 26, 1842. And in this, he illustrated, with his usual command of copious and luminous experiments, a like view, that the electricity is produced by the friction of the particles of the water carried along by the asterisk steam. And thus this is a new manifestation of that electricity, which, to distinguish it from voltaic electricity, is sometimes called friction electricity or machine electricity. Dr. Faraday has, however, in the course of this investigation, brought to light several new electrical relations of bodies. Chapter 2. The Progress of Electrical Theory. The cause of electrical phenomena and the mode of its operation were naturally at first spoken of in an indistinct and wavering manner. It was called the electric fire, the electric fluid. Its effects were attributed to virtues, effluvia, atmospheres. When men's mechanical ideas became somewhat more distinct, the motions and tendencies to motion were ascribed to currents, in the same manner as the cosmical motions had been in the Cartesian system. This doctrine of currents was maintained by Nollet, who ascribed all the phenomena of electrized bodies to the contemporaneous afflux and efflux of electrical matter. It was an important step towards sound theory to get rid of this notion of moving fluids and to consider attraction and repulsion as statical forces, and this appears to have been done by others about the same time. Dufay considered that he had proved the existence of two electricities, the vitreous and the resinous, and conceived each 202 of these to be a fluid which repelled its own parts and attracted those of the other. This is, in fact, the outline of the theory which recently has been considered as the best established, but from various causes it was not at once, or at least not generally adopted. The hypothesis of the excess and defect of a single fluid is capable of being so treated as to give the same results with the hypothesis of two opposite fluids, and happen to obtain the preference for some time. We have already seen that this hypothesis, according to which electric phenomena arose from the excess and defect of a generally diffused fluid, suggested itself to Watson and Franklin about 1747. Watson found that when an electric body was excited, the electricity was not created, but collected, and Franklin held that when the Leyden jar was charged, the quantity of electricity was unaltered, though its distribution was changed. Simmer maintained the existence of two fluids, and Cygnus supplied the main defect which belonged to this tenet in the way in which Dufay held it, by showing that the two opposite electricities were usually produced at the same time. Still, the apparent simplicity of the hypothesis of one fluid procured it many supporters. It was that which Franklin adopted in his explanation of the Leyden experiment. And though after the first conception of an electrical charge as a disturbance of equilibrium, there was nothing in the development or details of Franklin's views which deserved to win for them any peculiar authority, his reputation and his skill as a writer gave a considerable influence to his opinions. Indeed, for a time he was considered, over a large part of Europe, as the creator of the science, and the terms Franklinism, Franklinist, Franklinian system occur in almost every page of continental publications on the subject. Yet the electrical phenomena to the knowledge of which Franklin added least, those of induction, were those by which the progress of the theory was most promoted. These, as we have already said, were at first explained by the hypothesis of electrical atmospheres. Lord Mahon wrote a treatise in which this hypothesis was mathematically treated. Yet the hypothesis was very untenable, for it would not account for the most obvious cases of induction, such as the Leyden jar, except the atmosphere was supposed to penetrate glass. The phenomena of electricity by induction, when fairly considered by a person of clear notions of the relations of space and force, were seen to accommodate themselves very generally to the conception, 203, introduced by Dufay, of two electricities each repelling itself and attracting the other. If we suppose that there is only one fluid, which repels itself and attracts all other matter, we obtain, in many cases, the same general results as if we suppose two fluids. Thus, if an electrized body, overcharged with the single fluid, act upon a ball, it drives the electric fluid in the ball to the further side by its repulsion, and then attracts the ball by attracting the matter of the ball more than it repels the fluid which is upon the ball. If we suppose two fluids, the positively electrized body draws the negative fluid to the nearer side of the ball, repels the positive fluid to the opposite side, and attracts the ball on the whole. because the attracted fluid is nearer than that which is repelled. The verification of either of these hypotheses and the determination of their details depended necessarily upon experiment and calculation. It was under the hypothesis of a single fluid that this trial was first properly made. Epochs of Petersburg published, in 1759, his Tentamen Theoriae Electricitatis et Magnetismi, in which he traces mathematically the consequences of the hypothesis of an electric fluid, attracting all other matter, but repelling itself. The law of force of this repulsion and attraction he did not pretend to assign precisely, confining himself to the supposition that the mutual force of the particles increases as the distance decreases. But it was found that in order to make this theory tenable, an additional supposition was required, namely, that the particles of bodies repel each other as much as they attract the electric fluid. For if two bodies, A and B, be in their natural electrical condition, they neither attract nor repel each other. Now, in this case, the fluid in A attracts the matter in B and repels the fluid in B with equal energy, and thus no tendency to motion results from the fluid in A, and if we further suppose that the matter in A attracts the fluid in B and repels the matter in B with equal energy, we have the resulting mutual inactivity of the two bodies explained. But without the latter supposition, there would be a mutual attraction. Or we may put the truth more simply thus. Two negatively electrized bodies repel each other. If negative electrization were merely the abstraction of the fluid which is the repulsive element, this result could not follow except there were a repulsion in the bodies themselves, independent of the fluid. And thus Epochs found himself compelled to assume this mutual repulsion of material particles. He had, in fact, the 204 alternative of this supposition, or that of two fluids, to choose between, for the mathematical results of both hypotheses are the same. Wilck, a Swede, who had at first asserted and worked out the opinion theory in its original form, afterwards inclined to the opinion of Simmer. And Coulomb, when, at a later period, he confirmed the theory by his experiments and determined the law of force, did not hesitate to prefer the theory of two fluids. Because, he says, it appears to me contradictory to admit at the same time, in the particles of bodies, an attractive force in the inverse ratio of the squares of the distances, which is demonstrated by universal gravitation, and a repulsive force in the same inverse ratio of the squares of the distances. A force which would necessarily be infinitely great relatively to the action of gravitation. We may add that by forcing us upon this doctrine of the universal repulsion of matter, the theory of a single fluid seems quite to lose that superiority in the way of simplicity which had originally been its principal recommendation. The mathematical results of the supposition of Epochs, which are, as Coulomb observes, the same as of that of the two fluids, were traced by the author himself in the work referred to, and shown to agree in a great number of cases with the observed facts of electrical induction, attraction, and repulsion. Apparently this work did not make its way very rapidly through Europe. For in 1771, Henry Cavendish stated the same hypothesis in a paper read before the Royal Society, which he prefaces by saying, "Since I first wrote the following paper, I find that this way of accounting for the phenomena of electricity is not new." Epochs, in his Tentamen Theoriae Electricitatis et Magnetismi, has made use of the same, or nearly the same hypothesis that I have, and the conclusions he draws from it agree nearly with mine as far as he goes. The confirmation of the theory was, of course, to be found in the agreement of its results with experiment, and in particular, in the facts of electrical induction, attraction, and repulsion, which suggested the theory. Epochs showed that such a confirmation appeared in a number of the most obvious cases, and to these Cavendish added others, which, though not obvious, were of such a nature that the calculations, in general difficult or impossible, could in these instances be easily performed. As, for example, cases in which there are plates or globes at the two extremities of a long wire. In all these cases of 205 electrical action, the theory was justified. But in order to give it full confirmation, it was to be considered whether any other facts, not immediately assumed in the foundation of the theory, were explained by it, a circumstance which, as we have seen, gave the final stamp of truth to the theories of astronomy and optics. Now we appear to have such confirmation, in the effective points and in the phenomena of the electrical discharge. The theory of neither of these was fully understood by Cavendish, but he made an approach to the true view of them. If one part of a conducting body be a sphere of small radius, the electric fluid upon the surface of this sphere will, it appears by calculation, be more dense, and tend to escape more energetically, in proportion as the radius of the sphere is smaller, and, therefore, if we consider a point as part of the surface of a sphere of imperceptible radius, it follows from the theory that the effort of the fluid to escape at that place will be enormous, so that it may easily be supposed to overcome the resisting causes. And the discharge may be explained in nearly the same manner. For when a conductor is brought nearer and nearer to an electrized body, the opposite electricity is more and more accumulated by attraction on the side next to the electrized body. Its tension becomes greater by the increase of its quantity and the diminution of the distance, and at last it is too strong to be contained and leaps out in the form of a spark. The light, sound, and mechanical effects produced by the electric discharge made the electric fluid to be not merely considered as a mathematical hypothesis, useful for reducing phenomena to formulae, as for a long time the magnetic fluid was, but caused it to be at once and universally accepted as a physical reality, of which we learn the existence by the common use of the senses, and of which measures and calculations are only wanted to teach us the laws. The applications of the theory of electricity, which I have principally considered above, are those which belong to conductors, in which the electric fluid is perfectly movable and can take that distribution which the forces require. In non-conducting or electric bodies, the conditions to which the fluid is subject are less easy to determine. But by supposing that the fluid moves with great difficulty among the particles of such bodies that, nevertheless, it may be dislodged and accumulated in parts of the surface of such bodies, by friction and other modes of excitement, and that the earth is an inexhaustible reservoir of electric matter, the principal facts of excitation and the like receive a tolerably satisfactory explanation. 206. The theory of epochs, however, still required to have the law of action of the particles of the fluid determined. If we were to call to mind how momentous an event in physical astronomy was the determination of the law of the cosmical forces, the inverse square of the distance, and were to suppose the importance and difficulty of the analogous step, in this case to be of the same kind, this would be to mistake the condition of science at that time. The leading idea, the conception of the possibility of explaining natural phenomena by means of the action of forces on rigorously mechanical principles, had already been promulgated by Newton, and was, from the first, seen to be peculiarly applicable to electrical phenomena, so that the very material step of clearly proposing the problem, often more important than the solution of it, had already been made. Moreover, the confirmation of the truth of the assumed cause in the astronomical case depended on taking the right law, but the electrical theory could be confirmed, in a general manner at least, without this restriction. Still, it was an important discovery that the law of the inverse square prevailed in these as well as in cosmical attractions. It was impossible not to conjecture beforehand that it would be so. Cavendish had professed in his calculations not to take the exponent of the inverse power, on which the force depended, to be strictly 2, but to leave it indeterminate between 1 and 3. But in his applications of his results, he obviously inclines to the assumption that it is 2. Experimenters tried to establish this in various ways. Robison, in 1769, had already proved that the law of force is very nearly or exactly the inverse square, and Mayer had discovered, but not published, the same result. The clear and satisfactory establishment of this truth is due to Coulomb, and was one of the first steps in his important series of researches on the subject. In his first paper in the Memoirs of the Academy for 1785, he proves this law for small globes. In his second memoir, he shows it to be true for globes 1 and 2 feet in diameter. His invention of the torsion balance, which measures very small forces with great certainty and exactness, enabled him to set this question at rest forever. The law of force being determined for the particles of the electric fluid, it now came to be the business of the experimenter and the 207 mathematician to compare the results of the theory in detail with those of experimental measures. Coulomb undertook both portions of the task. He examined the electricity of portions of bodies by means of a little disk, his tangent plane, which he applied to them and then removed, and which thus acted as a sort of electric taster. His numerical results, the intensity being still measured by the torsion balance, are the fundamental facts of the theory of the electrical fluid. Without entering into detail, we may observe that he found the electricity to be entirely collected at the surface of conductors, which Beccaria had before shown to be the case, and that he examined and recorded the electric intensity at the surface of globes, cylinders, and other conducting bodies, placed within each other's influence in various ways. The mathematical calculation of the distribution of two fluids, all the particles of which attract and repel each other according to the above law, was a problem of no ordinary difficulty. As may easily be imagined, when it is recollected that the attraction and repulsion determine the distribution, and the distribution reciprocally determines the attraction and repulsion. The problem was of the same nature as that of the figure of the Earth, and its rigorous solution was beyond the powers of the analysis of Coulomb's time. He obtained, however, approximate solutions with much ingenuity. For instance, in a case in which it was obvious that the electric fluid would be most accumulated at and near the equator of a certain sphere, he calculated the action of the sphere on two suppositions. First, that the fluid was all collected precisely at the equator, and next, that it was uniformly diffused over the surface. And he then assumed the actual case to be intermediate between these two. By such artifices, he was able to show that the results of his experiments and of his calculations gave an agreement sufficiently near to entitle him to consider the theory as established on a solid basis. Thus, at this period, mathematics was behind experiment, and a problem was proposed in which theoretical numerical results were wanted for comparison with observation, but could not be accurately obtained. As was the case in astronomy also, till the time of the approximate solution of the problem of three bodies, and the consequent formation of the tables of the moon and planets on the theory of universal gravitation. After some time, electrical theory was relieved from this reproach, mainly in consequence of the progress which astronomy had occasioned in pure mathematics. About 1801, 208, there appeared in the Bulletin des Sciences an exact solution of the problem of the distribution of electric fluid on a spheroid, obtained by M. Biot, by the application of the peculiar methods which Laplace had invented for the problem of the figure of the planets. And in 1811, M. Poisson applied Laplace's artifices to the case of two spheres acting upon one another in contact, a case to which many of Coulomb's experiments were referable. And the agreement of the results of theory and observation, thus extricated from Coulomb's numbers, obtained above 40 years previously, was very striking and convincing. It followed also from Poisson's calculations that when two electrized spheres are brought near each other, the accumulation of the opposite electricities on their nearest points increases without limit as the spheres approach to contact, so that before the contact takes place, the external resistance will be overcome and a spark will pass. Though the relations of nonconductors to electricity and various other circumstances leave many facts imperfectly explained by the theory, yet we may venture to say that, as a theory which gives the laws of the phenomena and which determines the distribution of those elementary forces on the surface of electrized bodies, from which elementary forces, whether arising from the presence of a fluid or not, the total effects result, the doctrine of Dufay and Coulomb, as developed in the analysis of Poisson, is securely and permanently established. This part of the subject has been called statical electricity. In the establishment of the theory of this branch of science, we must, I conceive, allow to Dufay more merit than is generally ascribed to him, since he saw clearly, and enunciated in a manner which showed that he duly appreciated their capital character, the two chief principles, the conditions of electrical attraction and repulsion, and the apparent existence of two kinds of electricity. His views of attraction are, indeed, partly expressed in terms of the Cartesian hypothesis of vortices, then prevalent in France. But at the time when he wrote, these forms of speech indicated scarcely anything besides the power of attraction. Franklin's real merit as a discoverer was that he was one of the first who distinctly conceived the electrical charge as a derangement of equilibrium. The great fame which, in his day, he enjoyed arose from the clearness and spirit with which he narrated his discoveries, from his dealing with electricity in the imposing form of thunder and lightning, and partly, perhaps, from his character as an 209 American and a politician. For he was already, in 1736, engaged in public affairs as clerk to the General Assembly of Pennsylvania, though it was not till a later period of his life that his admirers had the occasion of saying of him Erepuit Caelis fulmen sceptrumque tyrannies, born to control all lawless force, all fierce and baleful sway. The thunder's bolt, the tyrant's rod, alike he wrenched away. Eponus and Coulomb were two of the most eminent physical philosophers of the last century, and labored in the way peculiarly required by that generation, whose office it was to examine the results, in particular subjects, of the general conception of attraction and repulsion, as introduced by Newton. The reasonings of the Newtonian period had in some measure anticipated all possible theories resembling the electrical doctrine of Eponus and Coulomb, and on that account this doctrine could not be introduced and confirmed in a sudden and striking manner, so as to make a great epoch. Accordingly, Dufay, Simmer, Watson, Franklin, Eponus, and Coulomb have all a share in the process of induction. With reference to these founders of the theory of electricity, Poisson holds the same place which Laplace holds with reference to Newton. The reception of the Coulombian theory, so we most call it, for the Epinian theory implies one fluid only, has hitherto not been so general as might have been reasonably expected from its very beautiful accordance with the facts which it contemplates. This has partly been owing to the extreme abstruseness of the mathematical reasoning which it employs, and which put it out of the reach of most experimenters and writers of works of general circulation. The theory of Eponus was explained by Robison in the Encyclopaedia Britannica. The analysis of Poisson has recently been presented to the public in the Encyclopaedia Metropolitana, but is of a kind not easily mastered even by most mathematicians. On these accounts probably it is that in English compilations of science, we find, even to this day, the two theories of one and of two fluids stated as if they were nearly on a par in respect of their experimental evidence. Still, we may say that the Coulombian theory is probably assented to by all who have examined it, at least as giving the laws of phenomena, and I have not heard of any denial of it from such a quarter, or of any attempt to show it to be erroneous by detailed and measured experiments. Mr. Snow Harris, 210, has recently described some important experiments and measures, but his apparatus was of such a kind that the comparison of the results with the Coulombian theory was not easy, and indeed the mathematical problems which Mr. Harris's combinations offered require another Poisson for their solution. Still, the more obvious results are such as agree with the theory, even in the cases in which their author considered them to be inexplicable. For example, he found that by doubling the quantity of electricity of a conductor, it attracted a body with 4 times the force. But the body not being insulated would have its electricity also doubled by induction, and thus the fact was what the theory required. Though it is thus highly probable that the Coulombian theory of electricity, or the Epinian, which is mathematically equivalent, will stand as a true representation of the law of the elementary actions, we must yet allow that it has not received that complete evidence by means of experiments and calculations added to those of its founders, which the precedents of other permanent sciences have led us to look for. The experiments of Coulomb, which he used in the establishment of the theory, were not very numerous, and they were limited to a peculiar form of bodies, namely spheres. In order to form the proper sequel to the promulgation of this theory, to give a full confirmation, and to ensure its general reception, we ought to have experiments more numerous and more varied, such as those of Mr. Harris, are shown to agree in all respects with results calculated from the theory. This would, as we have said, be a task of labor and difficulty, but the person who shall execute it will deserve to be considered as one of the real founders of the true doctrine of electricity. To show that the coincidence between theory and observation, which has already been proved for spherical conductors, obtains also for bodies of other forms, will be a step in electricity analogous to what was done in astronomy, when it was shown that the law of gravitation applied to comets as well as to planets. But although we consider the views of Eponus or Coulomb in a very high degree probable as a formal theory, the question is very different when we come to examine them as a physical theory. That is, when we inquire whether there really is a material electric fluid or fluids. Question of one or two fluids in the first place as to the question whether the fluids are one or two. Coulomb's introduction of 211. The hypothesis of two fluids has been spoken of as a reform of the theory of Eponus. It would probably have been more safe to have called his labors an advance in the calculation, and in the comparison of hypothesis with experiment, than to have used language which implied that the question between the rival hypotheses of one or two fluids could be treated as settled. For in reality, if we assume, as Eponus does, the mutual repulsion of all the particles of matter, in addition to the repulsion of the particles of the electric fluid for one another and their attraction for the particles of matter, the one fluid of Eponus will give exactly the same results as the two fluids of Coulomb. The mathematical formulae of Coulomb and of Poisson express the conditions of the one case as well as of the other, the interpretation only being somewhat different. The place of the forces of the resinous fluid is supplied by the excess of the forces ascribed to the matter above the forces of the fluid, in the parts where the electric fluid is deficient. The obvious argument against this hypothesis is that we ascribe to the particles of matter a mutual repulsion, in addition to the mutual attraction of universal gravitation, and that this appears incongruous. Accordingly, Eponus says that when he was first driven to this proposition, it horrified him. But we may answer it in this way very satisfactorily. If we suppose the mutual repulsion of matter to be somewhat less than the mutual attraction of matter and electric fluid, it will follow, as a consequence of the hypothesis, that besides all obvious electrical action, the particles of matter would attract each other with forces varying inversely as the square of the distance. Thus, gravitation itself becomes an electrical phenomenon, arising from the residual excess of attraction over repulsion, and the fact which is urged against the hypothesis becomes a confirmation of it. By this consideration, the prerogative of simplicity passes over to the side of the hypothesis of one fluid, and the rival view appears to lose at least all its superiority. Note 37:11, Nec diffiter cum ipsa si mihi offerit, mi ad ipsum quadmodo exoruis, tentamen theor, elect, p. 39. Very recently, M. Masati has calculated the results of the opinion theory in a far more complete manner than had previously been performed, using Laplace's coefficients, as Poisson had done for the 212 Coulombian theory. He finds that, from the supposition of a fluid and of particles of matter exercising such forces as that theory assumes, with the very allowable additional supposition that the particles are small compared with their distances, it follows that the particles would exert a force repulsive at the smallest distances, a little further on vanishing, afterwards attractive, and at all sensible distances attracting in proportion to the inverse square of the distance. Thus, there would be a position of stable equilibrium for the particles at a very small distance from each other, which may be, M. Masati suggests, that equilibrium on which their physical structure depends. According to this view, the resistance of bodies to compression and to extension, as well as the phenomena of statical electricity and the mutual gravitation of matter, are accounted for by the same hypothesis of a single fluid or ether. A theory which offers a prospect of such a generalization is worth attention. But a very clear and comprehensive view of the doctrines of several sciences is requisite to prepare us to estimate its value and probable success. Note 38:11, Sur les forces qui régissent la constitution intérieure des corps. Turin, 1836. Question of the material reality of the electric fluidet. First cite the beautiful accordance of the experiments with calculations founded upon the attractions and repulsions of the two hypothetical fluids, persuade us that the hypotheses must be the real state of things. But we have already learned that we must not trust to such evidence too readily. It is a curious instance of the mutual influence of the histories of two provinces of science, but I think it will be allowed to be just to say that the discovery of the polarization of heat has done much to shake the theory of the electric fluids as a physical reality. For the doctrine of a material caloric appeared to be proved from the laws of conduction and radiation by the same kind of mathematical evidence, the agreement of laws respecting the elementary actions with those of fluids, which we have for the doctrine of material electricity. Yet we now seem to see that heat cannot be matter, since its rays have sides, in a manner in which a stream of particles of matter cannot have sides without inadmissible hypotheses. We see, then, that it will not be contrary to precedent if our electrical theory, representing with perfect accuracy the laws of the actions, in all their forms, simple and complex, should yet be fallacious as a view of the cause of the actions. Any true view of electricity must include, or at least be consistent with, the other classes of the phenomena as well as this statical electrical action, such as the conditions of excitation and retention of 213 electricity, to which we may add the connection of electricity with magnetism and with chemistry, a vast field as yet dimly seen. Now, even with regard to the simplest of these questions, the cause of the retention of electricity at the surface of bodies, it appears to be impossible to maintain Coulomb's opinion that this is affected by the resistance of air to the passage of electricity. The other questions are such as Coulomb did not attempt to touch. They refer, indeed, principally to laws not suspected at his time. How wide and profound a theory must be which deals worthily with these, we shall obtain some indications in the succeeding part of our history. But it may be said on the other side that we have the evidence of our senses for the reality of an electric fluid. We see it in the spark. We hear it in the explosion. We feel it in the shock, and it produces the effects of mechanical violence, piercing and tearing the bodies through which it passes. And those who are disposed to assert a real fluid on such grounds may appear to be justified in doing so by one of Newton's rules of philosophizing, in which he directs the philosopher to assume, in his theories, causes which are true. The usual interpretation of a vera causa has been that it implies causes which, independently of theoretical calculations, are known to exist by their mechanical effects, as gravity was familiarly known to exist on the earth before it was extended to the heavens. The electric fluid might seem to be such a vera causa. To this I should venture to reply that this reasoning shows how delusive the Newtonian rule, so interpreted, may be. For a moment's consideration will satisfy us that none of the circumstances above adduced can really prove material currents, rather than vibrations or other modes of agency. The spark and shock are quite insufficient to supply such a proof. Sound is vibrations, light is vibrations, vibrations may affect our nerves and may rend a body, as when glasses are broken by sounds. Therefore, all these supposed indications of the reality of the electric fluid are utterly fallacious. In truth, this mode of applying Newton's rule consists in elevating our first rude and unscientific impressions into a supremacy over the results of calculation, generalization, and systematic induction. 214. Note asterisk 39/11. On the subject of this Newtonian rule of philosophizing, see further Phil. Ind. Sc. B. Roman 12. C. 13. I have given an account of the history and evidence of the theory of electricity in the reports of the British Association for 1835. I may seem there to have spoken more favorably of the theory as a physical theory than I have done here. This difference is principally due to a consideration of the present aspect of the theory of heat. Thus, our conclusion with regard to this subject is that if we wish to form a stable physical theory of electricity, we must take into account not only the laws of statical electricity, which we have been chiefly considering, but the laws of other kinds of agency, different from the electric, yet connected with it. For the electricity of which we have hitherto spoken, and which is commonly excited by friction, is identical with galvanic action, which is a result of chemical combinations and belongs to chemical philosophy. The connection of these different kinds of electricity with one another leads us into a new domain, but we must, in the first place, consider their mechanical laws. We now proceed to another branch of the same subject, magnetism. 215, Book 12. Mechanico-Chemical Sciences. Continued. History of magnetism. If esse, ut interifera munera militiae per maria ac terras omnes sapita quiescent. Nam tu sola pots tranquilla pace juver mortals. Quoniam belli fera munera mavers armipotens regit, ingremium qui seep tuum si regicit, eterno divictus vulner amoris, ac ita suspicions to ready service reposta. Passit amoria vidos in hyens in d vicis, ec tuo pendit risupini spiritus or. Hunc tu, diva, tuo recubentum corpor sancto circumfusa super, suaves ex or liquellas fund, petens placidum romanes, includa, pacem, lucret. I-31. O charming goddess, whose mysterious sway the unseen hosts of earth and sky obey, to whom, though cold and hard to all besides, the iron god by strong affection glides, flings himself eager to thy close embrace, and bends his head to gaze upon thy face, do thou, what time thy fondling arms are thrown around his form, and he is all thy own, do thou, thy Rome to save, thy power to prove, beg him to grant a boon for thy dear love, beg him no more in battlefields to deal, or crush the nations with his mailed heel, but, touched and softened by a worthy flame, quit sword and spear, and seek a better fame. Bid him to make all war and slaughter cease, and ply his genuine task in arts of peace, and by thee guided o'er the trackless surge, bear wealth and joy to ocean's farthest verge. 217, Chapter 1. Discovery of laws of magnetic phenomena. The history of magnetism is in a great degree similar to that of electricity, and many of the same persons were employed in the two trains of research. The general fact that the magnet attracts iron was nearly all that was known to the ancients, and is frequently mentioned and referred to, for instance, by Pliny, who wonders and declaims concerning it in his usual exaggerated style. The writers of the stationary period, in this subject as in others, employed themselves in collecting and adorning a number of extravagant tales, which the slightest reference to experiment would have disproved. As, for example, that a magnet, when it has lost its virtue, has it restored by goat's blood. Gilbert, whose work De Magnete we have already mentioned, speaks with becoming indignation and pity of this bookish folly, and repeatedly asserts the paramount value of experiments. He himself, no doubt, acted up to his own precepts, for his work contains all the fundamental facts of the science, so fully examined indeed, that even at this day we have little to add to them. Thus, in his first book, the subjects of the third, fourth, and fifth chapters are that the magnet has poles, that we may call these poles the North and the South Pole, that in two magnets the North Pole of each attracts the South Pole and repels the North Pole of the other. This is, indeed, the cardinal fact on which our generalizations rest, and the reader will perceive at once its resemblance to the leading phenomena of statical electricity. But the doctrines of magnetism, like those of heat, have an additional claim on our notice from the manner in which they are exemplified in the globe of the Earth. The subject of terrestrial magnetism forms a very important addition to the general facts of magnetic attraction and repulsion. The property of the magnet by which it directs its poles exactly or nearly north and south, when once discovered, was of immense importance to the mariner. It does not, 218, appear easy to trace with certainty the period of this discovery. Passing over certain legends of the Chinese, as at any rate not bearing upon the progress of European science, the earliest notice of this property appears to be contained in the poem of Guillaume de Provence, who describes the needle as being magnetized, and then placed in or on a straw, floating on water, as I presume, puis si tourne la pointe tout contre l'estel sans doubt, that is, it turns towards the pole star. This account would make the knowledge of this property in Europe anterior to 1200. It was afterwards found that the needle does not point exactly towards the north. Gilbert was aware of this deviation, which he calls the variation, and also that it is different in different places. He maintained on theoretical principles also that at the same place the variation is constant. Probably in his time, there were not any recorded observations by which the truth of this assertion could be tested. It was afterwards found to be false. The alteration of the variation in proceeding from one place to another was, it will be recollected, one of the circumstances which most alarmed the companions of Columbus in 1492. Gilbert says, other learned men have in long navigations observed the differences of magnetic variations, as Thomas Harriot, Robert Hughes, Edward Wright, Abraham Kendall, all Englishmen. Others have invented magnetic instruments and convenient modes of observation, such as are requisite for those who take long voyages, as William Burrough in his book concerning the variation of the compass, William Barlow in his supplement, William Norman in his new attractive. This is that Robert Norman, a good seaman and an ingenious artificer, who first discovered the dip of magnetic iron. This important discovery was made in 1576. From the time when the difference of the variation of the compass in different places became known, it was important to mariners to register the variation in all parts of the world. Halley was appointed to the command of a ship in the Royal Navy by the government of William and Mary, with orders to seek by observation the discovery of the rule for the variation of the compass. He published magnetic charts, which 219 have been since corrected and improved by various persons. The most recent are those of Mr. Yates in 1817 and of M. Hanstein. The dip, as well as the variation, was found to be different in different places. M. Humboldt, in the course of his travels, collected many such observations, and both the observations of variation and of dip seem to indicate that the Earth, as to its effect on the magnetic needle, may, approximately at least, be considered as a magnet, the poles of which are not far removed from the Earth's poles of rotation. Thus we have a magnetic equator, in which the needle has no dip, and which does not deviate far from the Earth's equator, although, from the best observations, it appears to be by no means a regular circle. And the phenomena, both of the dip and of the variation, in high northern latitudes, appear to indicate the existence of a pole below the surface of the Earth to the north of Hudson's Bay. In his second remarkable expedition into those regions, Captain Ross is supposed to have reached the place of this pole, the dipping needle there pointing vertically downwards, and the variation compass turning towards this point in the adjacent regions. We shall hereafter have to consider the more complete and connected views which have been taken of terrestrial magnetism. In 1633, Gellibrand discovered that the variation is not constant, as Gilbert imagined, but that at London it had diminished from 11 degrees east in 1580 to 4 degrees in 1633. Since that time, the variation has become more and more westerly. It is now about 25 degrees west, and the needle is supposed to have begun to travel eastward again. The next important fact which appeared with respect to terrestrial magnetism was that the position of the needle is subject to a small diurnal variation. This was discovered in 1722 by Graham, a philosophical instrument maker, of London. The daily variation was established by 1,000 observations of Graham and confirmed by 4,000 more made by Canton, and is now considered to be out of dispute. It appeared also, by Canton's researches, that the diurnal variation undergoes an annual inequality, being nearly 1/4 of a degree in June and July, and only half that quantity in December and January. Having thus noticed the principal facts which belong to terrestrial magnetism, we must return to the consideration of those phenomena which gradually led to a consistent magnetic theory. Gilbert observed that both smelted iron and hammered iron have the magnetic virtue, 220, though in a weaker degree than the magnet itself, and he asserted distinctly that the magnet is merely an ore of iron, lib. IC 16, quod magnes et vena ferri idem sunt. He also noted the increased energy which magnets acquire by being armed, that is, fitted with a cap of polished iron at each pole. But we do not find, till a later period, any notice of the distinction which exists between the magnetical properties of soft iron and of hard steel, the latter being susceptible of being formed into artificial magnets, with permanent poles, while soft iron is only passively magnetic, receiving a temporary polarity from the action of a magnet near it, but losing this property when the magnet is removed. About the middle of the last century, various methods were devised of making artificial magnets, which exceeded in power all magnetic bodies previously known. The remaining experimental researches had so close an historical connection with the theory that they will be best considered along with it, and to that, therefore, we now proceed. Chapter 2. Progress of Magnetic Theory. Theory of magnetic action. The assumption of a fluid, as a mode of explaining the phenomena, was far less obvious in magnetic than in electric cases, yet it was soon arrived at. After the usual philosophy of the Middle Ages, the forms of Aquinas, the efflux of Cusanus, the vapors of Costius, and the like, which are recorded by Gilbert, we have his own theory, which he also expresses by ascribing the effects to a formal efficiency. A. Form of primary globes. The proper entity and existence of their homogeneous parts, which we may call a primary and radical and astral form, of which forms there is one in the sun, one in the moon, one in the earth, the latter being the magnetic virtue. Without attempting to analyze the precise import of these expressions, we may proceed to Descartes' explanation of magnetic phenomena. The mode in which he presents this subject is, perhaps, the 221 most persuasive of his physical attempts. If a magnet be placed among iron filings, these arrange themselves in curved lines, which proceed from one pole of the magnet to the other. It was not difficult to conceive these to be the traces of currents of ethereal matter which circulate through the magnet, and which are thus rendered sensible even to the eye. When phenomena could not be explained by means of one vortex, several were introduced. 3 memoirs on magnetism, written on such principles, had the prize adjudged by the French Academy of Sciences in 1746. But the Cartesian philosophy gradually declined, and it was not difficult to show that the magnetic curves, as well as other phenomena, would, in fact, result from the attraction and repulsion of 2 poles. The analogy of magnetism with electricity was so strong and clear that similar theories were naturally proposed for the 2 sets of facts. The distinction of bodies into conductors and electrics in the one case, corresponding to the distinction of soft and hard steel in their relations to magnetism. Epochs published a theory of magnetism and electricity at the same time, 1759, and the former theory, like the latter, explained the phenomena of the opposite poles as results of the excess and defect of a magnetic fluid, which was dislodged and accumulated in the ends of the body by the repulsion of its own particles, and by the attraction of iron or steel, as in the case of induced electricity. The Pinion theory of magnetism, as of electricity, was recast by Coulomb and presented in a new shape, with 2 fluids instead of 1. But before this theory was reduced to calculation, it was obviously desirable, in the first place, to determine the law of force. In magnetic, as in electric action, the determination of the law of attraction of the particles was attended at first with some difficulty, because the action which a finite magnet exerts is a compound result of the attractions and repulsions of many points. Newton had imagined the attractive force of magnetism to be inversely as the cube of the distance, but Mayer in 1760 and Lambert a few years later asserted the law to be, in this as in other forces, the inverse square. Coulomb has the merit of having first clearly confirmed this law by the use of his torsion balance. He established, at the same time, other very important facts, for instance, that the directive magnetic force, which the Earth exerts upon a needle, is a constant quantity, parallel 222 to the magnetic meridian, and passing through the same point of the needle whatever be its position. This was the more important, because it was necessary, in the first place, to allow for the effect of the terrestrial force, before the mutual action of the magnets could be extricated from the phenomena. Coulomb then proceeded to correct the theory of magnetism. Coulomb's reform of the Pinion theory, in the case of magnetism, as in that of electricity, substituted 2 fluids, an austral and a boreal fluid, for the single fluid, and in this way removed the necessity under which Epochs found himself, of supposing all the particles of iron and steel and other magnetic bodies to have a peculiar repulsion for each other, exactly equal to their attraction for the magnetic fluid. But in the case of magnetism, another modification was necessary. It was impossible to suppose here, as in the electrical phenomena, that one of the fluids was accumulated on one extremity of a body, and the other fluid on the other extremity. For though this might appear, at first sight, to be the case in a magnetic needle, it was found that when the needle was cut into 2 halves, the half in which the austral fluid had seemed to predominate acquired immediately a boreal pole opposite to its austral pole, and a similar effect followed in the other half. The same is true into however many parts the magnetic body be cut. The way in which Coulomb modified the theory so as to reconcile it with such facts is simple and satisfactory. He supposes the magnetic body to be made up of molecules or integral parts, or, as they were afterwards called by M. Poisson, magnetic elements. In each of these elements, which are extremely minute, the fluids can be separated, so that each element has an austral and a boreal pole, but the austral pole of an element which is adjacent to the boreal pole of the next neutralizes, or nearly neutralizes, its effect, so that the sensible magnetism appears only towards the extremities of the body, as it would do if the fluids could permeate the body freely. We shall have exactly the same result as to sensible magnetic force on the one supposition and on the other, as Coulomb showed. The theory, thus freed from manifest incongruities, was to be reduced to calculation and compared with experiment. This was done in Coulomb's seventh memoir. The difficulties of calculation in this, as in the electric problem, could not be entirely surmounted by the analysis of Coulomb, but by various artifices, he obtained theoretically the 223 relative amount of magnetism at several points of a needle, and the proposition that the directive force of the Earth on similar needles saturated with magnetism was as the cube of their dimensions, conclusions which agreed with experiment. The agreement thus obtained was sufficient to give a great probability to the theory, but an improvement of the methods of calculation and a repetition of experiments was, in this as in other cases, desirable as a confirmation of the labors of the original theorist. These requisites, in the course of time, were supplied. The researches of Laplace and Legendre on the figure of the Earth had, as we have already stated, introduced some very peculiar analytical artifices applicable to the attractions of spheroids, and these methods were employed by M. Biot in 1811 to show that, on an elliptical spheroid, the thickness of the fluid in the direction of the radius would be as the distance from the center. But the subject was taken up in a more complete manner in 1824 by M. Poisson, who obtained general expressions for the attractions or repulsions of a body of any form whatever, magnetized by influence, upon a given point, and in the case of spherical bodies was able completely to solve the equations which determine these forces. Previously to these theoretical investigations, Mr. Barlow had made a series of experiments on the effect of an iron sphere upon a compass needle, and had obtained empirical formulae for the amount of the deviation of the needle, according to its dependence upon the position and magnitude of the sphere. He afterwards deduced the same formulae from a theory which was, in fact, identical with that of Coulomb, but which he considered as different, in that it supposed the magnetic fluids to be entirely collected at the surface of the sphere. He had indeed found, by experiment, that the surface was the only part in which there was any sensible magnetism, and that a thin shell of iron would produce the same effect as a solid ball of the same diameter. But this was, in fact, a most complete verification of Coulomb's theory. For though that theory did not suppose the magnetism to be collected solely at the surface, as Mr. Barlow found it, it followed from the theory that the sensible magnetic intensity assumed the same distribution, namely, a surface distribution, as if the fluids could permeate the whole body instead of the magnetic elements only. Coulomb, indeed, had not expressly noticed the result, that the sensible 224 magnetism would be confined to the surface of bodies, but he had found that, in a long needle, the magnetic fluid might be supposed to be concentrated very near the extremities, just as it is in a long electric body. The theoretical confirmation of this rule among the other consequences of the theory that the sensible magnetism would be collected at the surface was one of the results of Poisson's analysis. For it appeared that if the sum of the electric elements of the body was equal to the whole body, there would be no difference between the action of a solid sphere and very thin shell. We may, then, consider the Coulombian theory to be fully established and verified as a representation of the laws of magnetical phenomena. We may add, as a remarkable and valuable example of an ulterior step in the course of sciences, the application of the laws of the distribution of magnetism to the purposes of navigation. It had been found that the mass of iron which exists in a ship produces a deviation in the direction of the compass needle, which was termed local attraction, and which rendered the compass an erroneous guide. Mr. Barlow proposed to correct this by a plate of iron placed near the compass, the plate being of comparatively small mass, but, in consequence of its expanded form and its proximity to the needle, of equivalent effect to the disturbing cause. This proposed arrangement was not successful, because as the ship turns into different positions, it may be considered as revolving round a vertical axis. And as this does not coincide with the magnetic axis, the relative magnetic position of the disturbing parts of the ship and of the correcting plate will be altered so that they will not continue to counteract each other. In high magnetic latitudes, the correcting plate was used with success. But when iron ships became common, a correction of the effect of the iron upon the ship's compass in the general case became necessary. Mr. Airy devised the means of making this correction. By placing a magnet and a mass of iron in certain positions relative to the compass, the effect of the rest of the iron in the ship is completely counteracted in all positions. But we have still to trace the progress of the theory of terrestrial magnetism. Theory of terrestrial magnetism Gilbert had begun a plausible course of speculation on this point. We must reject, he says, in 225, the first place, that vulgar opinion of recent writers concerning magnetic mountains or a certain magnetic rock or an imaginary pole at a certain distance from the pole of the earth. For, he adds, we learn by experience that there is no such fixed pole or term in the earth for the variation. Gilbert describes the whole earth as a magnetic globe and attributes the variation to the irregular form of its protuberances, the solid parts only being magnetic. It was not easy to confirm or refute this opinion, but other hypotheses were tried by various writers. For instance, Halley had imagined, from the forms of the lines of equal variation, that there must be 4 magnetic poles. But Euler showed that the Halleyan lines would, for the most part, result from the supposition of 2 magnetic poles, and assign their position so as to represent pretty well the known state of the variation all over the world in 1744. But the variation was not the only phenomenon which required to be taken into account. The dip at different places, and also the intensity of the force, were to be considered. We have already mentioned M. de Humboldt's collection of observations of the dip. These were examined by M. Biot, with the view of reducing them to the action of 2 poles in the supposed terrestrial magnetic axis. Having, at first, made the distance of these poles from the center of the Earth indefinite, he found that his formulae agreed more and more nearly with the observations as the poles were brought nearer, and that fact and theory coincided tolerably well when both poles were at the center. In 1809, Kraft simplified this result by showing that, on this supposition, the tangent of the dip was twice the tangent of the latitude of the place as measured from the magnetic equator. But M. Hansteen, who has devoted to the subject of terrestrial magnetism a great amount of labor and skill, has shown that, taking together all the observations which we possess, we are compelled to suppose 4 magnetic poles, 2 near the North Pole and 2 near the South Pole of the terrestrial globe, and that these poles, no 2 of which are exactly opposite each other, are all in motion, with different velocities, some moving to the east and some to the west. This curious collection of facts awaits the hand of future theorists, when the ripeness of time shall invite them to the task. I had thus written in the first edition. The theorist who was needed to reduce this accumulation of facts to their laws, 226, had already laid his powerful hand upon them. Namely, M. Gauss, a mathematician not inferior to any of the great men who completed the theory of gravitation. And institutions had been established for extending the collection of the facts pertaining to it, on a scale which elevates magnetism into a companionship with astronomy. M. Hansteen's Magnetismus der Erde was published in 1819. His conclusions respecting the position of the 4 magnetic poles excited so much interest in his own country that the Norwegian Storthing, or Parliament, by a unanimous vote, provided funds for a magnetic expedition which he was to conduct along the north of Europe and Asia. And this they did at the very time when they refused to make a grant to the king for building a palace at Christiania. The expedition was made in 1828-30 and verified Hansteen's anticipations as to the existence of a region of magnetic convergence in Siberia, which he considered as indicating a pole to the north of that country. M. Ehrman also traveled round the Earth at the same time, making magnetic observations. About the same time, another magnetical phenomenon attracted attention. Besides the general motion of the magnetic poles and the diurnal movements of the needle, it was found that small and irregular disturbances take place in its position, which M. de Humboldt termed magnetic storms. And that which excited a strong interest on this subject was the discovery that these magnetic storms, seen only by philosophers who watch the needle with microscopic exactness, rage simultaneously over large tracts of the surface of our globe. This was detected about 1825 by a comparison of the observations of M. Arago at Paris with simultaneous observations of M. Kupfer at Kazan in Russia, distant more than 47 degrees of longitude. At the instance of M. de Humboldt, the Imperial Academy of Russia adopted with zeal the prosecution of this inquiry and formed a chain of magnetic stations across the whole of the Russian Empire. Magnetic observations were established at Petersburg and at Kazan, and corresponding observations were made at Moscow, at Nikolaev in the Crimea, and Barnaul and Nerchinsk in Siberia, at Sitka in Russian America, and even at Pekin. To these magnetic stations, the Russian government afterwards added Katharinenburg in Russia proper, Helsingfors in Finland, Tiflis in Georgia. A comparison of the results obtained at 4 of these stations, made by M. de Humboldt and Dove, in the year 1830, showed that the magnetic disturbances were simultaneous and were for the most parallel in their progress. 227. Important steps in the prosecution of this subject were soon after made by M. Gauss, the great mathematician of Göttingen. He contrived instruments and modes of observation far more perfect than any before employed, and organized a system of comparative observations throughout Europe. In 1835, stations for this purpose were established at Altona, Augsburg, Berlin, Breda, Breslau, Copenhagen, Dublin, Freiburg, Göttingen, Greenwich, Hanover, Leipzig, Marburg, Milan, Munich, Petersburg, Stockholm, and Uppsala. At these places 6 times in the year, observations were taken simultaneously, at intervals of 5 minutes for 24 hours. The results of the magnetic association, Resultaten des magnetischen Verins, were published by M.M. Gauss and Weber, beginning in 1836. British physicists did not at first take any leading part in these plans. But in 1836, Baron Humboldt, who by his long labors and important discoveries in this subject might be considered as peculiarly entitled to urge its claims, addressed a letter to the Duke of Sussex, then president of the Royal Society, asking for the cooperation of this country in so large and hopeful a scheme for the promotion of science. The Royal Society willingly entertained this appeal, and the progress of the cause was still further promoted when it was zealously taken up by the British Association for the Advancement of Science, assembled at Newcastle in 1838. The association there expressed its strong interest in the German system of magnetic observations, and at the instigation of this body and of the Royal Society, 4 complete magnetical observatories were established by the British government at Toronto, St. Helena, the Cape of Good Hope, and Van Diemen's Land. The munificence of the directors of the East India Company founded and furnished an equal number at Simla, in the Himalaya, Madras, Bombay, and Singapore. Sir Thomas Brisbane added another at his own expense at Kelso, in Scotland. Besides this, the government sent out a naval expedition to make discoveries, magnetic among others, in the Antarctic regions under the command of Sir James Ross. Other states lent their assistance also, and founded or reorganized their magnetic observatories. Besides those already mentioned, one was established by the French government at Algiers, one by the Belgian at Brussels, 2 by Austria at Prague and Milan, 1 by Prussia at Breslau, 1 by Bavaria at Munich, 1 by Spain at Cadiz. There are 2 in the United States at Philadelphia and Cambridge, 1 at Cairo, founded by the Pasha of Egypt, and in India 1 at Trivandrum, established by the Raja of Travancore, and 1 by 228, the King of Oudh, at Lucknow. At all these distant stations, the same plan was followed out, by observations strictly simultaneous, made according to the same methods, with the same instrumental means. Such a scheme, combining worldwide extent with the singleness of action of an individual mind, is hitherto without parallel. At first, the British stations were established for 3 years only, but it was thought advisable to extend this period 3 years longer, to end in 1845. And when the termination of that period arrived, a discussion was held among the magneticians themselves, whether it was better to continue the observations still, or to examine and compare the vast mass of observations already collected, so as to see to what results and improvements of methods they pointed. This question was argued at the meeting of the British Association at Cambridge in that year, and the conference ended in the magneticians requesting to have the observations continued at some of the observatories for an indefinite period, at others, till the year 1848. In the meantime, the Antarctic expedition had brought back a rich store of observations, fitted to disclose the magnetic condition of those regions which it had explored. These were discussed, and their results exhibited in the Philosophical Transactions for 1843 by Carl Sabine, who had himself at various periods made magnetic observations in the Arctic regions and in several remote parts of the globe, and had always been a zealous laborer in this fruitful field. The general mass of the observations was placed under the management of Professor Lloyd, of Dublin, who has enriched the science of magnetism with several valuable instruments and methods, and who, along with Carl Sabine, made a magnetic survey of the British Isles in 1835 and 1836. I do not dwell upon magnetic surveys of various countries made by many excellent observers, as Mquetelet, Forbes, Fox, Bach, and others. The facts observed at each station were the intensity of the magnetic force, the declination of the needle from the meridian, sometimes called the variation, and its inclination to the horizon, the dip, or at least some elements equivalent to these. The values of these elements at any given time, if known, can be expressed by charts of the Earth's surface, on which are drawn the isodynamic, isogonal, and isoclinal curves. The second of these kinds of charts contain the Hallian lines spoken of in a previous page. Moreover, the magnetic elements at each place are to be observed in such a 229 manner as to determine both their periodical variations, the changes which occur in the period of a day, and of a year, the secular changes, as the gradual increase or diminution of the declination at the same place for many years, and the irregular fluctuations which, as we have said, are simultaneous over a large part, or the whole, of the Earth's surface. When these facts have been ascertained over the whole extent of the Earth's surface, we shall still have to inquire what is the cause of the changes in the forces which these phenomena disclose. But as a basis for all speculation on that subject, we must know the law of the phenomena and of the forces which immediately produce them. I have already said that Euler tried to account for the Hallian lines by means of two magnetic poles, but that M. Hansteen conceived it necessary to assume four. But an entirely new light has been thrown upon this subject by the beautiful investigations of Gauss in his theory of terrestrial magnetism, published in 1839. He remarks that the term poles, as used by his predecessors, involves an assumption arbitrary, and, as it is now found, false. Namely, that certain definite points, 2, 4, or more, acting according to the laws of ordinary magnetical poles, will explain the phenomena. He starts from a more comprehensive assumption, that magnetism is distributed throughout the mass of the Earth in an unknown manner. On this assumption, he obtains a function v, by the differentials of which the elements of the magnetic force at any point will be expressed. This function v is well known in physical astronomy, and is obtained by summing all the elements of magnetic force in each particle, each multiplied by the reciprocal of its distance, or, as we may express it, by taking the sum of each element and its proximity jointly. Hence, it has been proposed to term this function the integral proximity of the attracting mass. By using the most refined, 230 mathematical artifices for deducing the values of v and its differentials in converging series, he is able to derive the coefficients of these series from the observed magnetic elements at certain places, and hence to calculate them for all places. The comparison of the calculation with the observed results is, of course, the test of the truth of the theory. Note 26/12. The function v is of constant occurrence in investigations respecting attractions. It is introduced by Laplace in his investigations respecting the attractions of spheroids, make, sail, liver, Roman 3. Art. For Mr. Green and Professor Mac Cullog have proposed to term this function the potential of the system, but this term, though suggested, I suppose, by analogy with the substantive exponential, does not appear convenient in its form. On the other hand, the term integral proximity does not indicate that which gives the function its peculiar claim to distinction, namely, that its differentials express the power or attraction of the system. Perhaps integral potentiality or integral attractivity would be a term combining the recommendations of both the others. The degree of convergence of the series depends upon the unknown distribution of magnetism within the Earth. If we could venture to assume, says M. Gauss, that the members have a sensible influence only as far as the fourth order, complete observations from 8 points would be sufficient, theoretically considered, for the determination of the coefficients. And under certain limitations, making this assumption, as the best we can do at present, M. Gauss obtains from 8 places 24 coefficients, each supplying 3 elements, and hence calculates the magnetic elements, intensity, variation, and dip at 91 places in all parts of the Earth. He finds his calculations approach the observed values with a degree of exactness which appears to be quite convincing as to the general truth of his results, especially taking into account how entirely unlimited is his original hypothesis. It is one of the most curious results of this investigation that, according to the most simple meaning which we can give to the term pole, the Earth has only 2 magnetic poles, that is, 2 points where the direction of the magnetic force is vertical. And thus the isogonal curves may be looked upon as deformations of the curves deduced by Euler from the supposition of 2 poles, the deformation arising from this, that the Earth does not contain a single definite magnet, but irregularly diffused magnetical elements, which still have collectively a distinct resemblance to a single magnet. And instead of Hansstein's Siberian pole, we have a Siberian region in which the needles converge. But if the apparent convergence be pursued, it nowhere comes to a point. And the like is the case in the Antarctic region. When the 24 Gaussian elements at any time are known, the magnetic condition of the globe is known, just as the mechanical condition of the solar system is known, when we know the elements of the orbits of the satellites and planets and the mass of each. And the comparison of this magnetic condition of the globe at distant periods of time cannot fail to supply materials for future researches and speculations with regard to the agencies by which the condition of the Earth is determined. The condition of which we here speak must necessarily be its mechanico-chemical condition, being expressed, as it will be, in terms of the mechanico-chemical sciences. The 231 investigations I have been describing belong to the mechanical side of the subject. But when philosophers have to consider the causes of the secular changes which are found to occur in this mechanical condition, they cannot fail to be driven to electrical, that is, chemical agencies and laws. I can only allude to Gauss's investigations respecting the absolute measure of the Earth's magnetic force. To determine the ratio of the magnetic force of the Earth to that of a known magnet, Poisson proposed to observe the time of vibration of a second magnet. The method of Gauss, now universally adopted, consists in observing the position of equilibrium of the second magnet when deflected by the first. The manner in which the business of magnetic observation has been taken up by the governments of our time makes this by far the greatest scientific undertaking which the world has ever seen. The result will be that we shall obtain in a few years a knowledge of the magnetic constitution of the Earth, which otherwise it might have required centuries to accumulate. The secular magnetic changes must still require a long time to reduce to their laws of phenomena, except observation be anticipated or assisted by some happy discovery as to the cause of these changes. But besides the special gain to magnetic science by this great plan of joint action among the nations of the Earth, there is thereby a beginning made in the recognition and execution of the duty of forwarding science in general by national exertions. For at most of the magnetic observatories, meteorological observations are also carried on, and such observations, being far more extensive, systematic, and permanent than those which have usually been made, can hardly fail to produce important additions to science. But at any rate, they do for science that which nations can do and individuals cannot, and they seek for scientific truths in a manner suitable to the respect now professed for science and to the progress which its methods have made. Nor are we to overlook the effect of such observations as means of training men in the pursuit of science. There is amongst us, says one of the magnetic observers, a growing recognition of the importance, both for science and for practical life, of forming exact observers of nature. Hitherto, astronomy alone has afforded a very partial opportunity for the formation of fine observers, of which few could avail themselves. Experience has shown that magnetic observations may serve as excellent training schools in this respect. 232. The various other circumstances which terrestrial magnetism exhibits, the diurnal and annual changes of the position of the compass needle, the larger secular change which affects it in the course of years, the difference of intensity at different places, and other facts have naturally occupied philosophers with the attempt to determine both the laws of the phenomena and their causes. But these attempts necessarily depend not upon laws of statical magnetism, such as they have been explained above, but upon the laws by which the production and intensity of magnetism in different cases are regulated, laws which belong to a different province and are related to a different set of principles. Thus, for example, we have not attempted to explain the discovery of the laws by which heat influences magnetism, and therefore we cannot now give an account of those theories of the facts relating to terrestrial magnetism, which depend upon the influence of temperature. The conditions of excitation of magnetism are best studied by comparing this force with other cases where the same effects are produced by very different apparent agencies, such as galvanic and thermoelectricity. To the history of these, we shall presently proceed. Conclusion: the hypothesis of magnetic fluids as physical realities was never widely or strongly embraced, as that of electric fluids was. For though the hypothesis accounted, to a remarkable degree of exactness, for large classes of the phenomena, the presence of a material fluid was not indicated by facts of a different kind, such as the spark, the discharge from points, the shock, and its mechanical effects. Thus, the belief of a peculiar magnetic fluid or fluids was not forced upon men's minds, and the doctrine above stated was probably entertained by most of its adherents, chiefly as a means of expressing the laws of phenomena in their elementary form. One other observation occurs here. We have seen that the supposition of a fluid movable from one part of bodies to another, and capable of accumulation in different parts of the surface, appeared at first to be as distinctly authorized by magnetic as by electric phenomena, and yet that it afterwards appeared, by calculation, that this must be considered as a derivative result. No real transfer of fluid taking place, except within the limits of the insensible particles of the body. Without attempting to found a formula of philosophizing on this circumstance, we may observe that this occurrence, like the disproof of heat as a material fluid, shows the possibility of an hypothesis which shall very exactly satisfy many phenomena and yet be incomplete. It 233 shows, too, the necessity of bringing facts of all kinds to bear on the hypothesis. Thus, in this case, it was requisite to take into account the facts of junction and separation of magnetic bodies, as well as their attractions and repulsions. If we have seen reason to doubt the doctrine of electric fluids as physical realities, we cannot help pronouncing upon the magnetic fluids as having still more insecure claims to a material existence, even on the grounds just stated. But we may add considerations still more decisive, for at a further stage of discovery, as we shall see, magnetic and electric action were found to be connected in the closest manner, so as to lead to the persuasion of there being different effects of one common cause. After those discoveries, no philosopher would dream of assuming electric fluids and magnetic fluids as two distinct material agents. Yet even now the nature of the dependence of magnetism upon any other cause is extremely difficult to conceive. But till we have noticed some of the discoveries to which we have alluded, we cannot even speculate about that dependence. We now, therefore, proceed to sketch the history of these discoveries. 235, Book 13. Mechanico-Chemical Sciences. Continued. History of Galvanism, or Voltaic Electricity. Percussi gelido trepidant sub pector fibri, et nova disudis subrepens vita metallis misseter morti, tunc omnes palpitat artis tendunter nervi, nexi teller cadaver palladum per membra levat, terrac repulsum est erectumc simul, Lucan, Roman 6. 752. The form which lay before inert and dead, sudden a piercing thrill of change o'erspread, returning life gleams in the stony face. The fibers quiver and the sinews brace move the stiff limbs, nor did the body rise with tempered strength which genial life supplies. But upright starting, its full stature held, as though the earth the supine course repelled. 237, Chapter 1. Discovery of voltaic electricity. We have given the name of mechanico-chemical to the class of sciences now under our consideration. For these sciences are concerned with cases in which mechanical effects, that is, attractions and repulsions, are produced, while the conditions under which these effects occur depend, as we shall hereafter see, on chemical relations. In that branch of these sciences which we have just treated of, magnetism, the mechanical phenomena were obvious, but their connection with chemical causes was by no means apparent, and indeed has not yet come under our notice. The subject to which we now proceed, galvanism, belongs to the same group, but at first sight exhibits only the other, the chemical portion of the features of the class. For the connection of galvanic phenomena with chemical action was soon made out, but the mechanical effects which accompany them were not examined till the examination was required by a new train of discovery. It is to be observed that I do not include in the class of mechanical effects the convulsive motions in the limbs of animals which are occasioned by galvanic action. For these movements are produced, not by attraction and repulsion, but by muscular irritability, and though they indicate the existence of a peculiar agency, cannot be used to measure its intensity and law. The various examples of the class of agents which we here consider, magnetism, electricity, galvanism, electromagnetism, thermoelectricity, differ from each other principally in the circumstances by which they are called into action. And these differences are in reality of a chemical nature, and will have to be considered when we come to treat of the inductive steps by which the general principles of chemical theory are established. In the present part of our task, therefore, we must take for granted the chemical conditions on which the excitation of these various kinds of action depends, and trace the history of the discovery of their mechanical laws only. This rule will much abridge the account we have here to give of the progress of discovery in the provinces to which I have just referred. 238. The first step in this career of discovery was that made by Galvani, professor of anatomy at Bologna. In 1790, electricity, as an experimental science, was nearly stationary. The impulse given to its progress by the splendid phenomena of the Leyden file had almost died away. Coulomb was employed in systematizing the theory of the electric fluid, as shown by its statical effects. But in all the other parts of the subject, no great principle or new result had for some time been detected. The first announcement of Galvani's discovery in 1791 excited great notice, for it was given forth as a manifestation of electricity under a new and remarkable character, namely, as residing in the muscles of animals. The limbs of a dissected frog were observed to move, when touched with pieces of two different metals. The agent which produced these motions was conceived to be identified with electricity, and was termed animal electricity. And Galvani's experiments were repeated, with various modifications, in all parts of Europe, exciting much curiosity and giving rise to many speculations. Note 1/13, De viribus electricis in modo musculari, com, Bonan T, Roman 7, 1792. It is our business to determine the character of each great discovery which appears in the progress of science. Men are fond of repeating that such discoveries are most commonly the result of accident, and we have seen reason to reject this opinion, since that preparation of thought by which the accident produces discovery is the most important of the conditions on which the successful event depends. Such accidents are like a spark, which discharges a gun already loaded and pointed. In the case of Galvani, indeed, the discovery may, with more propriety than usual, be said to have been casual. But in the form in which it was first noted, it exhibited no important novelty. His frog was lying on a table near the conductor of an electrical machine, and the convulsions appeared only when a spark was taken from the machine. If Galvani had been as good a physicist as he was an anatomist, he would probably have seen that the movement so occasioned proved only that the muscles or nerves, or the two together, formed a very sensitive indicator of electrical action. It was when he produced such motions by contact of metals alone that he obtained an important and fundamental fact in science. The analysis of this fact into its real and essential conditions was the work of Alexander Volta, another Italian professor. Volta, indeed, possessed that knowledge of the subject of electricity which made a hint like that of Galvani the basis of a new science. Galvani appears, 239, never to have acquired much general knowledge of electricity. Volta, on the other hand, had labored at this branch of knowledge from the age of 18 through a period of nearly 30 years, and had invented an electrophorus and an electrical condenser, which showed great experimental skill. When he turned his attention to the experiments made by Galvani, he observed that the author of them had been far more surprised than he needed to be at those results in which an electrical spark was produced, and that it was only in the cases in which no such apparatus was employed that the observations could justly be considered as indicating a new law or a new kind of electricity. He soon satisfied himself, about 1794, that the essential conditions of this kind of action depended on the metals, that it is brought into play most decidedly when two different metals touch each other and are connected by any moist body, and that the parts of animals which had been used discharged the office both of such moist bodies and of very sensitive electrometers. The animal electricity of Galvani might, he observed, be with more propriety called metallic electricity. The recognition of this agency as a peculiar kind of electricity arose in part perhaps, at first, from the confusion made by Galvani between the cases in which his electrical machine was and those in which it was not employed. But the identity was confirmed by its being found that the known difference of electrical conductors and non-conductors regulated the conduction of the new influence. The more exact determination of the new facts to those of electricity was a succeeding step of the progress of the subject. The term animal electricity has been superseded by others, of which galvanism is perhaps the most familiar. I think it will appear from what has been said that Volta's office in this discovery is of a much higher and more philosophical kind than that of Galvani, and it would, on this account, be more fitting to employ the term voltaic electricity, which indeed is very commonly used, especially by our most recent and comprehensive writers. Volta more fully still established his claim as the main originator of this science by his next step. When some of those who repeated the experiments of Galvani had expressed a wish that there was some method of multiplying the effect of this electricity, such as the Leyden file supplies for common electricity, they probably thought their wishes far from a realization. But the voltaic pile, which Volta 240 described in the Philosophical Transactions for 1800, completely satisfies this aspiration, and was, in fact, a more important step in the history of electricity than the Leyden jar had been. It has since undergone various modifications, of which the most important was that introduced by Cruikshanks, who substituted a trough for a pile. But in all cases, the principle of the instrument was the same: a continued repetition of the triple combination of two metals and a fluid in contact, so as to form a circuit which returns into itself. Such an instrument is capable of causing effects of great intensity, as seen both in the production of light and heat and in chemical changes. But the discovery with which we are here concerned is not the details and consequences of the effects, which belong to chemistry, but the analysis of the conditions under which such effects take place. And this we may consider as completed by Volta at the epoch of which we speak. Chapter 2. Reception and confirmation of the discovery of voltaic electricity. Galvani's experiments excited a great interest all over Europe, in consequence partly of a circumstance which, as we have seen, was unessential: the muscular contractions and various sensations which they occasioned. Galvani himself had not only considered the animal element of the circuit as the origin of the electricity, but had framed a theory in which he compared the muscles to charged jars and the nerves to the discharging wires. And a controversy was, for some time, carried on in Italy between the adherents of Galvani and those of Volta. The galvanic experiments, and especially those which appeared to have a physiological bearing, were verified and extended by a number of the most active philosophers of Europe, and especially William von Humboldt. A commission of the Institute of France, appointed in 1797, repeated many of the known experiments, but does not seem to have decided any disputed points. The researches of this 241 commission referred rather to the discoveries of Galvani than to those of Volta. The latter were, indeed, hardly known in France till the conquest of Italy by Bonaparte in 1801. France was, at the period of these discoveries, separated from all other countries by war, and especially from England, where Volta's memoirs were published. The political revolutions of Italy affected, in very different manners, the two discoverers of whom we speak. Galvani refused to take an oath of allegiance to the Cisalpine Republic, which the French conqueror established. He was consequently stripped of all his offices, and deprived, by the calamities of the times, of most of his relations. He sank into poverty, melancholy, and debility. At last, his scientific reputation induced the Republican rulers to decree his restoration to his professorial chair. But his claims were recognized too late, and he died without profiting by this intended favor in 1798. Volta, on the other hand, was called to Paris by Bonaparte as a man of science and invested with honors, emoluments, and titles. The conqueror himself, indeed, was strongly interested by this train of research. He himself founded valuable prizes, expressly with a view to promote its prosecution. At this period, there was something in this subject peculiarly attractive to his Italian mind. For the first glimpses of discoveries of great promise have always excited an enthusiastic activity of speculation in the philosophers of Italy, though generally accompanied with a want of precise thought. It is narrated of Bonaparte that after seeing the decomposition of the salts by means of the voltaic pile, he turned to Corvisart, his physician, and said, "Here, doctor, is the image of life. The vertebral column is the pile, the liver is the negative, the bladder the positive pole." The importance of voltaic researches is not less than it was estimated by Bonaparte, but the results to which it was to lead were of a kind altogether different from those which thus suggested themselves to his mind. The connection of mechanical and chemical action was the first great point to be dealt with, and for this purpose the laws of the mechanical action of voltaic electricity were to be studied. It will readily be supposed that the voltaic researches, thus begun, opened a number of interesting topics of examination and discussion. These, however, it does not belong to our place to dwell upon at present, since they formed parts of the theory of the subject, which, 242, was not completed till light had been thrown upon it from other quarters. The identity of galvanism with electricity, for instance, was at first, as we have intimated, rather conjectured than proved. It was denied by Dr. Fowler in 1793, was supposed to be confirmed by Dr. Wells 2 years later, but was, still later, questioned by Davy. The nature of the operation of the pile was variously conceived. Volta himself had obtained a view of it which succeeding researches confirmed when he asserted in 1800 that it resembled an electric battery feebly charged and constantly renewing its charge. In pursuance of this view, the common electrical action was, at a later period, for instance by Ampere in 1820, called electrical tension, while the voltaic action was called the electrical current or electromotive action. The different effects produced by increasing the size and the number of the plates in the voltaic trough were also very remarkable. The power of producing heat was found to depend on the size of the plates. The power of producing chemical changes, on the other hand, was augmented by the number of plates of which the battery consisted. The former effect was referred to the increased quantity, the latter to the intensity, of the electric fluid. We mention these distinctions at present, rather for the purpose of explaining the language in which the results of the succeeding investigations are narrated, than with the intention of representing the hypotheses and measures which they imply as clearly established at the period of which we speak. For that purpose, new discoveries were requisite, which we have soon to relate. Chapter 3. Discovery of the laws of the mutual attraction and repulsion of voltaic currents, Ampere. In order to show the place of voltaic electricity among the mechanico-chemical sciences, we must speak of its mechanical laws as separate from the laws of electromagnetic action. Although, in fact, it was only in consequence of the forces which conducting voltaic wires exert upon magnets that those forces were detected which they exert upon each 243 other. This latter discovery was made by M. Ampere, and the extraordinary rapidity and sagacity with which he caught the suggestion of such forces from the electromagnetic experiments of M. Ørsted, of which we shall speak in the next chapter, well entitle him to be considered as a great and independent discoverer. As he truly says, it by no means followed that because a conducting wire exerted a force on a magnet, two conducting wires must exert a force on each other. For two pieces of soft iron, both of which affect a magnet, do not affect each other. But immediately on the promulgation of Oersted's experiments, in 1820, Ampere leapt forwards to a general theory of the facts, of which theory the mutual attraction and repulsion of conducting voltaic wires was a fundamental supposition. The supposition was immediately verified by direct trial, and the laws of this attraction and repulsion were soon determined, with great experimental ingenuity and a very remarkable command of the resources of analysis. But the experimental and analytical investigation of the mutual action of voltaic or electrical currents was so mixed up with the examination of the laws of electromagnetism, which had given occasion to the investigation, that we must not treat the two provinces of research as separate. The mention in this place, premature as it might appear, of the labors of Ampere, arises inevitably from his being the author of a beautiful and comprehensive generalization, which not only included the phenomena exhibited by the new combinations of Oersted, but also disclosed forces which existed in arrangements already familiar, although they had never been detected till the theory pointed out how they were to be looked for. Chapter 4. Discovery of electromagnetic action Oersted. The impulse which the discovery of galvanism in 1791 and that of the voltaic pile in 1800 had given to the study of electricity as a mechanical science, had nearly died away in 1820. It was in that year that M. Oersted of Copenhagen announced that the conducting 244 wire of a voltaic circuit acts upon a magnetic needle, and thus recalled into activity that endeavor to connect magnetism with electricity, which, though apparently on many accounts so hopeful, had hitherto been attended with no success. Oersted found that the needle has a tendency to place itself at right angles to the wire, a kind of action altogether different from any which had been suspected. This observation was of vast importance, and the analysis of its conditions and consequences employed the best philosophers in Europe immediately on its promulgation. It is impossible, without great injustice, to refuse great merit to Oersted as the author of the discovery. We have already said that men appear generally inclined to believe remarkable discoveries to be accidental, and the discovery of Oersted has been spoken of as a casual insulated experiment. Yet Oersted had been looking for such an accident probably more carefully and perseveringly than any other person in Europe. In 1807, he had published a work, in which he professed that his purpose was to ascertain whether electricity, in its most latent state, had any effect on the magnet. And he, as I know from his own declaration, considered his discovery as the natural sequel and confirmation of his early researches, as, indeed, it fell in readily and immediately with speculations on these subjects, then very prevalent in Germany. It was an accident like that by which a man guesses a riddle on which his mind has long been employed. Besides the confirmation of Oersted's observations by many experimenters, great additions were made to his facts. Of these, one of the most important was due to Ampere. Since the Earth is in fact magnetic, the voltaic wire ought to be affected by terrestrial magnetism alone, and ought to tend to assume a position depending on the position of the compass needle. At first, the attempts to produce this effect failed, but soon, with a more delicate apparatus, the result was found to agree with the anticipation. It is impossible here to dwell on any of the subsequent researches, except so far as they are essential to our great object, the progress towards a general theory of the subject. I proceed, therefore, immediately to the attempts made towards this object. 245. Chapter 5. Discovery of the laws of electromagnetic action. On attempting to analyze the electromagnetic phenomena observed by Oersted and others into their simplest forms, they appeared, at least at first sight, to be different from any mechanical actions which had yet been observed. It seemed as if the conducting wire exerted on the pole of the magnet a force which was not attractive or repulsive, but transverse, not tending to draw the point acted on nearer, or to push it further off, in the line which reached from the acting point, but urging it to move at right angles to this line. The forces appeared to be such as Kepler had dreamt of in the infancy of mechanical conceptions, rather than such as those of which Newton had established the existence in the solar system, and such as he and all his successors had supposed to be the only kinds of force which exist in nature. The north pole of the needle moved as if it were impelled by a vortex revolving round the wire in one direction, while the south pole seemed to be driven by an opposite vortex. The case seemed novel and almost paradoxical. It was soon established by experiments, made in a great variety of forms, that the mechanical action was really of this transverse kind. And a curious result was obtained, which a little while before would have been considered as altogether incredible, that this force would cause a constant and rapid revolution of either of the bodies about the other, of the conducting wire about the magnet, or of the magnet about the conducting wire. This was effected by Mr. Faraday in 1821. The laws which regulated the intensity of this force, with reference to the distance and position of the bodies, now naturally came to be examined. Biot and Savart in France, and Mr. Barlow in England, instituted such measures, and satisfied themselves that the elementary force followed the law of magnitude of all known elementary forces, in being inversely as the square of the distance, although, in its direction, it was so entirely different from other forces. But the investigation of the laws of phenomena of the subject was too closely connected with the choice of a mechanical theory to be established 246, previously and independently, as had been done in astronomy. The experiments gave complex results, and the analysis of these into their elementary actions was almost an indispensable step in order to disentangle their laws. We must, therefore, state the progress of this analysis. Chapter 6. Theory of electrodynamical action. Ampere's theory nothing can show in a more striking manner the advanced condition of physical speculation in 1820 than the reduction of the strange and complex phenomena of electromagnetism to a simple and general theory as soon as they were published. Instead of a gradual establishment of laws of phenomena, and of theories more and more perfect, occupying ages, as in the case of astronomy, or generations, as in the instances of magnetism and electricity, a few months sufficed for the whole process of generalization, and the experiments made at Copenhagen were announced at Paris and London, almost at the same time with the skillful analysis and comprehensive inductions of Ampere. Yet we should err if we should suppose, from the celerity with which the task was executed, that it was an easy one. There were required in the author of such a theory not only those clear conceptions of the relations of space and force, which are the first conditions of all sound theory, and a full possession of the experiments, but also a masterly command of the mathematical arms by which alone the victory could be gained, and a sagacious selection of proper experiments which might decide the fate of the proposed hypothesis. It is true that the nature of the requisite hypothesis was not difficult to see in a certain vague and limited way. The conducting wire and the magnetic needle had a tendency to arrange themselves at right angles to one another. This might be represented by supposing the wire to be made up of transverse magnetic needles, or by supposing the needle to be made up of transverse conducting wires, for it was easy to conceive forces which should bring corresponding elements, either magnetic or voltaic, into parallel positions. And then the 247 general phenomena above stated would be accounted for. And the choice between the two modes of conception appeared at first sight a matter of indifference. The majority of philosophers at first adopted, or at least employed, the former method, as Ørsted in Germany, Berzelius in Sweden, Wollaston in England. Ampere adopted the other view, according to which the magnet is made up of conducting wires in a transverse position. But he did for his hypothesis what no one did or could do for the other. He showed that it was the only one which would account, without additional and arbitrary suppositions, for the facts of continued motion in electromagnetic cases. And he further elevated his theory to a higher rank of generality, by showing that it explained not only the action of a conducting wire upon a magnet, but also two other classes of facts, already spoken of in this history: the action of magnets upon each other and the action of conducting wires upon each other. The deduction of such particular cases from the theory required, as may easily be imagined, some complex calculations. But the deduction being satisfactory, it will be seen that Ampere's theory conformed to that description, which we have repeatedly had to point out as the usual character of a true and stable theory. Namely, that besides accounting for the class of phenomena which suggested it, it supplies an unforeseen explanation of other known facts. For the mutual action of magnets, which was supposed to be already reduced to a satisfactory theoretical form by Coulomb, was not contemplated by Ampere in the formation of his hypothesis, and the mutual action of voltaic currents, though tried only in consequence of the suggestion of the theory, was clearly a fact distinct from electromagnetic action. Yet all these facts flowed alike from the theory. And thus Ampere brought into view a class of forces for which the term electromagnetic was too limited, and which he designated by the appropriate term electrodynamic, distinguishing them by this expression as the forces of an electric current from the statical effects of electricity which we had formerly to treat of. This term has passed into common use among scientific writers and remains the record and stamp of the success of the Amperian induction. The first promulgation of Ampere's views was by a communication to the French Academy of Sciences, September 18, 1820, Oersted's discoveries having reached Paris only in the preceding July. 248. At almost every meeting of the Academy during the remainder of that year and the beginning of the following one, he had new developments or new confirmations of his theory to announce. The most hypothetical part of his theory, the proposition that magnets might be considered in their effects as identical with spiral voltaic wires, he asserted from the very first. The mutual attraction and repulsion of voltaic wires, the laws of this action, the deduction of the observed facts from it by calculation, the determination, by new experiments, of the constant quantities which entered into his formulae, followed in rapid succession. The theory must be briefly stated. It had already been seen that parallel voltaic currents attracted each other. When, instead of being parallel, they were situate in any directions, they still exerted attractive and repulsive forces depending on the distance, and on the directions of each element of both currents. Add to this doctrine the hypothetical constitution of magnets, namely, that a voltaic current runs round the axis of each particle, and we have the means of calculating a vast variety of results which may be compared with experiment. But the laws of the elementary forces required further fixation. What functions are the forces of the distance and the directions of the elements? To extract from experiment an answer to this inquiry was far from easy, for the elementary forces were mathematically connected with the observed facts by a double mathematical integration, A long, and, while the constant coefficients remained undefined, hardly a possible operation. Ampere made some trials in this way, but his happier genius suggested to him a better path. It occurred to him that if his integrals, without being specially found, could be shown to vanish upon the whole, under certain conditions of the problem, this circumstance would correspond to arrangements of his apparatus in which a state of equilibrium was preserved, however the form of some of the parts might be changed. He found two such cases, which were of great importance to the theory. The first of these cases proved that the force exerted by any element of the voltaic wire might be resolved into other forces by a theorem resembling the well-known proposition of the parallelogram of forces. This was proved by showing that the action of a straight wire is the same with that of another wire which joins the same extremities, but is bent and contorted in any way whatever. But it still remained necessary to determine two fundamental quantities, one which expressed the power of the distance according to which the force varied, the other, the 249 degree in which the force is affected by the obliquity of the elements. One of the general causes of equilibrium, of which we have spoken, gave a relation between these two quantities, and as the power was naturally, and, as it afterwards appeared, rightly conjectured to be the inverse square, the other quantity also was determined, and the general problem of electrodynamical action was fully solved. Note 15/13, Communication to the Acad. SC, June 10, 1822. See Ampere, Recueil, p. 292. If Ampere had not been an accomplished analyst, he would not have been able to discover the condition on which the nullity of the integral in this case depended. And throughout his labors, we find reason to admire, both his mathematical skill and his steadiness of thought, although these excellences are by no means accompanied throughout with corresponding clearness and elegance of exposition in his writings. Reception of Ampere's theory-clear mathematical conceptions and some familiarity with mathematical operations were needed by readers also, in order to appreciate the evidence of the theory. And therefore, we need not feel any surprise if it was, on its publication and establishment, hailed with far less enthusiasm than so remarkable a triumph of generalizing power might appear to deserve. For some time, indeed, the greater portion of the public were naturally held in suspense by the opposing weight of rival names. The Amperian theory did not make its way without contention and competition. The electromagnetic experiments, from their first appearance, gave a clear promise of some new and wide generalization, and held out a prize of honor and fame to him who should be first in giving the right interpretation of the riddle. In France, the emulation for such reputation is perhaps more vigilant and anxious than it is elsewhere, and we see, on this as on other occasions, the scientific host of Paris springing upon a new subject with an impetuosity which, in a short time, runs into controversies for priority or for victory. In this case, M. Biot, as well as Ampere, endeavored to reduce the electromagnetic phenomena to general laws. The discussion between him and Ampere turned on some points which are curious. M. Biot was disposed to consider as an elementary action the force which an element of a voltaic wire exerts upon a magnetic particle, and which is, as we have seen, at right angles to their mutual distance. And he conceived that 250, the equal reaction which necessarily accompanies this action, acts oppositely to the action, not in the same line, but in a parallel line at the other extremity of the distance, thus forming a primitive couple, to use a technical expression borrowed from mechanics. To this Ampere objected that the direct opposition of all elementary action and reaction was a universal and necessary mechanical law. He showed too that such a couple as had been assumed would follow as a derivative result from his theory. And in comparing his own theory with that in which the voltaic wire is assimilated to a collection of transverse magnets, he was also able to prove that no such assemblage of forces acting to and from fixed points, as the forces of magnets do act, could produce a continued motion like that discovered by Faraday. This, indeed, was only the well-known demonstration of the impossibility of a perpetual motion. If, instead of a collection of magnets, the adverse theorists had spoken of a magnetic current, they might probably interpret their expressions so as to explain the facts. That is, if they considered every element of such a current as a magnet, and consequently, every point of it as being a north and a south point at the same instant. But to introduce such a conception of a magnetic current was to abandon all the laws of magnetic action hitherto established, and consequently to lose all that gave the hypothesis its value. The idea of an electric current, on the other hand, was so far from being a new and hazardous assumption that it had already been forced upon philosophers from the time of Volta. And in this current, the relation of preceding and succeeding, which necessarily existed between the extremities of any element, introduced that relative polarity on which the success of the explanations of the facts depended. And thus, in this controversy, the theory of Ampere has a great and undeniable superiority over the rival hypotheses. Chapter 7. Consequences of the electrodynamic theory. It is not necessary to state the various applications which were soon made of the electromagnetic discoveries, but we may notice 251 of the most important, the galvanometer, an instrument which, by enabling the philosopher to detect and to measure extremely minute electrodynamic actions, gave an impulse to the subject similar to that which it received from the invention of the Leyden file or the voltaic pile. The strength of the voltaic current was measured, in this instrument, by the deflection produced in a compass needle, and its sensibility was multiplied by making the wire pass repeatedly above and below the needle. Schweger, of Halle, was one of the first devisers of this apparatus. The substitution of electromagnets, that is, of spiral tubes composed of voltaic wires, for common magnets, gave rise to a variety of curious apparatus and speculations, some of which I shall hereafter mention. When a voltaic apparatus is in action, there may be conceived to be a current of electricity running through its various elements, as stated in the text. The force of this current in various parts of the circuit has been made the subject of mathematical investigation by M. Ohm. The problem is in every respect similar to that of the flow of heat through a body, and taken generally, leads to complex calculations of the same kind. But Dr. Ohm, by limiting the problem in the first place by conditions which the usual nature and form of voltaic apparatus suggest, has been able to give great simplicity to his reasonings. These conditions are the linear form of the conductors, wires, and the steadiness of the electric state. For this part of the problem, Dr. Ohm's reasonings are as simple and as demonstrative as the elementary propositions of mechanics. The formulae for the electric force of a voltaic current to which he is led have been experimentally verified by others, especially Fechner, Gauss, Lenz, Jacobi, Poggendorff, and Pouillet. Note 18-13. Die galvanische mathematische Bearbeitet von Dr. G. S. Ohm, Berlin, 1827. Note 19-13. Maßbestimmungen über die galvanische Leipzig, 1831. Among ourselves, Mr. Wheatstone has confirmed and applied the views of M. Ohm in a memoir on new instruments and processes for determining the constants of a voltaic circuit. He there remarks that the clear ideas of electromotive forces and resistances, substituted by Ohm for the vague notions of quantity and intensity which have long been prevalent, give satisfactory explanations of the most important difficulties and express the laws of a vast number of phenomena. 252. In formulae of remarkable simplicity and generality. In this memoir, Professor Wheatstone describes an instrument which he terms rheostat, because it brings to a common standard the voltaic currents which are compared by it. He generalizes the language of the subject by employing the term rheometer for any apparatus which originates an electric current, whether voltaic or thermoelectric, and rheometa for any instrument to measure the force of such a current. It appears that the idea of constructing an instrument of the nature of the rheostat had occurred also to Prof. Jacobi of St. Petersburg. The galvanometer led to the discovery of another class of cases in which the electrodynamical action was called into play, namely, those in which a circuit, composed of two metals only, became electromagnetic by heating one part of it. This discovery of thermoelectricity was made by Professor Seebeck of Berlin in 1822 and prosecuted by various persons, especially by Prof. Cumming of Cambridge, who, early in 1823, extended the examination of this property to most of the metals and determined their thermoelectric order. But as these investigations exhibited no new mechanical effects of electromotive forces, they do not now further concern us, and we pass on, at present, to a case in which such forces act in a manner different from any of those already described. Note 22-13, Cam, Trans Volume Roman II, p. 62, on the development of electromagnetism by heat. Discovery of diamagnetism. By the discoveries just related, a cylindrical spiral of wire through which an electric current is passing is identified with a magnet, and the effect of such a spiral is increased by placing in it a core of soft iron. By the use of such a combination, under the influence of a voltaic battery, magnets are constructed far more powerful than those which depend upon the permanent magnetism of iron. The electromagnet employed by Dr. Faraday in some of his experiments would sustain a hundredweight at either end. By the use of such magnets, Dr. Faraday discovered that, besides iron, nickel, and cobalt, which possess magnetism in a high degree, many bodies are magnetic in a slight degree. And he made the further very important discovery, that of those substances which are not magnetic, many, perhaps all, possess an opposite property, in virtue of which he terms them diamagnetic. The opposition is of this, 253 kind, that magnetic bodies in the form of bars or needles, if free to move, arrange themselves in the axial line joining the poles. Diamagnetic bodies under the same circumstances arrange themselves in an equatorial position, perpendicular to the axial line. And this tendency he conceives to be the result of one more general, that whereas magnetic bodies are attracted to the poles of a magnet, diamagnetic bodies are repelled from the poles. The list of diamagnetic bodies includes all kinds of substances, not only metals, as antimony, bismuth, gold, silver, lead, tin, zinc, but many crystals, glass, phosphorus, sulfur, sugar, gum, wood, ivory, and even flesh and fruit. It appears that M. Le Bailly had shown, in 1829, that both bismuth and antimony and bismuth repelled the magnetic needle. And as Dr. Faraday remarks, it is astonishing that such an experiment should have remained so long without further results. M. Becquerel in 1827 observed, and quoted Coulomb as having also observed, that a needle of wood under certain conditions pointed across the magnetic curves, and also stated that he had found a needle of wood place itself parallel to the wires of a galvanometer. This he referred to a magnetism transverse to the length. But he does not refer the phenomena to elementary repulsive action, nor show that they are common to an immense class of bodies, nor distinguish this diamagnetic from the magnetic class, as Faraday has taught us to do. I do not dwell upon the peculiar phenomena of copper, which, in the same series of researches, are traced by Dr. Faraday to the combined effect of its diamagnetic character, and the electric currents excited in it by the electromagnet, nor to the optical phenomena manifested by certain transparent diamagnetic substances under electric action, as already stated in Book 9. Note 23/13. See the 20th series of experimental researches in electricity read to the Royal Society, Dec. 18, 1845. Chapter 8. Discovery of the laws of magnetoelectric induction Faraday. It was clearly established by Ampere, as we have seen, that magnetic action is a peculiar form of electromotive actions, and that, in 254, this kind of agency, action and reaction, are equal and opposite. It appeared to follow almost irresistibly from these considerations that magnetism might be made to produce electricity, as electricity could be made to imitate all the effects of magnetism. Yet for a long time the attempts to obtain such a result were fruitless. Faraday, in 1825, endeavored to make the conducting wire of the voltaic circuit excite electricity in a neighboring wire by induction, as the conductor charged with common electricity would have done, but he obtained no such effect. If this attempt had succeeded, the magnet, which, for all such purposes, is an assemblage of voltaic circuits, might also have been made to excite electricity. About the same time, an experiment was made in France by M. Arago, which really involved the effect thus sought, though this effect was not extricated from the complex phenomenon till Faraday began his splendid career of discovery on this subject in 1832. Arago's observation was that the rapid revolution of a conducting plate in the neighborhood of a magnet gave rise to a force acting on the magnet. In England, Messrs. Barlow and Christie, Herschel and Babbage repeated and tried to analyze this experiment, but referring the forces only to conditions of space and time, and overlooking the real cause, the electrical currents produced by the motion, these philosophers were altogether unsuccessful in their labors. In 1831, Faraday again sought for electrodynamical induction, and after some futile trials, at last found it in a form different from that in which he had looked for it. It was then seen that at the precise time of making or breaking the contact which closed the galvanic circuit, a momentary effect was induced in a neighboring wire, but disappeared instantly. Once in possession of this fact, Mr. Faraday ran rapidly up the ladder of discovery, to the general point of view instead of suddenly making or breaking the contact of the inducing circuit. A similar effect was produced by removing the inducible wire nearer to or further from the circuit. The effects were increased by the proximity of soft iron when the soft iron was affected by an ordinary magnet instead of the voltaic wire. The same effect still recurred, and thus it appeared that by making and breaking magnetic contact, a momentary electric current was produced. It was produced also by moving the magnet or by moving the wire with reference to the magnet. Finally, it was found that the Earth might supply the place of a magnet, 255 in this as in other experiments, and the mere motion of a wire, under proper circumstances, produced in it, it appeared, a momentary electric current. These facts were curiously confirmed by the results in special cases. They explained Arago's experiments, for the momentary effect became permanent by the revolution of the plate. And without using the magnet, a revolving plate became an electrical machine. A revolving globe exhibited electromagnetic action, the circuit being complete in the globe itself without the addition of any wire, and a mere motion of the wire of a galvanometer produced an electrodynamic effect upon its needle. But the question occurs, what is the general law which determines the direction of electric currents thus produced by the joint effects of motion and magnetism? Nothing but a peculiar steadiness and clearness in his conceptions of space could have enabled Mr. Faraday to detect the law of this phenomenon. For the question required that he should determine the mutual relations in space which connect the magnetic poles, the position of the wire, the direction of the wire's motion, and the electrical current produced in it. This was no easy problem. Indeed, the mere relation of the magnetic to the electric forces, the one set being perpendicular to the other, is of itself sufficient to perplex the mind, as we have seen in the history of the electrodynamical discoveries. But Mr. Faraday appears to have seized at once the law of the phenomena. The relation, he says, which holds between the magnetic pole, the moving wire or metal, and the direction of the current evolved, is very simple, so it seemed to him, although rather difficult to express. He represents it by referring position and motion to the magnetic curves, which go from a magnetic pole to the opposite pole. The current in the wire sets one way or the other, according to the direction in which the motion of the wire cuts these curves. And thus he was enabled, at the end of his second series of researches, December 1831, to give, in general terms, the law of nature to which may be referred the extraordinary number of new and curious experiments which he has stated, namely, that if a wire moves so as to cut a magnetic curve, a power is called into action which tends to urge a magnetic current through the wire, and that if a mass moves so that its parts do not move in the same direction across the magnetic curves, 256, and with the same angular velocity, electrical currents are called into play in the mass. This rule, thus simple from its generality, though inevitably complex in every special case, may be looked upon as supplying the first demand of philosophy, the law of the phenomena. And accordingly Dr. Faraday has, in all his subsequent researches on magnetoelectric induction, applied this law to his experiments, and has thereby unraveled an immense amount of apparent inconsistency and confusion for those who have followed him in his mode of conceiving the subject. But yet other philosophers have regarded these phenomena in other points of view, and have stated the laws of the phenomena in a manner different from Faraday's, although for the most part equivalent to his. And these attempts to express, in the most simple and general form, the law of the phenomena of magnetoelectrical induction, have naturally been combined with the expression of other laws of electrical and magnetical phenomena. Further, these endeavors to connect and generalize the facts have naturally been clothed in the garb of various theories. The laws of phenomena have been expressed in terms of the supposed causes of the phenomena, as fluids, attractions and repulsions, particles with currents running through them or round them, physical lines of force, and the like. Such views, and the conflict of them, are the natural and hopeful prognostics of a theory which shall harmonize their discords and include all that each contains of truth. The fermentation at present is perhaps too great to allow us to see clearly the truth which lies at the bottom. But a few of the leading points of recent discussions on these subjects will be noticed in the additions to this volume. Chapter 9. Transition to Chemical Science. The preceding train of generalization may justly appear extensive, and of itself well worthy of admiration. Yet we are to consider all that has there been established as only one half of the science to which it belongs one limb of the colossal form of chemistry. We 257 have ascertained, we will suppose, the laws of electric polarity, but we have then to ask, what is the relation of this polarity to chemical composition? This was the great problem which, constantly present to the minds of electrochemical inquirers, drew them on, with the promise of some deep and comprehensive insight into the mechanism of nature. Long tasks of research, though only subsidiary to this, were cheerfully undertaken. Thus Faraday describes himself as compelled to set about satisfying himself of the identity of common, animal, and voltaic electricity, as the decision of a doubtful point which interfered with the extension of his views and destroyed the strictness of reasoning. Having established this identity, he proceeded with his grand undertaking of electrochemical research. The connection of electrical currents with chemical action, though kept out of sight in the account we have hitherto given, was never forgotten by the experimenters. For, in fact, the modes in which electrical currents were excited were chemical actions, the action of acids and metals on each other in the voltaic trough or in some other form. The dependence of the electrical effect on these chemical actions, and still more, the chemical actions produced by the agency of the poles of the circuit, had been carefully studied, and we must now relate with what success. But in what terms shall we present this narration? We have spoken of chemical actions, but what kind of actions are these? Decomposition, the resolution of compounds into their ingredients, the separation of acids from bases, the reduction of bodies to simple elements. These names open to us a new drama. They are words which belong to a different set of relations of things, a different train of scientific inductions, a different system of generalizations from any with which we have hitherto been concerned. We must learn to understand these phrases before we can advance in our history of human knowledge. And how are we to learn the meaning of this collection of words? In what other language shall it be explained? In what terms shall we define these new expressions? To this, we are compelled to reply that we cannot translate these terms into any ordinary language, that we cannot define them in any terms already familiar to us. Here, as in all other branches of knowledge, the meaning of words is to be sought in the progress of thought. The history of science is our 258 dictionary. The steps of scientific induction are our definitions. It is only by going back through the successful researches of men respecting the composition and elements of bodies that we can learn in what sense such terms must be understood, so as to convey real knowledge. In order that they may have a meaning for us, we must inquire what meaning they had in the minds of the authors of our discoveries. And thus we cannot advance a step till we have brought up our history of chemistry to the level of our history of electricity, till we have studied the progress of the analytical as well as the mechanical sciences. We are compelled to pause and look backwards here, just as happened in the history of astronomy, when we arrived at the brink of the great mechanical inductions of Newton and found that we must trace the history of mechanics before we could proceed to mechanical astronomy. The terms force, attraction, inertia, momentum sent us back into preceding centuries then, just as the terms composition and element send us back now. Nor is it to a small extent that we have thus to double back upon our past advance. Next to astronomy, chemistry is one of the most ancient of sciences, the field of the earliest attempts of man to command and understand nature. It has held men for centuries by a kind of fascination, and innumerable and endless are the various labors, the failures and successes, the speculations and conclusions, the strange pretenses and fantastical dreams of those who have pursued it. To exhibit all these, or give any account of them, would be impossible, and for our design, it would not be pertinent. To extract from the mass that which is to our purpose is difficult, but the attempt must be made. We must endeavor to analyze the history of chemistry so far as it has tended towards the establishment of general principles. We shall thus obtain a sight of generalizations of a new kind and shall prepare ourselves for others of a higher order. 259, Book 14. The Analytical Science. History of Chemistry. Soon had his crew opened into the hill a spacious wound and digged out ribs of gold. Anon out of the earth a fabric huge rose like an exhalation, with the sound of dulcet symphonies and voices sweet, built like a temple. Milton. Paradise Lost, I. 261, Chapter 1. Improvement of the notion of chemical analysis, and recognition of it as the spagyric art. The doctrine of the four elements is one of the oldest monuments of man's speculative nature, goes back, perhaps, to times anterior to Greek philosophy, and as the doctrine of Aristotle and Galen reigned for 1,500 years over the Gentile, Christian, and Mohammedan world. In medicine, taught as the doctrine of the four elementary qualities, of which the human body and all other substances are compounded, it had a very powerful and extensive influence upon medical practice. But this doctrine never led to any attempt actually to analyze bodies into their supposed elements. For composition was inferred from the resemblance of the qualities, not from the separate exhibition of the ingredients. The supposed analysis was, in short, a decomposition of the body into adjectives, not into substances. This doctrine, therefore, may be considered as a negative state, antecedent to the very beginning of chemistry, and some progress beyond this mere negation was made, as soon as men began to endeavor to compound and decompound substances by the use of fire or mixture, however erroneous might be the opinions and expectations which they combined with their attempts. Alchemy is a step in chemistry, so far as it implies the recognition of the work of the cupel and the retort as the produce of analysis and synthesis. How perplexed and perverted were the forms in which this recognition was clothed, how mixed up with mythical follies and extravagancies, we have already seen, and the share which alchemy had in the formation of any sounder knowledge is not such as to justify any further notice of that pursuit. The result of the attempts to analyze bodies by heat, mixture, and the like processes was the doctrine that the first principles of things are three, not four, namely salt, sulfur, and mercury, and that, of these three, all things are compounded. In reality, the doctrine, as thus stated, contained no truth which was of any value. For though the chemist could extract from most bodies portions which he called salt, 262, and sulfur, and mercury, these names were given rather to save the hypothesis than because the substances were really those usually so called. And thus the supposed analyses proved nothing, as Boyle justly urged against them. The only real advance in chemical theory, therefore, which we can ascribe to the school of the three principles, as compared with those who held the ancient dogma of the four elements, is the acknowledgement of the changes produced by the chemist's operations as being changes which were to be accounted for by the union and separation of substantial elements, or, as they were sometimes called, of hypostatical principles. The workmen of this school acquired, no doubt, a considerable acquaintance with the results of the kinds of processes which they pursued. They applied their knowledge to the preparation of new medicines, and some of them, as Paracelsus and Van Helmont, attained in this way to great fame and distinction. But their merits, as regards theoretical chemistry, consist only in a truer conception of the problem and of the mode of attempting its solution than their predecessors had entertained. This step is well marked by a word which, about the time of which we speak, was introduced to denote the chemist's employment. It was called the spagyric art, often misspelled spagyric, from two Greek words, sigma pi alpha omega, letter 1 F00 gamma epsilon iota rho omega, which mean to separate parts and to unite them. These two processes, or in more modern language analysis and synthesis, constitute the whole business of the chemist. We are not making a fanciful arrangement, therefore, when we mark the recognition of this object as a step in the progress of chemistry. I now proceed to consider the manner in which the conditions of this analysis and synthesis were further developed. Chapter 2. Doctrine of Acid and Alkali, Sylvius. Among the results of mixture observed by chemists were many instances in which two ingredients, each in itself pungent or destructive, being put together, became mild and inoperative, each, 263, counteracting and neutralizing the activity of the other. The notion of such opposition and neutrality is applicable to a very wide range of chemical processes. The person who appears first to have steadily seized and generally applied this notion is Francis de la Baie Sylvius, who was born in 1614 and practiced medicine at Amsterdam, with a success and reputation which gave great currency to his opinions on that art. His chemical theories were propounded as subordinate to his medical doctrines, and from being thus presented under a most important practical aspect, excited far more attention than mere theoretical opinions on the composition of bodies could have done. Sylvius is spoken of by historians of science as the founder of the iatrochemical sect among physicians, that is, the sect which considers the disorders in the human frame as the effects of chemical relations of the fluids, and applies to them modes of cure founded upon this doctrine. We have here to speak, not of his physiological, but of his chemical views. Note 2/14. Sprengel. Geschichte der Arsenikund, Volume Roman 4. Thomson's History of Chemistry in the corresponding part is translated from Sprengel. The distinction of acid and alkaline bodies, acidum, lixivium, was familiar before the time of Sylvius, but he framed a system, by considering them both as eminently acrid and yet opposite, and by applying this notion to the human frame. Thus the lymph contains an acid, the bile an alkaline salt. These two opposite acrid substances, when they are brought together, neutralize each other in fringunt, and are changed into an intermediate and milder substance. Note 3/14, De Methodo Medendi Amst, 1679, Lib Roman 2, Cap. 28 Sex. 8 and 53. The progress of this doctrine, as a physiological one, is an important part of the history of medical science in the 17th century. But with that we are not here concerned. But as a chemical doctrine, this notion of the opposition of acid and alkali, and of its very general applicability, struck deep root, and has not been eradicated up to our own time. Boyle, indeed, whose disposition led him to suspect all generalities, expressed doubts with regard to this view, and argued that the supposition of acid and alkaline parts in all bodies was precarious, their offices arbitrary, and the notion of them unsettled. Indeed, it was not difficult to show that there was no one certain criterion to which all supposed acids conformed. Yet the general conception of such a combination as that of acid and alkali was supposed to 264b served so well to express many chemical facts that it kept its ground. It is found, for instance, in Lemery's chemistry, which was one of those in most general use before the introduction of the phlogistic theory. In this work, which was translated into English by Kale, in 1698, we find alkalis defined by their effervescing with acids. They were distinguished as the mineral alkali, soda, the vegetable alkali, potassa, and the volatile alkali, ammonia. Again, in Macker's chemistry, which was long the textbook in Europe during the reign of phlogiston, we find acids and alkalis, and their union, in which they rob each other of their characteristic properties and form neutral salts, stated among the leading principles of the science. In truth, the mutual relation of acids to alkalis was the most essential part of the knowledge which chemists possessed concerning them. The importance of this relation arose from its being the first distinct form in which the notion of chemical attraction or affinity appeared. For the acrid or caustic character of acids and alkalis is, in fact, a tendency to alter the bodies they touch, and thus to alter themselves. And the neutral character of the compounds is the absence of any such proclivity to change. Acids and alkalis have a strong disposition to unite. They combine, often with vehemence, and produce neutral salts. They exhibit, in short, a prominent example of the chemical attraction, or affinity, by which two ingredients are formed into a compound. The relation of acid and base in a salt is, to this day, one of the main grounds of all theoretical reasonings. The more distinct development of the notion of such chemical attraction gradually made its way among the chemists of the latter part of the 17th and the beginning of the 18th century, as we may see in the writings of Boyle, Newton, and their followers. Beecher speaks of this attraction as a magnetism, but I do not know that any writer in particular can be pointed out as the person who firmly established the general notion of chemical attraction. But this idea of chemical attraction became both more clear and more extensively applicable when it assumed the form of the doctrine of elective attractions, in which shape we must now speak of it. 265. Chapter 3. Doctrine of Elective Attractions, Geoffroy Bergman. Though the chemical combinations of bodies had already been referred to attraction, in a vague and general manner, it was impossible to explain the changes that take place, without supposing the attraction to be greater or less, according to the nature of the body. Yet it was some time before the necessity of such a supposition was clearly seen. In the History of the French Academy for 1718, published 1719, the writer of the introductory notice, probably Fontenelle, says that a body which is united to another, for example, a solvent which has penetrated a metal, should quit it to go and unite itself with another which we present to it, is a thing of which the possibility had never been guessed by the most subtle philosophers, and of which the explanation even now is not easy. The doctrine had in fact been stated by Stahl, but the assertion just quoted shows, at least, that it was not familiar. The principle, however, is very clearly stated in a memoir in the same volume, by Geoffroy, a French physician of great talents and varied knowledge. We observe in chemistry, he says, certain relations amongst different bodies, which cause them to unite. These relations have their degrees and their laws. We observe their different degrees in this, that among different matters jumbled together, which have a certain disposition to unite, we find that one of these substances always unites constantly with a certain other, preferably to all the rest. He then states that those which unite by preference have plus de rapport, or, according to a phrase afterwards used, more affinity. And I have satisfied myself, he adds, that we may deduce from these observations the following proposition, which is very extensively true, though I cannot enunciate it as universal, not having been able to examine all the possible combinations, to assure myself that I should find no exception. The proposition which he states in this admirable spirit of philosophical caution is this: in all cases where two substances, 266, which have any disposition to combine, are united, if there approaches them a third, which has more affinity with one of the two, this one unites with the third and lets go the other. He then states these affinities in the form of a table, placing a substance at the head of each column and other substances in succession below it, according to the order of their affinities for the substance which stands at the head. He allows that the separation is not always complete, an imperfection which he ascribes to the glutinosity of fluids and other causes. But, with such exceptions, he defends very resolutely and successfully his table, and the notions which it implies. The value of such a tabulation was immense at the time, and is even still very great. It enabled the chemist to trace beforehand the results of any operation, since, when the ingredients were given, he could see which were the strongest of the affinities brought into play, and, consequently, what compounds would be formed. Geoffroy himself gave several good examples of this use of his table. It was speedily adopted into works on chemistry. For instance, Macker places it at the end of his book, taking it, as he says, to be of great use at the end of an elementary tract, as it collects into one point of view the most essential and fundamental doctrines which are dispersed through the work. The doctrine of elective attraction, as thus promulgated, contained so large a mass of truth that it was never seriously shaken, though it required further development and correction. In particular, the celebrated work of Torbern Bergman, professor at Uppsala, on elective attractions, published in 1775, introduced into it material improvements. Bergman observed that not only the order of attractions, but the sum of those attractions which had to form the new compounds must be taken account of in order to judge of the result. Thus, if we have a combination of two elements P, S, potassa and vitriolic acid, and another combination, L, M, lime and muriatic acid, though S has a greater affinity for P than for L, yet the sum of the attractions of P to M and of L to S is greater than that of the original compounds, and therefore if the two combinations are brought together, the new compounds P, M, and L, S are formed. The table of elective attractions, modified by Bergman in pursuance of these views, and corrected according to the advanced knowledge of the time, became still more important than before. The next step, 267, was to take into account the quantities of the elements which combined. But this leads us into a new train of investigation, which was, indeed, a natural sequel to the researches of Geoffroy and Bergman. In 1803, however, a chemist of great eminence, Berthollet, published a work, Essai de statique chimique, the tendency of which appeared to be to throw the subject back into the condition in which it had been before Geoffroy. For Berthollet maintained that the rules of chemical combination were not definite and dependent on the nature of the substances alone, but indefinite, depending on the quantity present and other circumstances. Proust answered him, and as Berzelius says, Berthollet defended himself with an acuteness which makes the reader hesitate in his judgment. But the great mass of facts finally decided the point in favor of Proust. Before, however, we trace the result of these researches, we must consider chemistry as extending her inquiries to combustion as well as mixture, to airs as well as fluids and solids, and to weight as well as quality. These three steps we shall now briefly treat of. Chapter 4. Doctrine of acidification and combustion phlogistic theory. Publication of the theory by Becker and Stahl. It will be recollected that we are tracing the history of the progress only of chemistry, not of its errors, that we are concerned with doctrines only so far as they are true, and have remained part of the received system of chemical truths. The phlogistic theory was deposed and succeeded by the theory of oxygen. But this circumstance must not lead us to overlook the really sound and permanent part of the opinions which the founders of the phlogistic theory taught. They brought together, as processes of the same kind, a number of changes which at first appeared to have nothing in common, as acidification, combustion, respiration. Now this classification is true, and its importance remains undiminished, whatever are the explanations which we adopt of the processes themselves. The two chemists to whom are to be ascribed the merit of this step, and the establishment of the phlogistic theory which they connected, 268 with it, are John Joachim Becher and George Ernest Stahl, the former of whom was professor at Mentz and physician to the Elector of Bavaria, born 1625, died 1682. The latter was professor at Halle, and afterwards royal physician at Berlin, born 1660, died 1734. These two men, who thus contributed to a common purpose, were very different from each other. The first was a frank and ardent enthusiast in the pursuit of chemistry, who speaks of himself and his employments with a communicativeness and affection both amusing and engaging. The other was a teacher of great talents and influence, but accused of haughtiness and moroseness, a character which is well borne out by the manner in which, in his writings, he anticipates an unfavorable reception and defies it. But it is right to add to this that he speaks of Becher, his predecessor, with an ungrudging acknowledgement of obligations to him and a vehement assertion of his merit as the founder of the true system, which give a strong impression of Stahl's justice and magnanimity. Becher's opinions were at first promulgated rather as a correction than a refutation of the doctrine of the three principles, salt, sulfur, and mercury. The main peculiarity of his views consists in the offices which he ascribes to his sulfur, these being such as afterwards induced Stahl to give the name of phlogiston to this element. Becher had the sagacity to see that the reduction of metals to an earthy form, calx, and the formation of sulfuric acid from sulfur are operations connected by a general analogy, as being alike processes of combustion. Hence the metal was supposed to consist of an earth, and of something which in the process of combustion was separated from it, and in like manner, sulfur was supposed to consist of the sulfuric acid, which remained after its combustion, and of the combustible part or true sulfur, which flew off in the burning. Becher insists very distinctly upon this difference between his element, sulfur, and the sulfur of his Paracelsian predecessors. It must be considered as indicating great knowledge and talent in Stahl, that he perceived so clearly what part of the views of Becher was of general truth and permanent value. Though he everywhere gives to Becher the credit of the theoretical opinions which he promulgates, Beccheriana sunt qui profero, it seems certain that he had the merit, not only of proving them more completely, and applying them more widely than his forerunner, but also of conceiving them, 269, with a distinctness which Becher did not attain. In 1697 appeared Stahl's Zymotechnia Fundamentalis, the doctrine of fermentation, Simulc experimentum novum sulfur verum art producendi. In this work, besides other tenets which the author considered as very important, the opinion published by Becher was now maintained in a very distinct form, namely, that the process of forming sulfur from sulfuric acid and of restoring the metals from their calces are analogous, and consist alike in the addition of some combustible element, which Stahl termed phlogiston, phi lambda omicron gamma iota sigma tau omicron u, combustible. The experiment most insisted on in the work now spoken of was the formation of sulfur from sulfate of potass, or of soda, by fusing the salt with an alkali and throwing in coals to supply phlogiston. This is the experimentum novum. Though Stahl published an account of this process, he seems to have regretted his openness. He denies not, he says, that he should peradventure have dissembled this experiment as the true foundation of the Beckerian assertion concerning the nature of sulfur, if he had not been provoked by the pretending arrogance of some of his contemporaries. From this time, Stahl's confidence in his theory may be traced becoming more and more settled in his succeeding publications. It is hardly necessary to observe here that the explanations which his theory gives are easily transformed into those which the more recent theory supplies. According to modern views, the addition of oxygen takes place in the formation of acids and of calces, and in combustion, instead of the subtraction of phlogiston. The coal which Stahl supposed to supply the combustible in his experiment does in fact absorb the liberated oxygen. In like manner, when an acid corrodes a metal and, according to existing theory, combines with and oxidates it, Stahl supposed that the phlogiston separated from the metal and combined with the acid. That the explanations of the phlogistic theory are so generally capable of being translated into the oxygen theory, merely by inverting the supposed transfer of the combustible element, shows us how important a step towards the modern doctrines the phlogistic theory really was. The question, whether these processes were in fact addition or subtraction, was decided by the balance and belongs to a succeeding period of the science. But we may observe that both Becher and Stahl were aware of the increase of weight which metals undergo in 270 calcination, although the time had not yet arrived in which this fact was to be made one of the bases of the theory. It has been said that in the adoption of the phlogistic theory, that is, in supposing the above-mentioned processes to be addition rather than subtraction, of two possible roads the wrong was chosen, as if to prove the perversity of the human mind. But we must not forget how natural it was to suppose that some part of a body was destroyed or removed by combustion, and we may observe that the merit of Becher and Stahl did not consist in the selection of one road or two, but in advancing so far as to reach this point of separation. That, having done this, they went a little further on the wrong line was an error which detracted little from the merit or value of the progress really made. It would be easy to show, from the writings of phlogistic chemists, what important and extensive truths their theory enabled them to express simply and clearly. That an enthusiastic temper is favorable to the production of great discoveries in science is a rule which suffers no exception in the character of Becher. In his preface addressed to the benevolent reader of his Physica Subterranea, he speaks of the chemists as a strange class of mortals, impelled by an almost insane impulse to seek their pleasure among smoke and vapor, soot and flame, poisons and poverty. Yet among all these evils, he says, I seem to myself to live so sweetly that may I die if I would change places with the Persian king. He is, indeed, well worthy of admiration, as one of the first who pursued the labors of the furnace and the laboratory without the bribe of golden hopes. My kingdom, he says, is not of this world. I trust that I have got hold of my pitcher by the right handle the true method of treating this study. For the pseudo-chemists seek gold, but the true philosophers, science, which is more precious than any gold. The Physica Subterranea made no converts. Stahl, in his indignant manner, says, no one will wonder that it never yet obtained a physician or a chemist as a disciple, still less as an advocate. And again, this work obtained very little reputation or estimation, or to speak ingenuously, as far as I know, none whatever. In 1671, Becher published a supplement to his work, in which he showed how metal might be extracted from mud and sand. He offered to execute 271 this at Vienna, but found that people there cared nothing about such novelties. He was then induced by Baron d'Isola to go to Holland for similar purposes. After various delays and quarrels, he was obliged to leave Holland for fear of his creditors, and then, I suppose, came to Great Britain, where he examined the Scottish and Cornish mines. He is said to have died in London in 1682. Stahl's publications appear to have excited more notice and led to controversy on the so-called sulfur. The success of the experiment had been doubted, which, as he remarks, it was foolish to make a matter of discussion when anyone might decide the point by experiment. And finally, it had been questioned whether the substance obtained by this process were pure sulfur. The originality of his doctrine was also questioned, which, as he says, could not with any justice be impugned. He published in defense and development of his opinion at various intervals, as the Specimen Beckerianum in 1703, the Documentum Theoriae Beecheriani, a dissertation de anatomia sulphuris artificialis, and finally, Casual Thoughts on the so-called sulfur in 1718, in which he gave, in German, both a historical and a systematic view of his opinions on the nature of salts and of his phlogiston. Reception and application of the theory that the formation of sulfuric acid and the restoration of metals from their calces are analogous processes and consist in the addition of phlogiston was soon widely received, and the phlogistic school was thus established. From Berlin, its original seat, it was diffused into all parts of Europe. The general reception of the theory may be traced, not only in the use of the term phlogiston and of the explanations which it implies, but in the adoption of a nomenclature founded on those explanations, which, though not very extensive, is sufficient evidence of the prevalence of the theory. Thus, when Priestley in 1774 discovered oxygen, and when Scheele a little later discovered chlorine, these gases were termed dephlogisticated air and dephlogisticated marine acid, while azotic acid gas, having no disposition to combustion, was supposed to be saturated with phlogiston and was called phlogisticated air. This phraseology kept its ground till it was expelled by the antiphlogistic or oxygen theory. For instance, Cavendish's papers on the chemistry of the airs are expressed in terms of it, although his researches led him to the confines of the new theory. We must now give an account of such researches and of the consequent revolution in the science. 272. Chapter 5. Chemistry of Gases. Black, Cavendish. The study of the properties of aeriform substances, or pneumatic chemistry, as it was called, occupied the chemists of the 18th century, and was the main occasion of the great advances which the science made at that period. The most material general truths which came into view in the course of these researches were that gases were to be numbered among the constituent elements of solid and fluid bodies, and that, in these, as in all other cases of composition, the compound was equal to the sum of its elements. The latter proposition, indeed, cannot be looked upon as a discovery, for it had been frequently acknowledged, though little applied. In fact, it could not be referred to with any advantage, till the aeriform elements, as well as others, were taken into the account. As soon as this was done, it produced a revolution in chemistry. Though the view of the mode in which gaseous elements become fixed in bodies and determine their properties had great additional light thrown upon it by Dr. Black's discoveries, as we shall see, the notion that solid bodies involve such gaseous elements was not new at that period. Mr. Vernon Harcourt has shown that Newton and Boyle admitted into their speculations airs of various kinds, capable of fixation in bodies. I have, in the succeeding chapter, chapter Roman 6, spoken of the views of Ray, Hooke, and Mayow, connected with the function of airs in chemistry, and forming a prelude to the oxygen theory. Notwithstanding these preludes, the credit of the first great step in pneumatic chemistry is, with justice, assigned to Dr. Black, afterwards professor at Edinburgh, but a young man of the age of 24 at the time when he made his discovery. He found that the difference between caustic lime and common limestone arose from this, that the latter substance consists of the former, combined with a certain air, which being thus fixed in the solid body, he called fixed air carbonic 273 acid gas. He found, too, that magnesia, caustic potash, and caustic soda would combine with the same air, with similar results. This discovery consisted, of course, in a new interpretation of observed changes. Alkalis appeared to be made caustic by contact with quicklime. At first, Black imagined that they underwent this change by acquiring igneous matter from the quicklime. But when he perceived that the lime gained, not lost, in magnitude as it became mild, he rightly supposed that the alkalis were rendered caustic by imparting their air to the lime. This discovery was announced in Black's inaugural dissertation, pronounced in 1755, on the occasion of his taking his degree of doctor in the University of Edinburgh. The chemistry of airs was pursued by other experimenters. The Honorable Henry Cavendish, about 1765, invented an apparatus in which aerial fluids are confined by water so that they can be managed and examined. This hydropneumatic apparatus, or as it is sometimes called, the pneumatic trough, from that time was one of the most indispensable parts of the chemist's apparatus. Cavendish, in 1766, showed the identity of the properties of fixed air derived from various sources, and pointed out the peculiar qualities of inflammable air, afterwards called hydrogen gas, which, being 9 times lighter than common air, soon attracted general notice by its employment for raising balloons. The promise of discovery which this subject now offered attracted the confident and busy mind of Priestley, whose experiments and observations on different kinds of air appeared in 1744-79. In these volumes, he describes an extraordinary number of trials of various kinds, the results of which were the discovery of new kinds of air, namely phlogisticated air, azotic gas, nitrous air, nitrous gas, and dephlogisticated air, oxygen gas. But the discovery of new substances, though valuable in supplying chemistry with materials, was not so important as discoveries respecting their modes of composition. Among such discoveries, that of Cavendish, published in the Philosophical Transactions for 1784, and disclosing the composition of water by the union of two gases, oxygen and hydrogen, must be considered as holding a most distinguished place. He states that his experiments were made principally with a view to find out the cause of the diminution which common air is well known to suffer, by all the various ways in which it is phlogisticated. And, after describing various unsuccessful attempts, he finds, 274, that when inflammable air is used in this phlogistication, or burning, the diminution of the common air is accompanied by the formation of a dew in the apparatus. And thus he infers that almost all the inflammable air, and 1/5 of the common air, are turned into pure water. Lavoisier, to whose researches this result was, as we shall soon see, very important, was employed in a similar attempt at the same time, 1783, and had already succeeded when he learned from Dr. Blagden, who was present at the experiment, that Cavendish had made the discovery a few months sooner. Monge had, about the same time, made the same experiments, and communicated the result to Lavoisier and Laplace immediately afterwards. The synthesis was soon confirmed by a corresponding analysis. Indeed, the discovery undoubtedly lay in the direct path of chemical research at the time. It was of great consequence in the view it gave of experiments in composition, for the small quantity of water produced in many such processes had been quite overlooked, though, as it now appeared, this water offered the key to the whole interpretation of the change. Though some objections to Mr. Cavendish's view were offered by Kirwan, on the whole they were generally received with assent and admiration. But the bearing of these discoveries upon the new theory of Lavoisier, who rejected phlogiston, was so close that we cannot further trace the history of the subject without proceeding immediately to that theory. With reference to recent attempts to deprive Cavendish of the credit of his discovery of the composition of water, and to transfer it to Watt not only did not anticipate, but did not fully appreciate the discovery of Cavendish and Lavoisier. And I have expressed my concurrence with Mr. Vernon Harcourt's views, when he says that Cavendish paired off from the current hypotheses their theory of combustion, and their affinities of imponderable for ponderable matter, as complicating chemical with physical considerations. And he then corrected and adjusted them with admirable skill to the actual phenomena, not binding the facts to the theory, but adapting the theory to the facts. I conceive that the discussion which the subject has recently received has left no doubt on the mind of anyone who has perused the 275 documents that Cavendish is justly entitled to the honor of this discovery, which in his own time was never contested. The publication of his journals of experiments shows that he succeeded in establishing the point in question in July, 1781. His experiments are referred to in an abstract of a paper of Priestley's, made by Dr. Mady, the Secretary of the Royal Society, in June 1783. In June 1783, also, Dr. Blagden communicated the result of Cavendish's experiments to Lavoisier, at Paris. Watt's letter, containing his hypothesis that water is composed of dephlogisticated air and phlogiston deprived of part of their latent or elementary heat, and that phlogisticated or pure air is composed of water deprived of its phlogiston and united to elementary heat and light, was not read till Nov. 1783, and even if it could have suggested such an experiment as Cavendish's, which does not appear likely, is proved, by the dates, to have had no share in doing so. Mr. Cavendish's experiment was suggested by an experiment in which Woltaire, a lecturer on chemistry at Birmingham, exploded a mixture of hydrogen and common air in a close vessel, in order to determine whether heat were ponderable. Chapter 6. Epoch of the Theory of Oxygen, Lavoisier. Sect 1. Prelude to the Theoriot's publication. We arrive now at a great epoch in the history of chemistry. Few revolutions in science have immediately excited so much general notice as the introduction of the theory of oxygen, the simplicity and symmetry of the modes of combination which it assumed, and above all, the construction and universal adoption of a nomenclature which applied to all substances, and which seemed to reveal their inmost constitution by their name, naturally gave it an almost irresistible sway over men's minds. We must, however, dispassionately trace the course of its introduction. 276. Antoine Laurent Lavoisier, an accomplished French chemist, had pursued, with zeal and skill, researches such as those of Black, Cavendish, and Priestley, which we have described above. In 1774, he showed that in the calcination of metals in air, the metal acquires as much weight as the air loses. It might appear that this discovery at once overturned the view which supposed the metal to be phlogiston added to the calx. Lavoisier's contemporaries were, however, far from allowing this. A greater mass of argument was needed to bring them to this conclusion. Convincing proofs of the new opinion were, however, rapidly supplied. Thus, when Priestley had discovered dephlogisticated air in 1774, Lavoisier showed in 1776 that fixed air consisted of charcoal and the dephlogisticated or pure air. For the mercurial calx, which, heated by itself, gives out pure air, gives out, when heated with charcoal, fixed air, which has therefore since been called carbonic acid gas. Again, Lavoisier showed that the atmospheric air consists of pure or vital air and of an unvital air, which he thence called azot. The vital air he found to be the agent in combustion, acidification, calcination, respiration. All of these processes were analogous. All consisted in a decomposition of the atmospheric air and a fixation of the pure or vital portion of it. But he thus arrived at the conclusion that this pure air was added in all the cases in which, according to the received theory, phlogiston was subtracted, and vice versa. He gave the name of oxygen, principe oxygene, to the substance which thus unites itself with metals to form their calces and with combustible substances to form acids. A new theory was thus produced, which would account for all the facts which the old one would explain, and had besides the evidence of the balance in its favor. But there still remained some apparent objections to be removed. In the action of dilute acids on metals, inflammable air was produced. Whence came this element? The discovery of the decomposition of water sufficiently answered this question, and converted the objection into an argument on the side of the theory. And thus the decomposition of water was, in fact, one of the most critical events for the fortune of the Lavoisierian doctrine, and one which, more than any other, decided chemists in its favor. In succeeding years, Lavoisier showed the consistency of his theory with 277 all that was discovered concerning the composition of alcohol, oil, animal and vegetable substances, and many other bodies. It is not necessary for us to consider any further the evidence for this theory, but we must record a few circumstances respecting its earlier history. Ray, a French physician, had in 1630 published a book in which he inquires into the grounds of the increase of the weight of metals by calcination. He says, "To this question, then, supported on the grounds already mentioned, I answer and maintain with confidence that the increase of weight arises from the air, which is condensed, rendered heavy and adhesive by the heat of the furnace." Hooke and Mayow had entertained the opinion that the air contains a nitrous spirit, which is the supporter of combustion. But Lavoisier disclaimed the charge of having derived anything from these sources. Nor is it difficult to understand how the received generalizations of the phlogistic theory had thrown all such narrower explanations into obscurity. The merit of Lavoisier consisted in his combining the generality of Stahl with the verified conjectures of Ray and Mayow. No one could have a better claim, by his early enthusiasm for science, his extensive knowledge, and his zealous labors, to hope that a great discovery might fall to his share than Lavoisier. His father, a man of considerable fortune, had allowed him to make science his only profession, and the zealous philosopher collected about him a number of the most active physical inquirers of his time, who met and experimented at his house one day in the week. In this school, the new chemistry was gradually formed. A few years after the publication of Priestley's first experiments, Lavoisier was struck with the presentiment of the theory which he was afterwards to produce. In 1772, he deposited with the Secretary of the Academy a note which contained the germ of his future doctrines. At that time, he says, in explaining this step, there was a kind of rivalry between France and England in science, which gave importance to new experiments, and which sometimes was the cause that the writers of the one or other of the nations disputed the discovery with the real author. In 1777, the editor of the Memoirs of the Academy speaks of his theory as overturning that of Stahl, but the general acceptance of the new opinion did not take place till later. 278. Sect 2. Reception and confirmation of the theory of oxygen. The oxygen theory made its way with extraordinary rapidity among the best philosophers. In 1785, that is, soon after Cavendish's synthesis of water had removed some of the most formidable objections to it, Berthollet, already an eminent chemist, declared himself a convert. Indeed, it was so soon generally adopted in France that Fourcroy promulgated its doctrines under the name of La Chimie Francaise, a title which Lavoisier did not altogether relish. The extraordinary eloquence and success of Fourcroy as a lecturer at the Jardin des Plantes had no small share in the diffusion of the oxygen theory, and the name of the apostle of the new chemistry, which was at first given him in ridicule, was justly held by him to be a glorious distinction. Guyton de Morveau, who had at first been a strenuous advocate of the phlogistic theory, was invited to Paris and brought over to the opinions of Lavoisier, and soon joined in the formation of the nomenclature founded upon the theory. This step, of which we shall shortly speak, fixed the new doctrine and diffused it further. De Lametherie alone defended the phlogistic theory with vigor and indeed with violence. He was the editor of the Journal de Physique, and to evade the influence which this gave him, the antiphlogistians established, as the vehicle of their opinions, another periodical, the Annals de Chimie. In England, indeed, their success was not so immediate. Cavendish, in his memoir of 1784, speaks of the question between the two opinions as doubtful. There are, he says, several memoirs of M. Lavoisier in which he entirely discards phlogiston, and as not only the foregoing experiments, but most other phenomena of nature, seem explicable as well, or nearly as well, upon this as upon the commonly believed principle of phlogiston, Cavendish proceeds to explain his experiments according to the new views, expressing no decided preference, however, for either system. But Kirwan, another English chemist, contested the point much more resolutely. His theory identified inflammable air, or hydrogen, with phlogiston, and in this view, he wrote a work which was intended as a confutation of 279, the essential part of the oxygen theory. It is a strong proof of the steadiness and clearness with which the advocates of the new system possessed their principles, that they immediately translated this work, adding, at the end of each chapter, a refutation of the phlogistic doctrines which it contained. Lavoisier, Berthollet, de Morveau, Fourcroy, and Monge were the authors of this curious specimen of scientific polemics. It is also remarkable evidence of the candor of Kirwan that, notwithstanding the prominent part he had taken in the controversy, he allowed himself at last to be convinced. After a struggle of 10 years, he wrote to Berthollet in 1796, "I lay down my arms and abandoned the cause of phlogiston." Black followed the same course. Priestley alone, of all the chemists of great name, would never assent to the new doctrines, though his own discoveries had contributed so much to their establishment. He saw, says Cuvier, without flinching, the most skillful defenders of the ancient theory go over to the enemy in succession. And when Kirwan had, almost the last of all, abjured phlogiston, Priestley remained alone on the field of battle, and threw out a new challenge in a memoir addressed to the principal French chemists. It happened, curiously enough, that the challenge was accepted, and the arguments answered by M. Adet, who was at that time, 1798, the French ambassador to the United States, in which country Priestley's work was published. Even in Germany, the birthplace and home of the phlogistic theory, the struggle was not long protracted. There was, indeed, a controversy, the older philosophers being, as usual, the defenders of the established doctrines. But in 1792, Klaproth repeated, before the Academy of Berlin, all the fundamental experiments, and the result was a full conviction on the part of Klaproth and the Academy that the Lavoisierian theory was the true one. Upon the whole, the introduction of the Lavoisierian theory in the scientific world, when compared with the great revolution of opinion to which it comes nearest in importance, the introduction of the Newtonian theory, shows, by the rapidity and temper with which it took place, a great improvement, both in the means of arriving at truth and in the spirit with which they were used. Some English writers have expressed an opinion that there was 280, little that was original in the new doctrines. But if they were so obvious, what are we to say of eminent chemists, as Black and Cavendish, who hesitated when they were presented, or Kirwan and Priestley, who rejected them? This at least shows that it required some peculiar insight to see the evidence of these truths. To say that most of the materials of Lavoisier's theory existed before him is only to say that his great merit was that which must always be the great merit of a new theory, his generalization. The effect which the publication of his doctrines produced shows us that he was the first person who, possessing clearly the idea of quantitative composition, applied it steadily to a great range of well-ascertained facts. This is, as we have often had to observe, precisely the universal description of an inductive discoverer. It has been objected, in like manner, to the originality of Newton's discoveries, that they were contained in those of Kepler. They were so, but they needed a Newton to find them there. The originality of the theory of oxygen is proved by the conflict, short as it was, which accompanied its promulgation. Its importance is shown by the changes which it soon occasioned in every part of the science. Note 39/14, Brand Hist, Dis, in Enk Brit, p. 182, Lun Chem, in Enk, Met, p. 596. Thus Lavoisier, far more fortunate than most of those who had, in earlier ages, produced revolutions in science, saw his theory accepted by all the most eminent men of his time, and established over a great part of Europe within a few years from its first promulgation. In the common course of events, it might have been expected that the later years of his life would have been spent amid the admiration and reverence which naturally wait upon the patriarch of a new system of acknowledged truths. But the times in which he lived allowed no such euthanasia to eminence of any kind. The democracy which overthrew the ancient political institutions of France and swept away the nobles of the land was not, as might have been expected, enthusiastic in its admiration of a great revolution in science, and forward to offer its homage to the genuine nobility of a great discoverer. Lavoisier was thrown into prison on some wretched charge of having, in the discharge of a public office which he had held, adulterated certain tobacco, but in reality for the purpose of confiscating his property. In his imprisonment, his philosophy was his resource, and he employed himself in the preparation of his papers for printing. When he was brought before the Revolutionary Tribunal, he begged for a respite of a few days, in order to complete some researches, the results of which 281 were, he said, important to the good of humanity. The brutish idiot, whom the state of the country at that time had placed in the judgment seat, told him that the Republic wanted no scavans. He was dragged to the guillotine, May the 8th, 1794, and beheaded, in the 52nd year of his age. A melancholy proof that, in periods of political ferocity, innocence and merit, private virtues and public services, amiable manners and the love of friends, literary fame and exalted genius, are all as nothing to protect their possessor from the last extremes of violence and wrong inflicted under judicial forms. Sect 3 Nomenclature of the oxygen theory. As we have already said, a powerful instrument in establishing and diffusing the new chemical theory was a systematic nomenclature founded upon it, and applicable to all chemical compounds, which was soon constructed and published by the authors of the theory. Such a nomenclature made its way into general use the more easily, in that the want of such a system had already been severely felt, the names in common use being fantastical, arbitrary, and multiplied beyond measure. The number of known substances had become so great that a list of names with no regulative principle, founded on accident, caprice, and error, was too cumbrous and inconvenient to be tolerated. Even before the currency which Lavoisier's theory obtained, these evils had led to attempts towards a more convenient set of names. Bergman and Black had constructed such lists, and Guyton de Morveau, a clever and accomplished lawyer of Dijon, had formed a system of nomenclature in 1782, before he had become a convert to Lavoisier's theory, in which task he had been exhorted and encouraged by Bergman and Macquer. In this system, we do not find most of the characters of the method which was afterwards adopted. But a few years later, Lavoisier, de Morveau, Berthollet, and Fourcroy associated themselves for the purpose of producing a nomenclature which should correspond to the new theoretical views. This appeared in 1787 and soon made its way into general use. The main features of this system are a selection of the simplest radical words, by which substances are designated, and a systematic distribution of terminations to express their relations. Thus, sulfur, combined with oxygen in two different proportions, forms two acids, the 282 sulfurose and the sulfur ike, and these acids form, with earthy or alkaline bases, sulfides and sulfates, while sulfur directly combined with another element forms a sulfuret. The term oxide, now usually written oxide, expressed a lower degree of combination with oxygen than the acids. The Méthode de nomenclature chimique was published in 1787, and in 1789, Lavoisier published a treatise on chemistry in order further to explain this method. In the preface to this volume, he apologizes for the great amount of the changes and pleads the authority of Bergman, who had exhorted de Morveau to spare no improper names. Those who are learned will always be learned, and those who are ignorant will thus learn sooner. To this maxim they so far conformed that their system offers few anomalies, and though the progress of discovery and the consequent changes of theoretical opinion, which have since gone on, appear now to require a further change of nomenclature, it is no small evidence of the skill with which this scheme was arranged, that for half a century it was universally used, and felt to be far more useful and effective than any nomenclature in any science had ever been before. Chapter 7. Application and correction of the oxygen theory. Since a chemical theory, as far as it is true, must enable us to obtain a true view of the intimate composition of all bodies whatever, it will readily be supposed that the new chemistry led to an immense number of analyses and researches of various kinds. These it is not necessary to dwell upon, nor will I even mention the names of any of the intelligent and diligent men who have labored in this field. Perhaps one of the most striking of such analyses was Davy's decomposition of the earths and alkalis into metallic bases and oxygen in 1807 and 1808, thus extending still further that analogy between the earths and the calces of the metals, which had had so large a share in the formation of chemical theories. This discovery, however, both in the means by which it was made and in the views to which it led, bears upon subjects hereafter to be treated of. The Lavoisierian theory also, wide as was the range of truth which it embraced, required some limitation and correction. I do not now, 283, speak of some erroneous opinions entertained by the author of the theory, as, for instance, that the heat produced in combustion, and even in respiration, arose from the conversion of oxygen gas to a solid consistence, according to the doctrine of latent heat. Such opinions not being necessarily connected with the general idea of the theory need not here be considered, but the leading generalization of Lavoisier, that acidification was always combination with oxygen, was found untenable. The point on which the contest on this subject took place was the constitution of the oxymuriatic and muriatic acids, as they had been termed by Berthollet, from the belief that muriatic acid contained oxygen and oxymuriatic a still larger dose of oxygen. In opposition to this, a new doctrine was put forward in 1809 by Gay-Lussac and Thénard in France, and by Davy in England, namely, that oxymuriatic acid was a simple substance, which they termed chlorine, and that muriatic acid was a combination of chlorine with hydrogen, which therefore was called hydrochloric acid. It may be observed that the point in dispute in the controversy on this subject was nearly the same which had been debated in the course of the establishment of the oxygen theory, namely, whether in the formation of muriatic acid from chlorine, oxygen is subtracted or hydrogen added, and the water concealed. In the course of this dispute, it was allowed on both sides that the combination of dry muriatic acid and ammonia afforded an experimentum crucis, since, if water was produced from these elements, oxygen must have existed in the acid. Davy being at Edinburgh in 1812, this experiment was made in the presence of several eminent philosophers, and the result was found to be that though a slight dew appeared in the vessel, there was not more than might be ascribed to unavoidable imperfection in the process, and certainly not so much as the old theory of muriatic acid required. The new theory, after this period, obtained a clear superiority in the minds of philosophical chemists and was further supported by new analogies. For the existence of one hydrocide being thus established, it was found that other substances gave similar combinations, and thus chemists obtained the hydriotic, hydrofluoric, and hydrobromic acids. These acids, it is to be observed, form salts with bases in the same manner as the oxygen acids do. The analogy of the muriatic and fluoric compounds was first clearly urged by a philosopher who was 284, not peculiarly engaged in chemical research, but who was often distinguished by his rapid and happy generalizations, Ampere. He supported this analogy by many ingenious and original arguments in letters written to Davy, while that chemist was engaged in his researches on fluorspar, as Davy himself declares. Still further changes have been proposed in that classification of elementary substances to which the oxygen theory led. It has been held by Berzelius and others that other elements, as, for example, sulfur, form salts with the alkaline and earthy metals rather than sulfurates. The character of these sulfosalts, however, is still questioned among chemists, and therefore it does not become us to speak as if their place in history were settled. Of course, it will easily be understood that, in the same manner in which the oxygen theory introduced its own proper nomenclature, the overthrow or material transformation of the theory would require a change in the nomenclature. Or rather, the anomalies which tended to disturb the theory would, as they were detected, make the theoretical terms be felt as inappropriate, and would suggest the necessity of a reformation in that respect. But the discussion of this point belongs to a step of the science which is to come before us hereafter. It may be observed that in approaching the limits of this part of our subject, as we are now doing, the doctrine of the combination of acids and bases, of which we formerly traced the rise and progress, is still assumed as a fundamental relation by which other relations are tested. This remark connects the stage of chemistry now under our notice with its earliest steps. But in order to point out the chemical bearing of the next subjects of our narrative, we may further observe that metals, earths, salts are spoken of as known classes of substances, and in like manner the newly discovered elements which form the last trophies of chemistry have been distributed into such classes according to their analogies. Thus potassium, sodium, barium have been asserted to be metals. Iodine, bromine, fluorine have been arranged as analogical to chlorine. Yet there is something vague and indefinite in the boundaries of such classifications and analogies, and it is precisely where this vagueness falls that the science is still obscure or doubtful. We are led, therefore, to see the dependence of chemistry upon classification, and it is to sciences of classification which we shall next proceed. As soon as we have noticed the most general views, 285, which have been given of chemical relations, namely, the views of the electrochemists. But before we do this, we must look back upon a law which obtains in the combination of elements, and which we have hitherto not stated, although it appears, more than any other, to reveal to us the intimate constitution of bodies, and to offer a basis for future generalizations. I speak of the atomic theory, as it is usually termed, or, as we might rather call it, the doctrine of definite, reciprocal, and multiple proportions. Chapter 8. Theory of definite, reciprocal, and multiple proportions. Sect 1. Prelude to the atomic theory, and its publication by Dalton. The general laws of chemical combination announced by Mr. Dalton are truths of the highest importance in the science, and are now nowhere contested. But the view of matter as constituted of atoms, which he has employed in conveying those laws, and in expressing his opinion of their cause, is neither so important nor so certain. In the place which I here assign to his discovery, as one of the great events of the history of chemistry, I speak only of the law of phenomena, the rules which govern the quantities in which elements combine. This law may be considered as consisting of three parts, according to the above description of it: that elements combine in definite proportions, that these determining proportions operate reciprocally, and that when, between the same elements, several combining proportions occur, they are related as multiples. That elements combine in certain definite proportions of quantity, and in no other, was implied as soon as it was supposed that chemical compounds had any definite properties. Those who first attempted to establish regular formulae for the constitution of salts, minerals, and 286 other compounds assumed, as the basis of this process, that the elements in different specimens had the same proportion. Wenzel, in 1777, published his Lehre von der Verwandtschaft der Körper, or Doctrine of the Affinities of Bodies, in which he gave many good and accurate analyses. His work, it is said, never grew into general notice. Berthollet, as we have already stated, maintained that chemical compounds were not definite, but this controversy took place at a later period. It ended in the establishment of the doctrine that there is, for each combination, only one proportion of the elements, or at most only 2 or 3. Not only did Wenzel, by his very attempt, presume the first law of chemical composition, the definiteness of the proportions, but he was also led by his results to the second rule that they are reciprocal. For he found that when two neutral salts decompose each other, the resulting salts are also neutral. The neutral character of the salts shows that they are definite compounds, and when the two elements of the one salt, P and S, are presented to those of the other, B and N, if P be in such quantity as to combine definitely with N, B will also combine definitely with S. Note 45/14. I am told that Wenzel, whose book one have not seen, though he adduces many cases in which double decomposition gives neutral salts, does not express the proposition in a general form nor use letters in expressing it. Views similar to those of Wenzel were also published by Jeremiah Benjamin Richter in 1792 in his Anfangsgrund der Stoichiometrie oder Messkunst chemischer Element. Principles of the measure of chemical elements, in which he took the law, just stated, of reciprocal proportions as the basis of his researches, and determined the numerical quantities of the common bases and acids which would saturate each other. It is clear that, by these steps, the two first of our 3 rules may be considered as fully developed. The change of general views which was at this time going on probably prevented chemists from feeling so much interest as they might have done otherwise in these details. The French and English chemists, in particular, were fully employed with their own researches and controversies. Thus the rules which had already been published by Wenzel and Richter had attracted so little notice that we can hardly consider Mr. Dalton as having been anticipated by those writers. When, in 1803, he began to communicate his views on the chemical constitution of 287 bodies. These views being such as to include both these 2 rules in their most general form, and further, the rule, at that time still more new to chemists, of multiple proportions. He conceived bodies as composed of atoms of their constituent elements, grouped, either 1 and 1, or 1 and 2, or 1 and 3, and so on. Thus, if C represent an atom of carbon and O one of oxygen, OC will be an atom of carbonic oxide, and OCO an atom of carbonic acid. And hence it follows that while both these bodies have a definite quantity of oxygen to a given quantity of carbon, in the latter substance this quantity is double of what it is in the former. The consideration of bodies as consisting of compound atoms, each of these being composed of elementary atoms, naturally led to this law of multiple proportions. In this mode of viewing bodies, Mr. Dalton had been preceded, unknown to himself, by Mr. Higgins, who, in 1789, published his comparative view of the phlogistic and antiphlogistic theories. He there says that in volatile vitriolic acid, a single ultimate particle of sulfur is united only to a single particle of dephlogisticated air, and that in perfect vitriolic acid, every single particle of sulfur is united to 2 of dephlogisticated air, being the quantity necessary to saturation. And he reasons in the same manner concerning the constitution of water and the compounds of nitrogen and oxygen. These observations of Higgins were, however, made casually and not followed out, and cannot affect Dalton's claim to original merit. Mr. Dalton's generalization was first suggested during his examination of olefiant gas and carburetted hydrogen gas, and was asserted generally on the strength of a few facts, being, as it were, irresistibly recommended by the clearness and simplicity which the notion possessed. Mr. Dalton himself represented the compound atoms of bodies by symbols, which profess to exhibit the arrangement of the elementary atoms in space as well as their numerical proportion, and he attached great importance to this part of his scheme. It is clear, however, that this part of his doctrine is not essential to that numerical comparison of the law with facts, on which its establishment rests. These hypothetical configurations of atoms have no value till they are confirmed by corresponding facts, such as the optical or crystalline properties of bodies may perhaps one day furnish. 288. Sect 2. Reception and confirmation of the atomic theory. In order to give a sketch of the progress of the atomic theory into general reception, we cannot do better than borrow our information mainly from Dr. Thomson, who was one of the earliest converts and most effective promulgators of the doctrine. Mr. Dalton, at the time when he conceived his theory, was a teacher of mathematics at Manchester, in circumstances which might have been considered narrow, if he himself had been less simple in his manner of life, and less moderate in his worldly views. His experiments were generally made with apparatus of which the simplicity and cheapness corresponded to the rest of his habits. In 1804, he was already in possession of his atomic theory, and explained it to Dr. Thomson, who visited him at that time. It was made known to the chemical world in Dr. Thomson's chemistry in 1807, and in Dalton's own system of chemistry, 1808, the leading ideas of it were very briefly stated. Dr. Wollaston's memoir, On Superacid and Subacid Salts, which appeared in the Philosophical Transactions for 1808, did much to secure this theory a place in the estimation of chemists. Here the author states that he had observed, in various salts, the quantities of acid combined with the base in the neutral and in the superacid salts to be as 1 to 2. And he says that, thinking it likely this law might obtain generally in such compounds, it was his design to have pursued this subject, with the hope of discovering the cause to which so regular a relation may be ascribed. But he adds that this appears to be superfluous after the publication of Dalton's theory by Dr. Thomson, since all such facts are but special cases of the general law. We cannot but remark here that the scrupulous timidity of Wollaston was probably the only impediment to his anticipating Dalton in the publication of the rule of multiple proportions, and the forwardness to generalize, which belongs to the character of the latter, justly secured him, in this instance, the name of the discoverer of this law. The rest of the English chemists soon followed Wollaston and Thomson, though Davy for some time resisted. They objected, indeed, to Dalton's assumption of atoms, and to avoid this hypothetical step, Wollaston used the phrase chemical equivalents, and Davy the word proportions, for the numbers which expressed Dalton's atomic weights. We may, however, venture to say that the term atom is the most convenient, and it need not be understood as claiming our assent to the hypothesis of indivisible molecules. 289. As Wollaston and Dalton were thus arriving independently at the same result in England, other chemists in other countries were, unknown to each other, traveling towards the same point. In 1807, Berzelius, intending to publish a system of chemistry, went through several works little read, and among others the treatises of Richter. He was astonished, he tells us, at the light which was there thrown upon composition and decomposition, and which had never been turned to profit. He was led to a long train of experimental research, and when he received information of Dalton's ideas concerning multiple proportions, he found, in his own collection of analyses, a full confirmation of this theory. Some of the Germans, indeed, appear discontented with the partition of reputation which has taken place with respect to the theory of definite proportions. One of them says, Dalton has only done this, he has wrapped up the good Richter, whom he knew. Compare Schwager, T. Older Series, Volume X, p. 381. In a ragged suit, patched together of atoms, and now poor Richter comes back to his own country in such a garb, like Ulysses, and is not recognized. It is to be recollected, however, that Richter says nothing of multiple proportions. The general doctrine of the atomic theory is now firmly established over the whole of the chemical world. There remain still several controverted points, as, for instance, whether the atomic weights of all elements are exact multiples of the atomic weight of hydrogen. Dr. Prout advanced several instances in which this appeared to be true, and Dr. Thomson has asserted the law to be of universal application. But on the other hand, Berzelius and Dr. Turner declare that this hypothesis is at variance with the results of the best analyses. Such controverted points do not belong to our history, which treats only of the progress of scientific truths already recognized by all competent judges. Though Dalton's discovery was soon generally employed and universally spoken of with admiration, it did not bring to him anything but barren praise, and he continued in the humble employment of which we have spoken, when his fame had filled Europe, and his name become a household word in the laboratory. After some years, he was appointed a corresponding member of the Institute of France, which may be considered as a European recognition of the importance, 290, of what he had done. And, in 1826, 2 medals for the encouragement of science having been placed at the disposal of the Royal Society by the King of England, one of them was assigned to Dalton, for his development of the atomic theory. In 1833, at the meeting of the British Association for the Advancement of Science, which was held in Cambridge, it was announced that the king had bestowed upon him a pension of 150L. At the preceding meeting at Oxford, that university had conferred upon him the degree of Doctor of Laws, a step the more remarkable since he belonged to the sect of Quakers. At all the meetings of the British Association, he has been present, and has always been surrounded by the reverence and admiration of all who feel any sympathy with the progress of science. May he long remain among us thus to remind us of the vast advance which chemistry owes to him. Soon after I wrote these expressions of hope, the period of Dalton's sojourn among us terminated. He died on the 27th of July, 1844, aged 78. His fellow townsmen, the inhabitants of Manchester, who had so long taken a pride in his residence among them, soon after his death came to a determination to perpetuate his memory by establishing in his honor a professor of chemistry at Manchester. Sect 3. The theory of volumes, Gay-Lussac. The atomic theory, at the very epoch of its introduction into France, received a modification in virtue of a curious discovery then made. Soon after the publication of Dalton's system, Gay-Lussac and Humboldt found a rule for the combination of substances, which includes that of Dalton as far as it goes, but extends to combinations of gases only. This law is the theory of volumes, namely, that gases unite together by volume in very simple and definite proportions. Thus, water is composed exactly of 100 measures of oxygen and 200 measures of hydrogen. And since these simple ratios 1 and 1, 1 and 2, 1 and 3, alone prevail in such combinations, it may easily be shown that laws like Dalton's law of multiple proportions must obtain in such cases as he considered. M. Schroeder of Mannheim has endeavored to extend to solids a law in some degree resembling Gay-Lussac's law of the volumes of gases. According to him, the volumes of the chemical equivalents, 291, of simple substances and their compounds are as whole numbers. Mkop, Playfair, and Joule have labored in the same field. Note 52/14. Die molecular Volume der chemischen Verbindungen in festen und flüssigen Zustand, 1843. I cannot now attempt to trace other bearings and developments of this remarkable discovery. I hasten on to the last generalization of chemistry, which presents to us chemical forces under a new aspect, and brings us back to the point from which we departed in commencing the history of this science. Chapter 9. Epoch of Davy and Faraday. Sect 1. Promulgation of the electrochemical theory by Davy. The reader will recollect that the history of chemistry, though highly important and instructive in itself, has been an interruption of the history of electrodynamic research. A necessary interruption, however, for till we became acquainted with chemistry in general, we could not follow the course of electrochemistry. We could not estimate its vast yet philosophical theories, nor even express its simplest facts. We have now to endeavor to show what has thus been done, and by what steps, to give a fitting view of the epoch of Davy and Faraday. This is, doubtless, a task of difficulty and delicacy. We cannot execute it at all, except we suppose that the great truths, of which the discovery marks this epoch, have already assumed their definite and permanent form. For we do not learn the just value and right place of imperfect attempts and partial advances in science, except by seeing to what they lead. We judge properly of our trials and guesses only when we have gained our point and guessed rightly. We might personify philosophical theories, and might represent them to ourselves as figures, all pressing eagerly onwards in the same 292 direction, whom we have to pursue. And it is only in proportion as we ourselves overtake those figures in the race and pass beyond them that we are enabled to look back upon their faces, to discern their real aspects, and to catch the true character of their countenances. Except, therefore, I were of opinion that the great truths which Davy brought into sight have been firmly established and clearly developed by Faraday, I could not pretend to give the history of this striking portion of science. But I trust, by the view I have to offer of these beautiful trains of research and their result, to justify the assumption on which I thus proceed. I must, however, state, as a further appeal to the reader's indulgence, that, even if the great principles of electrochemistry have now been brought out in their due form and extent, the discovery is but a very few years, I might rather say a few months, old, and that this novelty adds materially to the difficulty of estimating previous attempts from the point of view to which we are thus led. It is only slowly and by degrees that the mind becomes sufficiently imbued with those new truths, of which the office is to change the face of a science. We have to consider familiar appearances under a new aspect, to refer old facts to new principles, and it is not till after some time that the struggle and hesitation which this employment occasions subsides into a tranquil equilibrium. In the newly acquired provinces of man's intellectual empire, the din and confusion of conquest pass only gradually into quiet and security. We have seen, in the history of all capital discoveries, how hardly they have made their way, even among the most intelligent and candid philosophers of the antecedent schools. We must, therefore, not expect that the metamorphosis of the theoretical views of chemistry which is now going on will be effected without some trouble and delay. I shall endeavor to diminish the difficulties of my undertaking by presenting the earlier investigations in the department of which I have now to speak, as much as possible according to the most deliberate view taken of them by the great discoverers themselves, Davy and Faraday, since these philosophers are they who have taught us the true import of such investigations. There is a further difficulty in my task, to which I might refer, the difficulty of speaking, without error and without offense, of men now alive, or who were lately members of social circles which exist still around us. But the scientific history in which such persons play a part is so important to my purpose that I do not hesitate to incur 293, the responsibility which the narration involves. And I have endeavored earnestly, and I hope not in vain, to speak as if I were removed by centuries from the personages of my story. The phenomena observed in the voltaic apparatus were naturally the subject of many speculations as to their cause, and thus gave rise to theories of the pile. Among these phenomena, there was one class which led to most important results. It was discovered by Nicholson and Carlisle in 1800 that water was decomposed by the pile of Volta. That is, it was found that when the wires of the pile were placed with their ends near each other in the fluid, a stream of bubbles of air arose from each wire, and these airs were found on examination to be oxygen and hydrogen, which, as we have had to narrate, had already been found to be the constituents of water. This was, as Davy says, the true origin of all that has been done in electrochemical science. It was found that other substances also suffered a like decomposition under the same circumstances. Certain metallic solutions were decomposed, and an alkali was separated on the negative plates of the apparatus. Cruikshank, in pursuing these experiments, added to them many important new results, such as the decomposition of muriates of magnesia, soda, and ammonia by the pile, and the general observation that the alkaline matter always appeared at the negative and the acid at the positive pole. Such was the state of the subject when one who was destined to do so much for its advance first contributed his labors to it. Humphrey Davy was a young man who had been apprenticed to a surgeon at Penzance, and having shown an ardent love and a strong aptitude for chemical research, was, in 1798, made the superintendent of a pneumatic institution, established at Bristol by Dr. Beddoes, for the purpose of discovering medical powers of factitious airs. But his main attention was soon drawn to galvanism, and when, in consequence of the reputation he had acquired, he was, in 1801, appointed lecturer at the Royal Institution in London, then recently established, He was soon put in possession of a galvanic apparatus of great power. And with this, he was not long in obtaining the most striking results. His first paper on the subject is sent from Bristol in September 1800 and describes experiments in which he had found that the decompositions observed by Nicholson and Carlisle go on, although the 294 water or other substance in which the two wires are plunged be separated into two portions, provided these portions are connected by muscular or other fibers. This use of muscular fibers was, probably, a remnant of the original disposition, or accident, by which galvanism had been connected with physiology as much as with chemistry. Davy, however, soon went on towards the conclusion that the phenomena were altogether chemical in their nature. He had already conjectured, in 1802, that all decompositions might be polar. That is, that in all cases of chemical decomposition, the elements might be related to each other as electrically positive and negative, a thought which it was the peculiar glory of his school to confirm and place in a distinct light. At this period, such a view was far from obvious, and it was contended by many, on the contrary, that the elements which the voltaic apparatus brought to view were not liberated from combinations, but generated. In 1806, Davy attempted the solution of this question. He showed that the ingredients which had been supposed to be produced by electricity were due to impurities in the water or to the decomposition of the vessel, and thus removed all preliminary difficulties. And then he says, referring to my experiments of 1800, 1801, and 1802, and to a number of new facts, which showed that inflammable substances and oxygen, alkalis and acids, and oxidable and noble metals were in electrical relations of positive and negative, I drew the conclusion that the combinations and decompositions by electricity were referable to the law of electrical attractions and repulsions, and advanced the hypothesis that chemical and electrical attractions were produced by the same cause, acting in the one case on particles, in the other on masses, and that the same property, under different modifications, was the cause of all the phenomena exhibited by different voltaic combinations. Although this is the enunciation, in tolerably precise terms, of the great discovery of his epoch, it was, at the period of which we speak, conjectured rather than proved, and we shall find that neither Davy nor his followers, for a considerable period, apprehended it with that distinctness which makes a discovery complete. But in a very short time afterwards, Davy drew great additional notice to his researches by effecting, in pursuance, as it appeared, of his theoretical views, the decomposition of potassa into a metallic base and oxygen. This was, as he truly said, in the memorandum written in his journal at the 295 instant, a capital experiment. This discovery was soon followed by that of the decomposition of soda, and shortly after, of other bodies of the same kind. And the interest and activity of the whole chemical world were turned to the subject in an intense degree. At this period, there might be noticed three great branches of speculation on this subject: the theory of the pile, the theory of electrical decomposition, and the theory of the identity of chemical and electrical forces, which last doctrine, however, was found to include the other two, as might have been anticipated from the time of its first suggestion. It will not be necessary to say much on the theories of the voltaic pile, as separate from other parts of the subject. The contact theory, which ascribed the action to the contact of different metals, was maintained by Volta himself, but gradually disappeared, as it was proved by Wollaston especially, that the effect of the pile was inseparably connected with oxidation or other chemical changes. The theories of electrochemical decomposition were numerous, and especially after the promulgation of Davy's memoir in 1806. And, whatever might be the defects under which these speculations for a long time labored, the subject was powerfully urged on in the direction in which truth lay by Davy's discoveries and views. That there remained something still to be done, in order to give full evidence and consistency to the theory, appears from this: that some of the most important parts of Davy's results struck his followers as extraordinary paradoxes. For instance, the fact that the decomposed elements are transferred from one part of the circuit to another, in a form which escapes the cognizance of our senses, through intervening substances for which they have a strong affinity. It was found afterwards that the circumstance which appeared to make the process so wonderful was, in fact, the condition of its going on at all. Davy's expressions often seem to indicate the most exact notions. For instance, he says, "It is very natural to suppose that the repellent and attractive energies are communicated from one particle to another of the same kind, so as to establish a conducting chain in the fluid, and that the locomotion takes place in consequence." And yet at other times he speaks of the element as attracted and repelled by the metallic surfaces which form the poles, a different, and, as it appeared afterwards, an untenable view. Mr. Faraday, who supplied what was wanting, justly notices this vagueness. 296, he says, that though in Davy's celebrated memoir of 1806, the points established are of the utmost value, the mode of action by which the effects take place is stated very generally. So generally, indeed, that probably a dozen precise schemes of electrochemical action might be drawn up, differing essentially from each other, yet all agreeing with the statement there given. And at a period, a little later, being reproached by Davy's brother with injustice in this expression, he substantiated his assertion by an enumeration of 12 such schemes which had been published. But yet we cannot look upon this memoir of 1806 otherwise than as a great event, perhaps the most important event of the epoch now under review. And as such it was recognized at once all over Europe. In particular, it received the distinguished honor of being crowned by the Institute of France, although that country and England were then engaged in fierce hostility. Buonaparte had proposed a prize of 60,000 francs to the person who by his experiments and discoveries should advance the knowledge of electricity and galvanism as much as Franklin and Volta did, and of 3,000 francs for the best experiment which should be made in the course of each year on the galvanic fluid. The latter prize was, by the first class of the Institute, awarded to Davy. From this period, he rose rapidly to honors and distinctions, and reached a height of scientific fame as great as has ever fallen to the lot of a discoverer in so short a time. I shall not, however, dwell on such circumstances, but confine myself to the progress of my subject. Sect 2. Establishment of the electrochemical theory by Faraday. The defects of Davy's theoretical views will be seen most clearly by explaining what Faraday added to them. Michael Faraday was in every way fitted and led to become Davy's successor in his great career of discovery. In 1812, being then a bookseller's apprentice, he attended the lectures of Davy, which at that period excited the highest admiration. "My desire to escape from trade," Mr. Faraday says, "which I thought vicious and selfish, and to enter into the service of science, which I imagined made its pursuers amiable and liberal, induced me at last to take the bold and simple step of writing to Sir H. Davy." He was favorably received, and in the next year became 297 Davy's assistant at the institution, and afterwards his successor. The institution which produced such researches as those of these two men may well be considered as a great school of exact and philosophical chemistry. Mr. Faraday, from the beginning of his course of inquiry, appears to have had the consciousness that he was engaged on a great connected work. His experimental researches, which appeared in a series of memoirs in the Philosophical Transactions, are divided into short paragraphs, numbered into a continued order from 1 up to 1160, at the time at which I write, and destined, probably, to extend much further. These paragraphs are connected by a very rigorous method of investigation and reasoning which runs through the whole body of them. Yet this unity of purpose was not at first obvious. His first two memoirs were upon subjects which we have already treated of B, Roman 13, C5 and C8, voltaic induction, and the evolution of electricity from magnetism. His third series has also been already referred to. Its object was, as a preparatory step towards further investigation, to show the identity of voltaic and animal electricity with that of the electrical machine. And as machine electricity differs from other kinds in being successively in a state of tension and explosion, instead of a continued current, Mr. Faraday succeeded in identifying it with them by causing the electrical discharge to pass through a bad conductor into a discharging train of vast extent. Nothing less, indeed, than the whole fabric of the metallic gas pipes and water pipes of London. In this memoir, it is easy to see already traces of the general theoretical views at which he had arrived, but these are not expressly stated till his fifth series, his intermediate fourth series being occupied by another subsidiary labor on the conditions of conduction. At length, however, in the fifth series, which was read to the Royal Society in June 1833, he approaches the theory of electrochemical decomposition. Most preceding theorists, and Davy amongst the number, had referred this result to attractive powers residing in the poles of the apparatus, and had even pretended to compare the intensity of this attraction at different distances from the poles. By a number of singularly beautiful and skillful experiments, Mr. Faraday shows that the phenomena can with no propriety be 298 ascribed to the attraction of the poles. As the substances evolved in cases of electrochemical decomposition may be made to appear against air, which according to common language is not a conductor, nor is decomposed, or against water, which is a conductor and can be decomposed, as well as against the metal poles, which are excellent conductors, but undecomposable. There appears but little reason to consider this phenomenon generally as due to the attraction or attractive powers of the latter, when used in the ordinary way, since similar attractions can hardly be imagined in the former instances. Note 62/14, December 1835. At present, when I am revising the second edition, September 1846, Dr. Faraday has recently published the 21st series of his researches ending with paragraph 2453. Faraday's opinion, and indeed the only way of expressing the results of his experiments, was that the chemical elements, in obedience to the direction of the voltaic currents established in the decomposing substance, were evolved, or, as he prefers to say, ejected at its extremities. He afterwards states that the influence which is present in the electric current may be described as an axis of power, having contrary forces exactly equal in amount in contrary directions. Having arrived at this point, Faraday rightly wished to reject the term poles, and other words which could hardly be used without suggesting doctrines now proved to be erroneous. He considered, in the case of bodies electrically decomposed, or, as he termed them, electrolytes, the elements as traveling in two opposite directions, which, with reference to the direction of terrestrial magnetism, might be considered as naturally east and west. And he conceived elements as, in this way, arriving at the doors or outlets at which they finally made their separate appearance. The doors he called electrodes, and, separately, the anode and the cathode, and the elements which thus travel he termed the anion and the cation or kathion. By means of this nomenclature, he was able to express his general results with much more distinctness and facility. Note 70/14. The analogy of the Greek derivation requires cation, but to make the relation to cathode obvious to the English reader, and to avoid a violation of the habits of English pronunciation, I should prefer kathion. But this general view of the electrolytical process required to be pursued further, in order to explain the nature of the action. The identity of electrical and chemical forces, which had been hazarded as 299, a conjecture by Davy, and adopted as the basis of chemistry by Berzelius, could only be established by exact measures and rigorous proofs. Faraday had, in his proof of the identity of voltaic and electric agency, attempted also to devise such a measure as should give him a comparison of their quantity. And in this way, he proved that a voltaic group of two small wires of platinum and zinc, placed near each other, and immersed in dilute acid for 3 seconds, yields as much electricity as the electrical battery, charged by 10 turns of a large machine. And this was established both by its momentary electromagnetic effect and by the amount of its chemical action. It was in his 7th series that he finally established a principle of definite measurement of the amount of electrolytical action, and described an instrument which he termed a voltelectrometer. In this instrument, the amount of action was measured by the quantity of water decomposed, and it was necessary, in order to give validity to the mensuration, to show, as Faraday did show, that neither the size of the electrodes, nor the intensity of the current, nor the strength of the acid solution which acted on the plates of the pile, disturbed the accuracy of this measure. He proved, by experiments upon a great variety of substances, of the most different kinds, that the electrochemical action is definite in amount according to the measurement of the new instrument. He had already, at an earlier period, asserted that the chemical power of a current of electricity is in direct proportion to the absolute quantity of electricity which passes. But the voltelectrometer enabled him to fix with more precision the meaning of this general proposition, as well as to place it beyond doubt. The vast importance of this step in chemistry soon came into view. By the use of the voltelectrometer, Faraday obtained, for each elementary substance, a number which represented the relative amount of its decomposition and which might properly be called its electrochemical equivalent. And the question naturally occurs whether these numbers bore any relation to any previously established chemical measures. The answer is remarkable. They were no other than the atomic weights of the Daltonian theory, which formed the climax of the previous ascent of chemistry. And thus here, as everywhere in 300, The Progress of Science, the generalizations of one generation are absorbed in the wider generalizations of the next. But in order to reach securely this wider generalization, Faraday combined the two branches of the subject which we have already noticed, the theory of electrical decomposition with the theory of the pile. For his researches on the origin of activity of the voltaic circuit, his 8th series, led him to see more clearly than anyone before him what, as we have said, the most sagacious of preceding philosophers had maintained, that the current in the pile was due to the mutual chemical action of its elements. He was led to consider the processes which go on in the exciting cell and in the decomposing place as of the same kind, but opposite in direction. The chemical composition of the fluid with the zinc in the common apparatus produces, when the circuit is completed, a current of electric influence in the wire. And this current, if it pass through an electrolyte, manifests itself by decomposition, overcoming the chemical affinity which there resists it. An electrolyte cannot conduct without being decomposed. The forces at the point of composition and the point of decomposition are of the same kind, and are opposed to each other by means of the conducting wire. The wire may properly be spoken of as conducting chemical affinity. It allows two forces of the same kind to oppose one another. Electricity is only another mode of the exertion of chemical forces. And we might express all the circumstances of the voltaic pile without using any other term than chemical affinity, though that of electricity may be very convenient. Bodies are held together by a definite power, which, when it ceases to discharge that office, may be thrown into the condition of an electric current. Thus, the great principle of the identity of electrical and chemical action was completely established. It was, as Faraday with great candor says, a confirmation of the general views put forth by Davy in 1806, and might be expressed in his terms that chemical and electrical attractions are produced by the same cause. But it is easy to see that neither was the full import of these expressions understood, nor were the quantities to which they refer conceived as measurable quantities, nor was the assertion anything but a sagacious conjecture, till Faraday gave the interpretation, measure, and proof of which we have spoken. The evidence of the incompleteness of the views of his predecessor we have already adduced in speaking of his vague and 301 inconsistent theoretical account of decomposition. The confirmation of Davy's discoveries by Faraday is of the nature of Newton's confirmation of the views of Borelli and Hooke respecting gravity, or like Young's confirmation of the undulatory theory of Huygens. We must not omit to repeat here the moral which we wish to draw from all great discoveries, that they depend upon the combination of exact facts with clear ideas. The former of these conditions is easily illustrated in the case of Davy and Faraday, both admirable and delicate experimenters. Davy's rapidity and resource in experimenting were extraordinary, and extreme elegance and ingenuity distinguish almost every process of Faraday. He had published, in 1829, a work on chemical manipulation, in which directions are given for performing in the neatest manner all chemical processes. Manipulation, as he there truly says, is to the chemist like the external senses to the mind. And without the supply of fit materials which such senses only can give, the mind can acquire no real knowledge. But still the operations of the mind, as well as the information of the senses, ideas as well as facts, are requisite for the attainment of any knowledge. And all great steps in science require a peculiar distinctness and vividness of thought in the discoverer. This it is difficult to exemplify in any better way than by the discoveries themselves. Both Davy and Faraday possessed this vividness of mind, and it was a consequence of this endowment that Davy's ** lectures upon chemistry and Faraday's upon almost any subject of physical philosophy were of the most brilliant and captivating character. In discovering the nature of voltaic action, the essential intellectual requisite was to have a distinct conception of that which Faraday expressed by the remarkable phrase, an axis of power having equal and opposite forces, and the distinctness of this idea in Faraday's mind shines forth in every part of his writings. Thus he says, the force which determines the decomposition of a body is in the body, not in the poles. But for the most part, he can of course only convey this fundamental idea by illustrations. Thus he represents the voltaic circuit by a double circle, studded with the elements of the circuit, and shows how the anions travel round it in one direction and the cathions in the opposite. He considers the powers at the two places of action as balancing against each other through the medium of the conductors, in a manner 302 analogous to that in which mechanical forces are balanced against each other by the intervention of the lever. It is impossible to him to resist the idea that the voltaic current must be preceded by a state of tension in its interrupted condition, which is relieved when the circuit is completed. He appears to possess the idea of this kind of force with the same eminent distinctness with which Archimedes in the ancient and Stevinus in the modern history of science possessed the idea of pressure, and were thus able to found the science of mechanics. And when he cannot obtain these distinct modes of conception, he is dissatisfied and conscious of defect. Thus, in the relation between magnetism and electricity, there appears to be a link in the chain of effects, a wheel in the physical mechanism of the action, as yet unrecognized. All this variety of expression shows how deeply seated is the thought. This conception of chemical affinity as a peculiar influence of force, which, acting in opposite directions, combines and resolves bodies, which may be liberated and thrown into the form of a voltaic current, and thus be transferred to remote points and applied in various ways, is essential to the understanding, as it was to the making, of these discoveries. By those to whom this conception has been conveyed, I venture to trust that I shall be held to have given a faithful account of this important event in the history of science. We may, before we quit the subject, notice one or two of the remarkable subordinate features of Faraday's discoveries. Sect 3 Consequences of Faraday's discoveries. Faraday's voltelectrometer, in conjunction with the method he had already employed, as we have seen, for the comparison of voltaic and common electricity, enabled him to measure the actual quantity of electricity which is exhibited, in given cases, in the form of chemical affinity. His results appeared in numbers of that enormous amount which so often comes before us in the expression of natural laws. 1 grain of water will require for its decomposition as much electricity as would make a powerful flash of lightning. By further calculation, he finds this quantity to be not less than 800,000 charges of his laden battery. And this is, by his theory of the identity of the combining with the decomposing force, the quantity of electricity, 303, which is naturally associated with the elements of the grain of water, endowing them with their mutual affinity. Many of the subordinate facts and laws which were brought to light by these researches clearly point to generalizations not included in that which we have had to consider and not yet discovered. Such laws do not properly belong to our main plan, which is to make our way up to the generalizations. But there is one which so evidently promises to have an important bearing on future chemical theories that I will briefly mention it. The class of bodies which are capable of electrical decomposition is limited by a very remarkable law. They are such binary compounds only as consist of single proportionals of their elementary principles. It does not belong to us here to speculate on the possible import of this curious law, which, if not fully established, Faraday has rendered, at least, highly probable. But it is impossible not to see how closely it connects the atomic with the electrochemical theory, and in the connection of these two great members of chemistry, is involved the prospect of its reaching wider generalizations and principles more profound than we have yet caught sight of. As another example of this connection, I will, finally, notice that Faraday has employed his discoveries in order to decide, in some doubtful cases, what is the true chemical equivalent. I have such conviction, he says, that the power which governs electrodecomposition and ordinary chemical attractions is the same, and such confidence in the overruling influence of those natural laws which render the former definite, as to feel no hesitation in believing that the latter must submit to them too. Such being the case, I can have no doubt that, assuming hydrogen as one and dismissing small fractions for the simplicity of expression, the equivalent number or atomic weight of oxygen is 8, of chlorine 36, of bromine 78.4, of lead 103.5, of tin 59, and C, notwithstanding that a very high authority doubles several of these numbers. Sect 4. Reception of the electrochemical theory. The epoch of establishment of the electrochemical theory, like other great scientific epochs, must have its sequel, the period of its reception and confirmation, application and extension. In that period, we 304 are living, and it must be the task of future historians to trace its course. We may, however, say a word on the reception which the theory met with, in the forms which it assumed, anterior to the labors of Faraday. Even before the great discovery of Davy, Grot thus, in 1805, had written upon the theory of electrochemical decomposition. But he and, as we have seen, Davy and afterwards other writers, as Rifault and Champré in 1807, referred the effects to the poles. But the most important attempt to appropriate and employ the generalization which these discoveries suggested was that of Berzelius, who adopted at once the view of the identity, or at least the universal connection, of electrical relations with chemical affinity. He considered that in all chemical combinations the elements may be considered as electropositive and electronegative, and made this opposition the basis of his chemical doctrines, in which he was followed by a large body of the chemists of Germany. He held too that the heat and light, evolved during cases of powerful combination, are the consequence of the electric discharge which is at that moment taking place, a conjecture which Faraday at first spoke of with praise. But at a later period, he more sagely says that the flame which is produced in such cases exhibits but a small portion of the electric power which really acts. These therefore cannot, be taken as evidences of the nature of the action, but are merely incidental results, incomparably small in relation to the forces concerned, and supplying no information of the way in which the particles are active on each other, or in which their forces are finally arranged. And comparing the evidence which he himself had given of the principle on which Berzelius's speculations rested, with the speculations themselves, Faraday justly conceived that he had transferred the doctrine from the domain of what he calls doubtful knowledge to that of inductive certainty. Now that we are arrived at the starting place, from which this well-proved truth, the identity of electric and chemical forces, must make its future advances, it would be trifling to dwell longer on the details of the diffusion of that doubtful knowledge which preceded this more certain science. Our history of chemistry is, therefore, here at an end. I have, as far as I could, executed my task, which was to mark all the 305 great steps of its advance, from the most unconnected facts and the most imperfect speculations to the highest generalization at which chemical philosophers have yet arrived. Yet it will appear to our purpose to say a few words on the connection of this science with those of which we are next to treat, and that I now proceed to do. Chapter 10. Transition from the chemical to the classificatory sciences. It is the object and the boast of chemistry to acquire a knowledge of bodies, which is more exact and constant than any knowledge borrowed from their sensible qualities can be, since it penetrates into their intimate constitution and discloses to us the invariable laws of their composition. But yet it will be seen, on a little reflection, that such knowledge could not have any existence if we were not also attentive to their sensible qualities. The whole fabric of chemistry rests, even at the present day, upon the opposition of acids and bases. An acid was certainly at first known by its sensible qualities, and how otherwise, even now, do we perceive its quality? It was a great discovery of modern times that earths and alkalis have for their bases metals. But what are metals? Or how, except from luster, hardness, weight, and the like, do we recognize a body as a metal? And how, except by such characters, even before its analysis, was it known to be an earth or an alkali? We must suppose some classification established before we can make any advance by experiment or observation. It is easy to see that all attempts to avoid this difficulty by referring to processes and analogies, as well as to substances, bring us back to the same point in a circle of fallacies. If we say that an acid and alkali are known by combining with each other, we still must ask, what is the criterion that they have combined? If we say that the distinctive qualities of metals and earths are that metals become earths by oxidation, we must still inquire how we recognize the process of oxidation. We have seen how important a part combustion plays in the history of chemical speculation, and we may usefully form such classes of 306 bodies as combustibles and supporters of combustion. But even combustion is not capable of being infallibly known, for it passes by insensible shades into oxidation. We can find no basis for our reasonings, which does not assume a classification of obvious facts and qualities. But any classification of substances on such grounds appears, at first sight, to involve us in vagueness, ambiguity, and contradiction. Do we really take the sensible qualities of an acid as the criterion of its being an acid? For instance, its sourness, prussic acid, arsenious acid, are not sour. I remember, says Dr. Paris, a chemist having been exposed to much ridicule from speaking of a sweet acid. Why not? When Davy had discovered potassium, it was disputed whether it was a metal, for though its luster and texture are metallic, it is so light as to swim on water. And if potassium be allowed to be a metal, is silicium one, a body which wants the metallic luster, and is a non-conductor of electricity? It is clear that, at least, the obvious application of a classification by physical characters is attended with endless perplexity. But since we cannot even begin our researches without assuming a classification, and since the forms of such a classification which first occur end in apparent confusion, it is clear that we must look to our philosophy for a solution of this difficulty, and must avoid the embarrassments and contradictions of casual and unreflective classification by obtaining a consistent and philosophical arrangement. We must employ external characters and analogies in a connected and systematic manner. We must have classificatory sciences, and these must have a bearing even on chemistry. Accordingly, the most philosophical chemists now proceed upon this principle. The method which I have followed, says M. Thenard in his Traité de Chimie, published in 1824, is to unite in one group all analogous bodies, and the advantage of this method, which is that employed by naturalists, is very great, especially in the study of the metals and their compounds. In this, as in all good systems of chemistry, which have appeared since the establishment of the phlogistic theory, combustion, and the analogous processes are one great element in the arrangement, while the difference of metallic and non-metallic is another element. Thus Thenard in the first place speaks of oxygen, in the next place of the non-metallic combustibles as hydrogen, carbon, sulfur, chlorine, and in the next place of metals. But the metals are again divided into 6 sections, with reference 307 principally to their facility of combination with oxygen. Thus, the first section is the metals of the earths, the second, the metals of the alkalis, the third, the easily oxidable metals, as iron, the fourth, metals less oxidable, as copper and lead. The fifth section contains only mercury and osmium, and the sixth, what were at an earlier period termed the noble metals, gold, silver, platinum, and others. How such principles are to be applied, so as to produce a definite and consistent arrangement, will be explained in speaking of the philosophy of the classificatory sciences. But there are 1 or 2 peculiarities in the classes of bodies thus recognized by modern chemistry, which it may be useful to notice. 1. The distinction of metallic and non-metallic is still employed as of fundamental importance. The discovery of new metals is so much connected with the inquiries concerning chemical elements that we may notice the general progress of such discoveries. Gold, silver, iron, copper, quicksilver, lead, tin were known from the earliest antiquity. In the beginning of the 16th century, mine directors, like George Agricola, had advanced so far in practical metallurgy that they had discovered the means of extracting 3 additional metals, zinc, bismuth, antimony. After this, there was no new metal discovered for a century. And then such discoveries were made by the theoretical chemists, a race of men who had not existed before Becher and Stahl. Thus arsenic and cobalt were made known by Brandt in the middle of the 18th century, and we have a long list of similar discoveries belonging to the same period. Nickel, manganese, and tungsten, which were detected by Cronstedt, Gahn and Scheele and Delhairt, respectively. Metals of a very different kind, tellurium and molybdenum, which were brought to light by Muller, Scheele, Bergman, and Helm. Platinum, which was known as early as 1741. But with the ore of which, in 1802 and 1803, the English chemists Wollaston and Tennant found that no less than 4 other new metals, palladium, rhodium, iridium, and osmium, were associated. Finally, omitting some other new metals, we have another period of discovery, opened in 1807 by Davy's discovery of potassium, and including the resolution of all, or almost all, the alkalis and earths into metallic bases. The next few years made at least some conjectural additions to the list of simple substances, detected by a more minute scrutiny of known substances. Thorium was discovered by Berzelius in 1828, and vanadium by Professor Sefstrom in 1830. A308, metal named cerium, was discovered in 1803 by Hisinger and Berzelius in a rare Swedish mineral known by the name of cerit. Mosander more recently has found combined with cerium other new metals which he has called lanthanium, didymium, erbium, and terbium. M. Claus has found a new metal, ruthenium, in the ore of platinum, and Rose has discovered in tantalite 2 other new metals, which he has announced under the names of pelopium and niobium. Svanberg is said to have discovered a new earth in eudialit, which is supposed to have, like the rest, a new radical. If these last discoveries be confirmed, the number of simple substances will be raised to 62. 2 attempts have been made to indicate the classification of chemical substances by some peculiarity in the name, and the metals, for example, have been designated generally by names in like the Latin names of the ancient metals, aurum, ferrum. This artifice is a convenient nomenclature for the purpose of marking a recognized difference, and it would be worth the while of chemists to agree to make it universal by writing molybden and platin which is sometimes done, but not always. 3. I am not now to attempt to determine how far this class, metals, extends, but where the analogies of the class cease to hold there, the nomenclature must also change. Thus, some chemists, as Dr. Thomson, have conceived that the base of silica is more analogous to carbon and boron, which form acids with oxygen, than it is to the metals, and he has accordingly associated this base with these substances and has given it the same termination, silicon. But on the validity of this analogy chemists appear not to be generally agreed. 4. There is another class of bodies which have attracted much notice among modern chemists, and which have also been assimilated to each other in the form of their names, the English writers calling them chlorine, fluorine, iodine, bromine, while the French use the terms chlora, pH-tor, iode, brome. We have already noticed the establishment of the doctrine that muriatic acid is formed of a base, chlorine, and of hydrogen as a great reform in the oxygen theory, with regard to which rival claims were advanced by Davy and Beim, Gay-Lussac and Thenard in 1800. Iodine, a remarkable body which, from a dark powder, is converted into a violet-colored gas by the application of heat, was also, in 1813, the subject of a similar rivalry between the same English and French chemists. Bromine, 309, was only discovered as late as 1826, and fluorine, or pH-tor, as, from its destructive nature, it has been proposed to term it, has not been obtained as a separate substance, and is inferred to exist by analogy only. The analogies of these bodies, chlora, pH-tor, and C, are very peculiar. For instance, by combination with metals they form salts. By combination with hydrogen they form very strong acids, and all, at the common temperature of the atmosphere, operate on other bodies in the most energetic manner. Berzelius proposes to call them halogenous bodies or halogens. The number of elementary substances which are at present presented in our treatises of chemistry is 53, or rather, as we have said above, 62. It is naturally often asked what evidence we have that all these are elementary, and what evidence that they are all the elementary bodies. How we know that new elements may not hereafter be discovered, or these supposed simple bodies resolved into simpler still. To these questions we can only answer by referring to the history of chemistry, by pointing out what chemists have understood by analysis, according to the preceding narrative. They have considered, as the analysis of a substance, that elementary constitution of it which gives the only intelligible explanation of the results of chemical manipulation, and which is proved to be complete as to quantity, by the balance, since the whole can only be equal to all its parts. It is impossible to maintain that new substances may not hereafter be discovered, for they may lurk, even in familiar substances, in doses so minute that they have not yet been missed amid the inevitable slight inaccuracies of all analysis, in the way in which iodine and bromine remained so long undetected in seawater. And new minerals, or old ones not yet sufficiently examined, can hardly fail to add something to our list. As to the possibility of a further analysis of our supposed simple bodies, we may venture to say that, in regard to such supposed simple bodies as compose a numerous and well-characterized class, no such step can be made, except through some great change in chemical theory, which gives us a new view of all the general relations which chemistry has yet discovered. The proper evidence of the reality of any supposed new analysis is that it is more consistent with the known analogies of chemistry to suppose the process analytical than synthetical. Thus, as has already been said, chemists admit the existence of fluorine from the analogy of chlorine. And Davy, when it was found, 310, that ammonia formed an amalgam with mercury, was tempted to assign to it a metallic basis. But then he again hesitates, and doubts whether the analogies of our knowledge are not better preserved by supposing that ammonia, as a compound of hydrogen and another principle, is a type of the composition of the metals. Our history, which is the history of what we know, has little to do with such conjectures. There are, however, some not unimportant principles which bear upon them, and which, as they are usually employed, belong to the science which next comes under our review, mineralogy. 311, Book 15. The Analytico-Classificatory Science. History of Mineralogy. Kappa rho upsilon sigma tau alpha lambda lambda omicron u, phi alpha epsilon theta omicron u tau alpha, delta iota alpha upsilon gamma epsilon alpha, lambda alpha zeta epsilon omicron, chi, epsilon rho sigma letter 1f7 6. Lambda letter 1f b6, alpha nu letter 1f00. Pi omicron letter 1fe4, letter 1fe5 omicron, iota alpha nu pi epsilon rho ot phi epsilon gamma gamma epsilon omicron sigma, letter 1f00 mu beta rho omicron tau omicron upsilon, alpha letter 1f34, gamma lambda eta sigma. Alpha letter 1f30, theta epsilon, rho iota delta, letter 1f00 theta alpha nu alpha tau omega nu, mu epsilon gamma alpha, tau epsilon rho pi epsilon tau alpha iota, letter 1f04 phi theta iota tau omicron nu, letter 1f26 tau omicron rho. Tau omicron u, kappa epsilon letter 1f34, pi epsilon rho mu, epsilon tau, letter 1f70, chi epsilon iota rho letter 1f70, sigma letter 1f14 chi omega nu. Pi epsilon rho letter 1f76, nu eta letter 1f78, nu letter 1f35 kappa eta alpha iota. Omicron letter 1f54, tau iota sigma tau omicron iota, mu alpha kappa alpha rho omega nu, letter 1f00 rho nu eta sigma epsilon tau alpha iota, epsilon letter 1f50, chi omega lambda letter 1f c6, sigma iota, Orpheus. Lithica. Now, if the bold but pious thought be thine, to reach our spacious temple's inner shrine take in thy reverent hands the crystal stone, where heavenly light in earthy shroud is shown. Where, molded into measured form, with rays complex yet clear, the eternal ether plays. This if thou firmly hold and rightly use, not long the gods thy ardent wish refuse. 313, Introduction. Sect, one of the classificatory sciences. The horizon of the sciences spreads wider and wider before us, as we advance in our task of taking a survey of the vast domain. We have seen that the existence of chemistry, as a science which declares the ingredients and essential constitution of all kinds of bodies, implies the existence of another corresponding science, which shall divide bodies into kinds and point out steadily and precisely what bodies they are which we have analyzed. But a science thus dividing and defining bodies is but one member of an order of sciences different from those which we have hitherto described, namely, of the classificatory sciences. Such sciences there must be, not only having reference to the bodies with which chemistry deals, but also to all things respecting which we aspire to obtain any general knowledge, as, for instance, plants and animals. Indeed, it will be found that it is with regard to these latter objects, to organized beings, that the process of scientific classification has been most successfully exercised, while with regard to inorganic substances, the formation of a satisfactory system of arrangement has been found extremely difficult, nor has the necessity of such a system been recognized by chemists so distinctly and constantly as it ought to be. The best exemplification of these branches of knowledge, of which we now have to speak, will, therefore, be found in the organic world, in botany and zoology. But we will, in the first place, take a brief view of the science which classifies inorganic bodies, and of which mineralogy is hitherto the very imperfect representative. The principles and rules of the classificatory sciences, as well as of those of the other orders of sciences, must be fully explained when we come to treat of the philosophy of the sciences, and cannot be introduced here, where we have to do with history only. But I may observe very briefly that with the process of classing is joined the process of naming, that names imply classification, and that even the rudest and earliest application of language presupposes a distribution of objects according to their kinds, but that such a spontaneous, 314, and unsystematic distribution cannot, in the cases we now have to consider, answer the purposes of exact and general knowledge. Our classification of objects must be made consistent and systematic in order to be scientific. We must discover marks and characters, properties and conditions which are constant in their occurrence and relations. We must form our classes, we must impose our names according to such marks. We can thus, and thus alone, arrive at that precise, certain, and systematic knowledge which we seek, that is, at science. The object, then, of the classificatory sciences is to obtain fixed characters of the kinds of things, and the criterion of the fitness of names is that they make general propositions possible. I proceed to review the progress of certain sciences on these principles, and first, though briefly, the science of mineralogy. Sect 2. Mineralogy as the analytico-classificatory science. Mineralogy, as it has hitherto been cultivated, is, as I have already said, an imperfect representative of the department of human knowledge to which it belongs. The attempts at the science have generally been made by collecting various kinds of information respecting mineral bodies, but the science which we require is a complete and consistent classified system of all inorganic bodies. For chemistry proceeds upon the principle that the constitution of a body invariably determines its properties, and, consequently, its kind. But we cannot apply this principle, except we can speak with precision of the kind of a body, as well as of its composition. We cannot attach any sense to the assertion that soda or baryta has a metal for its base, except we know what a metal is, or at least what properties it implies. It may not be, indeed it is not, possible to define the kinds of bodies by words only, but the classification must proceed by some constant and generally applicable process, and the knowledge which has reference to the classification will be precise as far as this process is precise, and vague as far as this is vague. There must be, then, as a necessary supplement to chemistry, a science of those properties of bodies by which we divide them into kinds. Mineralogy is the branch of knowledge which has discharged the office of such a science, so far as it has been discharged, and, indeed, mineralogy has been gradually approaching to a clear consciousness of her real place and of her whole task. I shall give the history of some of the advances which have thus been made. They are, principally, 315, the establishment and use of external characters, especially of crystalline form, as a fixed character of definite substances, and the attempts to bring into view the connection of chemical constitution and external properties made in the shape of mineralogical systems, both those in which chemical methods of arrangement are adopted and those which profess to classify by the natural history method. 316. Crystallography. Chapter 1. Prelude to the Epic of Delisle and Howey. Of all the physical properties of bodies, there is none so fixed, and in every way so remarkable as this, that the same chemical compound always assumes, with the utmost precision, the same geometrical form. This identity, however, is not immediately obvious. It is often obscured by various mixtures and imperfections in the substance, and even when it is complete, it is not immediately recognized by a common eye, since it consists not in the equality of the sides or faces of the figures, but in the equality of their angles. Hence, it is not surprising that the constancy of form was not detected by the early observers. Pliny says, "Why crystal is generated in a hexagonal form, it is difficult to assign a reason, and the more so since, while its faces are smoother than any art can make them, the pyramidal points are not all of the same kind." The quartz crystals of the Alps, to which he refers, are in some specimens very regular, while in others, one side of the pyramid becomes much the largest, yet the angles remain constantly the same. But when the whole shape varied so much, the angles also seemed to vary. Thus Conrad Gessner, a very learned naturalist, who in 1564 published at Zurich his work De Rerum Fossilium, Lapidum et Gemmarum Maxime Figuris, says, "One crystal differs from another in its angles, and consequently in its figure." And Caesalpinus, who, as we shall find, did so much in establishing fixed characters in botany, was led by some of his general views to disbelieve the fixity of the form of crystals. In his work De Metallicis, published at Nuremberg in 1602, he says, "To ascribe to inanimate bodies a definite form does not appear consentaneous to reason, for it is the office of organization to produce a definite form." 317, an opinion very natural in one who had been immersed in the study of the general analogies of the forms of plants. But though this is excusable in Caesalpinus, the rejection of this definiteness of form 100 years later, when its existence had been proved and its laws developed by numerous observers, cannot be ascribed to anything but strong prejudice. Yet this was the course taken by no less a person than Buffon. "The form of crystallization," says he, "is not a constant character, but is more equivocal and more variable than any other of the characters by which minerals are to be distinguished." And accordingly, he makes no use of this most important feature in his history of minerals. This strange perverseness may perhaps be ascribed to the dislike which Buffon is said to have entertained for Linnaeus, who had made crystalline form a leading character of minerals. It is not necessary to mark all the minute steps by which mineralogists were gradually led to see clearly the nature and laws of the fixity of crystalline forms. These forms were at first noticed in that substance which is peculiarly called rock crystal or quartz, and afterwards in various stones and gems, in salts obtained from various solutions, and in snow. But those who observed the remarkable regular figures which these substances assume were at first impelled onwards in their speculations by the natural tendency of the human mind to generalize and guess, rather than to examine and measure. They attempted to snatch at once the general laws of geometrical regularity of these occurrences, or to connect them with some doctrine concerning formative causes. Thus Kepler, in his Harmonics of the World, asserts a formatrix facultas, which has its seat in the entrails of the earth, and, after the manner of a pregnant woman, expresses the 5 regular geometrical solids in the forms of gems. But philosophers, in the course of time, came to build more upon observation and less upon abstract reasonings. Nicholas Steno, a Dane, published, in 1669, a dissertation de solido intra solidum naturaliter contento, in which he says that though the sides of the hexagonal crystal may vary, the angles are not changed. And Dominic Guglielmini, in a dissertation on salts published in 1707, says, in a true inductive spirit, "Nature does not employ all figures, but only certain ones of those which are possible. And of these, the determination is not to be fetched from the brain or proved a priori, but obtained by experiments and observations." And 318, he speaks with entire decision on this subject. Nevertheless, since there is here a principle of crystallization, the inclination of the planes and of the angles is always constant. He even anticipates, very nearly, the views of later crystallographers as to the mode in which crystals are formed from elementary molecules. From this time, many persons labored and speculated on this subject, as Kepler, whose prodromus crystallography appeared at Lucerne in 1723. Burget, who published Letters philosophiques sur la formation de cells et de cristaux at Amsterdam in 1792. And Henkel, the physicus of the Elector of Saxony, whose Pyrotologia came forth in 1725. In this last work, we have an example of the description of the various forms of special classes of minerals: iron pyrites, copper pyrites, and arsenic pyrites, and an example of the enthusiasm which this apparently dry and laborious study can excite. "Neither tongue nor stone," he exclaims, "can express the satisfaction which I received on setting eyes upon the sinter covered with galena." And thus it constantly happens that one must have more pleasure in what seems worthless rubbish than in the purest and most precious ores if we know aught of minerals. Still, however, Henkel disclaims the intention of arranging minerals according to their mathematical forms, and this, which may be considered as the first decided step in the formation of crystallographic mineralogy, appears to have been first attempted by Linnaeus. In this attempt, however, he was by no means happy, nor does he himself appear to have been satisfied. He begins his preface by saying, "Lithology is not what I plume myself upon. Lithologia mihi Christus non erigit." Though his sagacity, as a natural historian, led him to see that crystalline form was one of the most definite, and therefore most important, characters of minerals, he failed in profiting by this thought, because, in applying it, he did not employ the light of geometry, but was regulated by what appeared to him resemblances, arbitrarily selected, and often delusive. Thus he derived the form of pyrites from that of vitriol, and brought together alum and diamond on account of their common octahedral form. But he had the great merit of animating to this study one to whom, more perhaps than to any other person, it owes its subsequent progress. I mean Remy Delisle. Instructed, this writer says, in his preface to his Essays de Crystallography, by the works of the celebrated von Linné, how, 319. Greatly the study of the angular form of crystals might become interesting, and fitted to extend the sphere of our mineralogical knowledge, I have followed them in all their metamorphoses with the most scrupulous attention. The views of Linnaeus as to the importance of this character had indeed been adopted by several others, as John Hill, the king's gardener at Kew, who, in 1777, published his Spathognesia, and Grignon, who, in 1775, says, "These crystallizations may give the means of finding a new theory of the generation of crystalline gems." The circumstance which threw so much difficulty in the way of those who tried to follow out his thought was, that in consequence of the apparent irregularity of crystals, arising from the extension or contraction of particular sides of the figure, each kind of substance may really appear under many different forms, connected with each other by certain geometrical relations. These may be conceived by considering a certain fundamental form to be cut into new forms in particular ways. Thus, if we take a cube and cut off all the 8 corners, till the original faces disappear, we make it an octahedron. And if we stop short of this, we have a figure of 14 faces, which has been called a cubo-octahedron. The first person who appears distinctly to have conceived this truncation of angles and edges, and to have introduced the word, is Damest. Although Wallerius had already said, in speaking of the various crystalline forms of calcspar, "I conceive it would be better not to attend to all differences, lest we be overwhelmed by the number." And Werner, in his celebrated work on the external characters of minerals, had formerly spoken of truncation, equation, and acumination, or replacement by a plane, an edge, a point respectively, Abstumpfung, Zuscharfung, Zuspitzung, as ways in which the forms of crystals are modified and often disguised. He applied this process in particular to show the connection of the various forms which are related to the cube. But still the extension of the process to the whole range of minerals and other crystalline bodies was due to Remy Delisle. 320. Chapter 2. Epoch of Remy Delisle and Hauy. Establishment of the fixity of crystalline angles and the simplicity of the laws of derivation. We have already seen that, before 1780, several mineralogists had recognized the constancy of the angles of crystals, and had seen, as Damest and Werner, that the forms were subject to modifications of a definite kind. But neither of these two thoughts was so apprehended and so developed as to supersede the occasion for a discoverer who should put forward these principles as what they really were, the materials of a new and complete science. The merit of this step belongs jointly to Remy de Lisle and to Hoy. The former of these two men had already, in 1772, published an essay de crystallographie, in which he had described a number of crystals. But in this work, his views are still rude and vague. He does not establish any connected sequence of transitions in each kind of substance and lays little or no stress on the angles. But in 1783, his ideas had reached a maturity which, by comparison, excites our admiration. In this, he asserts, in the most distinct manner, the invariability of the angles of crystals of each kind, under all the changes of relative dimension which the faces may undergo. And he points out that this invariability applies only to the primitive forms, from each of which many secondary forms are derived by various changes. Thus we cannot deny him the merit of having taken steady hold on both the handles of this discovery, though something still remained for another to do. Remy pursues his general ideas into detail with great labor and skill. He gives drawings of more than 500 regular forms. In his first work, he had inserted only 110. Linnaeus only knew 40, and assigns them to their proper substances, for instance, 30 to calcspar and 16 to felspar. He also invented and used a goniometer. We cannot doubt that he would have been 321, looked upon as a great discoverer, if his fame had not been dimmed by the more brilliant success of his contemporary Hoy. Note 16/15, Crystallographie, au description de formes propres à tous les corps du regne minéral, 3 vols, and 1 volume of plates. René Just Hoy is rightly looked upon as the founder of the modern school of crystallography. For all those who have, since him, pursued the study with success, have taken his views for their basis. Besides publishing a system of crystallography and of mineralogy, far more complete than any which had yet appeared, the peculiar steps in the advance which belong to him are the discovery of the importance of cleavage and the consequent expression of the laws of derivation of secondary from primary forms, by means of the decrements of the successive layers of integrant molecules. The latter of these discoveries had already been, in some measure, anticipated by Bergman, who had, in 1773, conceived a hexagonal prism to be built up by the juxtaposition of solid rhombs on the planes of a rhombic nucleus. It is not clear whether Hoy was acquainted with Bergman's memoir, at the time when the cleavage of a hexagonal prism of calcspar, accidentally obtained, led him to the same conception of its structure. But however this might be, he had the indisputable credit of following out this conception with all the vigor of originality, and with the most laborious and persevering earnestness. Indeed, he made it the business of his life. The hypothesis of a solid, built up of small solids, had this peculiar advantage in reference to crystallography. It rendered a reason of this curious fact, that a certain series of forms occur in crystals of the same kind, while other forms, apparently intermediate between those which actually occur, are rigorously excluded. The doctrine of decrements explained this, for by placing a number of regularly decreasing rows of equal solids, as for instance of bricks upon one another, we might form a regular equal-sided triangle, as the gable of a house. And if the breadth of the gable were 100 bricks, the height of the triangle might be 100 or 50 or 25. But it would be found that if the height were an intermediate number, as 57 or 43, the edge of the wall would become irregular. And such irregularity is assumed to be inadmissible in the regular structure of crystals. Thus, this mode of conceiving crystals allows of certain definite secondary forms and no others. Note 19/15, Deformes Crystallorum, Nov. Act. Reg. Soc. Sc. Ups. 1773. The mathematical deduction of the dimensions and proportions, 322 of these secondary forms, the invention of a notation to express them, the examination of the whole mineral kingdom in accordance with these views, the production of a work in which they are explained with singular clearness and vivacity, are services by which Hoy richly earned the admiration which has been bestowed upon him. The wonderful copiousness and variety of the forms and laws to which he was led, thoroughly exercised and nourished the spirit of deduction and calculation which his discoveries excited in him. the reader may form some conception of the extent of his labors by being told that the mere geometrical propositions, which he found it necessary to premise to his special descriptions, occupy a volume and a half of his work, that his diagrams are nearly 1,000 in number, that in one single substance, calcspar, he has described 47 varieties of form, and that he has described one kind of crystal, called by him fur sulfure parallelique, which has 134 faces. In the course of a long life, he examined, with considerable care, all the forms he could procure of all kinds of mineral, and the interpretation which he gave of the laws of those forms was, in many cases, fixed by means of a name applied to the mineral in which the form occurred. Thus, he introduced such names as epochs, médestatique, unibinaire, perihexaheter, bisaltern, and others. It is not now desirable to apply separate names to the different forms of the same mineral species, but these terms answered the purpose, at the time, of making the subjects of study more definite. A symbolical notation is the more convenient mode of designating such forms, and such a notation Hoy invented, but the symbols devised by him had many inconveniences and have since been superseded by the systems of other crystallographers. Another of Hoy's leading merits was, as we have already intimated, to have shown, more clearly than his predecessors had done, that the crystalline angles of substances are a criterion of the substances, and that this is peculiarly true of the angles of cleavage. That is, the angles of those edges which are obtained by cleaving a crystal in two different directions, a mode of division which the structure of many kinds of crystals allowed him to execute in the most complete manner. As an instance of the employment of this criterion, I may mention his separation of the sulfates of baryta and strontia, which had 323 previously been confounded, among crystals which in the collections were ranked together as heavy spar, and which were so perfect as to admit of accurate measurement. He found that those which were brought from Sicily and those of Derbyshire differed in their cleavage angle by 3 degrees and a half. I could not suppose, he says, that this difference was the effect of any law of decrement, for it would have been necessary to suppose so rapid and complex a law that such an hypothesis might have been justly regarded as an abuse of the theory. He was, therefore, in great perplexity. But a little while previous to this, Klaproth had discovered that there is an earth which, though in many respects it resembles baryta, is different from it in other respects. And this earth, from the place where it was found in Scotland, had been named strontia. The French chemists had ascertained that the two earths had, in some cases, been mixed or confounded, and Vauquelin, on examining the Sicilian crystals, found that their base was strontia, and not, as in the Derbyshire ones, baryta. The riddle was now read. All the crystals with the larger angle belonged to the one, all those with the smaller to the other, of these two sulfates. And crystallometry was clearly recognized as an authorized test of the difference of substances which nearly resemble each other. Enough has been said, probably, to enable the reader to judge how much each of the two persons, now under review, contributed to crystallography. It would be unwise to compare such contributions to science with the great discoveries of astronomy and chemistry, and we have seen how nearly the predecessors of Ramey and Hoy had reached the point of knowledge on which these two crystallographers took their stand. But yet it is impossible not to allow that in these discoveries, which thus gave form and substance to the science of crystallography, we have a manifestation of no common sagacity and skill. Here, as in other discoveries, were required ideas and facts, clearness of geometrical conception, which could deal with most complex relations of form, a minute and extensive acquaintance with actual crystals, and the talent and habit of referring these facts to the general ideas. Hoy, in particular, was happily endowed for his task. Without being a great mathematician, he was sufficiently a geometer to solve all the problems which his undertaking demanded. And though the mathematical reasoning might have been made more compendious, 324, by one who was more at home in mathematical generalization, probably this could hardly have been done without making the subject less accessible and less attractive to persons moderately disciplined in mathematics. In all his reasonings upon particular cases, Hoy is acute and clear, while his general views appear to be suggested rather by a lively fancy than by a sage inductive spirit. And though he thus misses the character of a great philosopher, the vivacity of style, and felicity and happiness of illustration, which grace his book, and which agree well with the character of an abbé of the old French monarchy, had a great and useful influence on the progress of the subject. Unfortunately, Remy de Lisle and Hoy were not only rivals, but in some measure enemies. The former might naturally feel some vexation at finding himself, in his later years, he died in 1790, thrown into shade by his more brilliant successor. In reference to Hoy's use of cleavage, he speaks of innovators in crystallography, who may properly be called crystalloclasts. Yet he adopted, in great measure, the same views of the formation of crystals by Laminy, which Hoy illustrated by the destructive process at which he thus sneers. His sensitiveness was kept alive by the conduct of the Academy of Sciences, which took no notice of him and his labors, probably because it was led by Buffon, who disliked Linnaeus and might dislike Remy as his follower, and who, as we have seen, despised crystallography. Hoy revenged himself by rarely mentioning Remy in his works, though it was manifest that his obligations to him were immense, and by recording his errors while he corrected them. More fortunate than his rival, Hoy was, from the first, received with favor and applause. His lectures at Paris were eagerly listened to by persons from all quarters of the world. His views were, in this manner, speedily diffused, and the subject was soon pursued, in various ways, by mathematicians and mineralogists in every country of Europe. Chapter 3. Reception and Corrections of the Hoyan Crystallography. I have not hitherto noticed the imperfections of the crystallographic views and methods of Hoy, because my business in the last section, 325, was to mark the permanent additions he made to the science. His system did, however, require completion and rectification in various points, and in speaking of the crystallographers of the subsequent time, who may all be considered as the cultivators of the Hoyan doctrines, we must also consider what they did in correcting them. The three main points in which this improvement was needed were a better determination of the crystalline forms of the special substances, a more general and less arbitrary method of considering crystalline forms according to their symmetry, and a detection of more general conditions by which the crystalline angle is regulated. The first of these processes may be considered as the natural sequel of the Hoyan epoch. The other two must be treated as separate steps of discovery. When it appeared that the angle of natural or of cleavage faces could be used to determine the differences of minerals, it became important to measure this angle with accuracy. Hoy's measurements were found very inaccurate by many succeeding crystallographers. Mohs says that they are so generally inaccurate that no confidence can be placed in them. This was said, of course, according to the more rigorous notions of accuracy to which the establishment of Hoy's system led. Among the persons who principally labored in ascertaining, with precision, the crystalline angles of minerals were several Englishmen, especially Wollaston, Phillips, and Brooke. Wollaston, by the invention of his reflecting goniometer, placed an entirely new degree of accuracy within the reach of the crystallographer. The angle of two faces being, in this instrument, measured by means of the reflected images of bright objects seen in them, so that the measure is the more accurate the more minute the faces are. In the use of this instrument, no one was more laborious and successful than William Phillips, whose power of apprehending the most complex forms with steadiness and clearness led Wollaston to say that he had a geometrical sense. Phillips published a treatise on mineralogy, containing a great collection of such determinations, and Mr. Brooke, a crystallographer of the same exact and careful school, has also published several works of the same kind. The precise measurement of crystalline angles must be the familiar employment of all who study crystallography, and therefore any further enumeration of those 326 who have added in this way to the stock of knowledge would be superfluous. Nor need I dwell long on those who added to the knowledge which Hoy left of derived forms. The most remarkable work of this kind was that of Count Bornand, who published a work on a single mineral, calcspar, in 3/4 volumes. He has here given representations of 700 forms of crystals, of which, however, only 56 are essentially different. From this example, the reader may judge what a length of time, and what a number of observers and calculators were requisite to exhaust the subject. Note 27/15, Traité complète de la chalcocarbonate et d'aragonite par M. Leconte de Bornand. London, 1808. If the calculations, thus occasioned, had been conducted upon the basis of Whewell's system, without any further generalization, they would have belonged to that process, the natural sequel of inductive discoveries, which we call deduction, and would have needed only a very brief notice here. But some additional steps were made in the upward road to scientific truth, and of these we must now give an account. Chapter 4. Establishment of the distinction of systems of crystallization, Weiss and Mohs. In Whewell's views, as generally happens in new systems, however true, there was involved something that was arbitrary, something that was false or doubtful, something that was unnecessarily limited. The principal points of this kind were his having made the laws of crystalline derivation depend so much upon cleavage, his having assumed an atomic constitution of bodies as an essential part of his system, and his having taken a set of primary forms, which, being selected by no general view, were partly superfluous and partly defective. How far evidence, such as has been referred to by various philosophers, has proved, or can prove, that bodies are constituted of indivisible atoms, will be more fully examined in the work which treats of the philosophy of this subject. There can be little doubt that the 327 portion of Whewell's doctrine, which most riveted popular attention and applause, was his dissection of crystals, in a manner which was supposed to lead actually to their ultimate material elements. Yet it is clear that since the solids given by cleavage are, in many cases, such as cannot make up a solid space, the primary conception of a necessary geometrical identity between the results of division and the elements of composition, which is the sole foundation of the supposition that crystallography points out the actual elements, disappears on being scrutinized. And when Whewell, pressed by this difficulty, as in the case of fluorspar, put his integrant octahedral molecules together, touching by the edges only, his method became an empty geometrical diagram with no physical meaning. The real fact, divested of the hypothesis which was contained in the fiction of decrements, was that when the relation of the derivative to the primary faces is expressed by means of numerical indices, these numbers are integers, and generally very small ones. And this was the form which the law gradually assumed, as the method of derivation was made more general and simple by Weiss and others. When, in 1809, I published my dissertation, says Weiss, I shared the common opinion as to the necessity of the assumption and the reality of the existence of a primitive form, at least in a sense not very different from the usual sense of the expression. While I sought, he adds, referring to certain doctrines of general philosophy which he and others entertained, a dynamical ground for this instead of the untenable atomistic view, I found that out of my primitive forms there was gradually unfolded to my hands that which really governs them and is not affected by their casual fluctuations, the fundamental relations of those dimensions according to which a multiplicity of internal oppositions, necessarily and mutually interdependent, are developed in the mass, each having its own polarity, so that the crystalline character is coextensive with these polarities. The dimensions of which Weiss here speaks are the axes of symmetry of the crystal, that is, those lines in reference to which every face is accompanied by other faces, having like positions and properties. Thus a rhomb, or more properly a rhombohedron, of 328 calcspar may be placed with one of its obtuse corners uppermost, so that all the three faces which meet there are equally inclined to the vertical line. In this position, every derivative face, which is obtained by any modification of the faces or edges of the rhombohedron, implies either 3 or 6 such derivative faces. For no one of the 3 upper faces of the rhombohedron has any character or property different from the other 2, and therefore there is no reason for the existence of a derivative from one of these primitive faces, which does not equally hold for the other primitive faces. Hence the derivative forms will, in all cases, contain none but faces connected by this kind of correspondence. The axis thus made vertical will be an axis of symmetry, and the crystal will consist of 3 divisions ranged round this axis and exactly resembling each other. According to Weiss's nomenclature, such a crystal is 3 and 3-membered. Note 29/15. I use this name for the solid figure since rhomb has always been used for a plane figure. But this is only one of the kinds of symmetry which crystalline forms may exhibit. they may have three axes of complete and equal symmetry at right angles to each other, as the cube and the regular octahedron, or two axes of equal symmetry, perpendicular to each other and to a third axis, which is not affected with the same symmetry with which they are. Such a figure is a square pyramid, or they may have three rectangular axes, all of unequal symmetry, the modifications referring to each axis separately from the other two. These are essential and necessary distinctions of crystalline form, and the introduction of a classification of forms founded on such relations, or, as they were called, systems of crystallization, was a great improvement upon the divisions of the earlier crystallographers, for those divisions were separated according to certain arbitrarily assumed primary forms. Thus, Ramé de Lisle's fundamental forms were the tetrahedron, the cube, the octahedron, the rhombic prism, the rhombic octahedron, the dodecahedron with triangular faces. Hoy's primary forms are the cube, the rhombohedron, the oblique rhombic prism, the right rhombic prism, the rhombic dodecahedron, the regular octahedron, tetrahedron and six-sided prism, and the bipyramidal dodecahedron. This division, as I have already said, errs both by excess and defect, for some of these primary forms might be made derivatives from others, and no solid reason could be assigned why they were not. Thus the cube may be derived from the tetrahedron, by truncating the edges, and the rhombic dodecahedron again from the cube, by truncating its edges, while the square pyramid could not be legitimately identified with the derivative of any of these forms. For if we were to 329 derive it from the rhombic prism, why should the acute angles always suffer decrements corresponding in a certain way to those of the obtuse angles, as they must do in order to give rise to a square pyramid? The introduction of the method of reference to systems of crystallization has been a subject of controversy, some ascribing this valuable step to Weiss and some to Mohs. It appears, I think, on the whole, that Weiss first published works in which the method is employed, but that Mohs, by applying it to all the known species of minerals, has had the merit of making it the basis of real crystallography. Weiss, in 1809, published a dissertation on the mode of investigating the principal geometrical character of crystalline forms, in which he says, "No part, line, or quantity is so important as the axis. No consideration is more essential or of a higher order than the relation of a crystalline plane to the axis." And again, an axis is any line governing the figure, about which all parts are similarly disposed, and with reference to which they correspond mutually. This he soon followed out by examination of some difficult cases, as felspar and epidote. In the Memoirs of the Berlin Academy, for 1814-15, he published an exhibition of the natural divisions of systems of crystallization. In this memoir, his divisions are as follows: the regular system, the four-membered, the two- and two-membered, the three- and three-membered, and some others of inferior degrees of symmetry. These divisions are by Mohs' Outlines of Mineralogy, 1822, termed the tessular, pyramidal, prismatic, and rhombohedral systems respectively. Haussmann, in his investigations concerning the forms of inanimate nature, makes a nearly corresponding arrangement: the isometric, monodimetric, trimetric, and monotrimetic, and one or other of these sets of terms have been adopted by most succeeding writers. In order to make the distinctions more apparent, I have purposely omitted to speak of the systems which arise when the prismatic system loses some part of its symmetry, when it has only half or a quarter its complete number of faces, or, according to Mohs' phraseology, when it is hemihedral or tetrahedral. Such systems are represented by the singly oblique or doubly oblique prism. They are termed by Weiss two- and one-membered and one- and one-membered, by other writers monoclinometric and triclinometric systems. There are also other 330 peculiarities of symmetry, such, for instance, as that of the plagiahedral faces of quartz and other minerals. The introduction of an arrangement of crystalline forms into systems, according to their degree of symmetry, was a step which was rather founded on a distinct and comprehensive perception of mathematical relations than on an acquaintance with experimental facts, beyond what earlier mineralogists had possessed. This arrangement was, however, remarkably confirmed by some of the properties of minerals which attracted notice about the time now spoken of, as we shall see in the next chapter. Chapter 5. Reception and confirmation of the distinction of systems of crystallization. Diffusion of the distinction of systems. The distinction of systems of crystallization was so far founded on obviously true views that it was speedily adopted by most mineralogists. I need not dwell on the steps by which this took place. Mr. Heidinger's translation of Mohs was a principal occasion of its introduction in England. As an indication of dates bearing on this subject, perhaps I may be allowed to notice that there appeared in the Philosophical Transactions for 1825 a general method of calculating the asterisk angles of crystals, which I had written and in which I referred only to Hoy's views. But that in 1826 I published a memoir on the classification of crystalline combinations, founded on the methods of Weiss and Mohs, especially the latter, with which I had in the meantime become acquainted, and which appeared to me to contain their own evidence and recommendation. General methods, such as was attempted in the memoir just quoted, are part of that process in the history of sciences, by which, when the principles are once established, the mathematical operation of deducing their consequences is made more and more general and symmetrical, which we have seen already exemplified in the history of celestial mechanics after the time of Newton. It does not enter into our plan to dwell upon the various steps in this way 331 made by Levy, Naumann, Grassmann, Kupfer, Hessel, and by Professor Miller among ourselves. I may notice that one great improvement was the method introduced by Montero and Levy of determining the laws of derivation of forces by means of the parallelisms of edges, which was afterwards extended so that faces were considered as belonging to zones. Nor need I attempt to enumerate, what indeed it would be difficult to describe in words, the various methods of notation by which it has been proposed to represent the faces of crystals, and to facilitate the calculations which have reference to them. My memoir of 1825 depended on the views of Hoy in so far as that I started from his primitive forms, but being a general method of expressing all forms by coordinates, it was very little governed by these views. The mode of representing crystalline forms which I proposed seemed to contain its own evidence of being more true to nature than Hoy's theory of decrements, inasmuch as my method expressed the faces at much lower numbers. I determine a face by means of the dimensions of the primary form divided by certain numbers. Hoy had expressed the face virtually by the same dimensions multiplied by numbers. In cases where my notation gives such numbers as 3, 4, 1, 1, 3, 7, 5, 1, 19, his method involves the higher numbers 4, 3, 12, 21, 7, 3, 19, 95, 5. My method, however, has, I believe, little value as a method of calculating the angles of crystals. M. Newman, of Königsberg, introduced a very convenient and elegant mode of representing the position of faces of crystals by corresponding points on the surface of a circumscribing sphere. He gave, in 1823, the laws of the derivation of crystalline faces, expressed geometrically by the intersection of zones, Beiträge zur Kristallonomie. The same method of indicating the position of faces of crystals was afterwards, together with the notation reinvented by M. Grassmann, zur Kristallonomie und geometrischen Kombinationslehre, 1829. Aiding himself by the suggestions of these writers, and partly adopting my method, Prof. Miller has produced a work on crystallography remarkable for mathematical elegance and symmetry, and has given expressions really useful for calculating the angles of crystalline faces, a treatise on crystallography. Cambridge, 1839. Confirmation of the distinction of systems by the optical properties of minerals Brewsteri must not omit to notice the striking confirmation which the distinction of systems of crystallization received from optical discoveries, especially those of Sir D. Brewster. Of the 332 history of this very rich and beautiful department of science, we have already given some account, in speaking of optics. The first facts which were noticed, those relating to double refraction, belonged exclusively to crystals of the rhombohedral system. The splendid phenomena of the rings and lemniscates produced by dipolarizing crystals were afterwards discovered, and these were, in 1817, classified by Sir David Brewster, according to the crystalline forms to which they belong. This classification, on comparison with the distinction of systems of crystallization, resolved itself into a necessary relation of mathematical symmetry. All crystals of the pyramidal and rhombohedral systems, which from their geometrical character have a single axis of symmetry, are also optically uniaxial and produce by dipolarization circular rings. While the prismatic system, which has no such single axis, but three unequal axes of symmetry, is optically biaxial, gives lemniscates by dipolarized light, and according to Fresnel's theory, has three rectangular axes of unequal elasticity. I have placed Sir David Brewster's arrangement of crystalline forms in this chapter, as an event belonging to the confirmation of the distinctions of forms introduced by Weiss and Mohs, because that arrangement was established not on crystallographical, but on optical grounds. But Sir David Brewster's optical discovery was a much greater step in science than the systems of the two German crystallographers. And even in respect to the crystallographical principle, Sir D. Brewster had an independent share in the discovery. He divided crystalline forms into three classes, enumerating the Hoyan primitive forms which belonged to each, and as he found some exceptions to this classification, such as idocrase and C, he ventured to pronounce that in those substances the received primitive forms were probably erroneous, a judgment which was soon confirmed by a closer crystallographical scrutiny. He also showed his perception of the mineralogical importance of his discovery by publishing it, not only in the Phil. Trans. 1818, but also in the Transactions of the Wernerian Society of Natural History. In a second paper inserted in this later series, read in 1820, he further notices Mohs's system of crystallography, which had then recently appeared, and points out its agreement with his own. Another reason why I do not make his great optical discovery a cardinal point in the history of crystallography is that as a crystallographical system it is incomplete. Although we are thus led to distinguish the tessular and the prismatic systems, using Mohs's terms, 333, from the rhombohedral and the square prismatic, we are not led to distinguish the latter two from each other, inasmuch as they have no optical difference of character. But this distinction is quite essential in crystallography, for these two systems have faces formed by laws as different as those of the other two systems. Moreover, Weiss and Mohs not only divided crystalline forms into certain classes, but showed that by doing this, the derivation of all the existing forms from the fundamental ones assumed a new aspect of simplicity and generality. And this was the essential part of what they did. On the other hand, I do not think it is too much to say, as I have elsewhere said, that Sir D. Brewster's optical experiments must have led to a classification of crystals into the above systems, or something nearly equivalent, even if crystals had not been so arranged by attention to their forms. Note 35/15, Philosophy of the Inductive Sciences, B Roman 8, C Roman 3, Art 3. Many other most curious trains of research have confirmed the general truth that the degree and kind of geometrical symmetry corresponds exactly with the symmetry of the optical properties. As an instance of this, eminently striking for its singularity, we may notice the discovery of Sir John Herschel, that the plagiahedral crystallization of quartz, by which it exhibits faces twisted to the right or the left, is accompanied by right-handed or left-handed circular polarization, respectively. No one acquainted with the subject can now doubt that the correspondence of geometrical and optical symmetry is of the most complete and fundamental kind. Our knowledge with respect to the positions of the optical axes of the oblique prismatic crystals is still imperfect. It appears to be ascertained that, in singly oblique crystals, one of the axes of optical elasticity coincides with the rectangular crystallographic axis. In doubly oblique crystals, one of the axes of optical elasticity is, in many cases, coincident with the axis of a principal zone. I believe no more determinate laws have been discovered. Thus, the highest generalization at which mathematical crystallographers have yet arrived may be considered as fully established, and the science of crystallography, in the condition in which these place it, is fit to be employed as one of the members of mineralogy, and thus to fill its appropriate place and office. 334. Chapter 6. Correction of the law of the same angle for the same substance. Discovery of isomorphism. Mitscherlich, the discovery of which we now have to speak may appear at first sight too large to be included in the history of crystallography and may seem to belong rather to chemistry. But it is to be recollected that crystallography, from the time of its first assuming importance in the hands of Whewell, founded its claim to notice entirely upon its connection with chemistry. Crystalline forms were properties of something. But what that something was, and how it might be modified without becoming something else, no crystallographer could venture to decide without the aid of chemical analysis. Whewell had assumed, as the general result of his researches, that the same chemical elements, combined in the same proportions, would always exhibit the same crystalline form, and reciprocally, that the same form and angles, except in the obvious case of the tessular system, in which the angles are determined by its being the tessular system, implied the same chemical constitution. But this dogma could only be considered as an approximate conjecture, for there were many glaring and unexplained exceptions to it. The explanation of several of these was beautifully described by the discovery that there are various elements which are isomorphous to each other. That is, such that one may take the place of another without altering the crystalline form, and thus the chemical composition may be much changed, while the crystallographic character is undisturbed. This truth had been caught sight of, probably as a guess only, by Fuchs as early as 1815. In speaking of a mineral which had been called jaelenite, he says, "I hold the oxide of iron, not for an essential component part of this genus, but only as a vicarious element, replacing so much lime." We shall find it necessary to consider the results of several analyses of mineral bodies in this point of view, if we wish, on the one hand, to bring them into agreement with the doctrine of chemical proportions, and on the other, to avoid unnecessarily splitting up genera. In a lecture on the mutual influence of 335, Chemistry and Mineralogy, he again draws attention to his term vicarious, vicariant, which undoubtedly expresses the nature of the general law afterwards established by Mitscherlich in 1822. But Fuchs's conjectural expression was only a prelude to Mitscherlich's experimental discovery of isomorphism. Till many careful analyses had given substance and signification to this conception of vicarious elements, it was of small value. Perhaps no one was more capable than Berzelius of turning to the best advantage any ideas which were current in the chemical world. Yet we find him, in 1820, dwelling upon a certain vague view of these cases, that oxides which contain equal doses of oxygen must have their general properties common, without tracing it to any definite conclusions. But his scholar, Mitscherlich, gave this proposition a real crystallographical import. Thus he found that the carbonates of lime calcspar, of magnesia, of protoxide of iron, and of protoxide of manganese agree in many respects of form, while the homologous angles vary through 1 or 2 degrees only. So again the carbonates of baryta, strontia, lead, and lime aragonite agree nearly. The different kinds of felspar vary only by the substitution of one alkali for another. The phosphates are almost identical with the arseniates of several bases. These and similar results were expressed by saying that, in such cases, the bases, lime, protoxide of iron, and the rest are isomorphous, or in the latter instance, that the arsenic and phosphoric acids are isomorphous. Since, in some of these cases, the substitution of one element of the isomorphous group for another does alter the angle, though slightly, it has since been proposed to call such groups plesiomorphous. This discovery of isomorphism was of great importance and excited much attention among the chemists of Europe. The history of its reception, however, belongs, in part, to the classification of minerals, for its effect was immediately to metamorphose the existing chemical systems of arrangement. But even those crystallographers and chemists who cared little for general systems of classification received a powerful impulse by the expectation, which was now excited, of discovering definite laws connecting chemical constitution with crystalline form. Such investigations were soon carried on with great activity. Thus, at a recent period, Abich analyzed a number of tessular minerals: spinel, pleonast, gonite, franklinite, and chromic iron oxide. And 336 seems to have had some success in giving a common type to their chemical formulae, as there is a common type in their crystallization. It will be seen by the above account that Prof. Mitscherlich's merit in the great discovery of isomorphism is not at all narrowed by the previous conjectures of M. Fuchs. I am informed, moreover, that M. Fuchs afterwards, in Schweger's journal, retracted the opinions he had put forward on this subject. Dimorphism, my business is to point out the connected truths which have been obtained by philosophers, rather than insulated difficulties which still stand out to perplex them. I need not, therefore, dwell on the curious cases of dimorphism, cases in which the same definite chemical compound of the same elements appears to have two different forms. Thus the carbonate of lime has two forms, calcspar and aragonite, which belong to different systems of crystallization. Such facts may puzzle us, but they hardly interfere with any received general truths, because we have as yet no truths of very high order respecting the connection of chemical constitution and crystalline form. Dimorphism does not interfere with isomorphism. The two classes of facts stand at the same stage of inductive generalization, and we wait for some higher truth which shall include both and rise above them. For additions to our knowledge of the dimorphism of bodies, see Professor Johnstone's valuable report on that subject in the reports of the British Association for 1837. Substances have also been found which are trimorphous. We owe to Professor Mitscherlich the discovery of dimorphism, as well as of isomorphism, and to him also we owe the greater part of the knowledge to which these discoveries have led. Chapter 7. Attempts to establish the fixity of other physical properties, Werner. The reflections from which it appeared, at the end of the last book, that in order to obtain general knowledge respecting bodies, we must give scientific fixity to our appreciation of their properties, applies to their other properties as well as to their crystalline 337 form. And though none of the other properties have yet been referred to standards so definite as that which geometry supplies for crystals, a system has been introduced which makes their measures far more constant and precise than they are to a common undisciplined sense. The author of this system was Abraham Gottlob Werner, who had been educated in the institutions which the Elector of Saxony had established at the mines of Freiburg. Of an exact and methodical intellect, and of great acuteness of the senses, Werner was well fitted for the task of giving fixity to the appreciation of outward impressions. And this he attempted in his dissertation on the external characters of fossils, which was published at Leipzig in 1774. Of the precision of his estimation of such characters, we may judge from the following story, told by his biographer Frisch. One of his companions had received a quantity of pieces of amber, and was relating to Werner, then very young, that he had found in the lot one piece from which he could extract no signs of electricity. Werner requested to be allowed to put his hand in the bag which contained these pieces, and immediately drew out the unelectrical piece. It was yellow chalcedony, which is distinguishable from amber by its weight and coldness. The principal external characters which were subjected by Werner to a systematic examination were color, luster, hardness, and specific gravity. His subdivisions of the first character, color, were very numerous, yet it cannot be doubted that if we recollect them by the eye, and not by their names, they are definite and valuable characters, and especially the metallic colors. Breithaupt, merely by the aid of this character, distinguished two new compounds among the small grains found along with the grains of platinum, and usually confounded with them. The kinds of luster, namely, glassy, fatty, adamantine, metallic, are, when used in the same manner, equally valuable. Specific gravity obviously admits of a numerical measure, and the hardness of a mineral was pretty exactly defined by the substances which it would scratch, and by which it was capable of being scratched. Werner soon acquired a reputation as a mineralogist, which drew persons from every part of Europe to Freiburg in order to hear his lectures, and thus diffused very widely his mode of employing external characters. It was, indeed, impossible to attend so closely to 338, these characters as the Wernerian method required, without finding that they were more distinctive than might at first sight be imagined. And the analogy which this mode of studying mineralogy established between that and other branches of natural history recommended the method to those in whom a general inclination to such studies was excited. Thus Professor Jameson of Edinburgh, who had been one of the pupils of Werner at Freiburg, not only published works in which he promulgated the mineralogical doctrines of his master, but established in Edinburgh a Wernerian society, having for its object the general cultivation of natural history. Werner's standards and nomenclature of external characters were somewhat modified by Mohs, who, with the same kinds of talents and views, succeeded him at Freiburg. Mohs reduced hardness to numerical measure by selecting 10 known minerals, each harder than the other in order, from talc to corundum and diamond, and by making the place which these minerals occupy in the list the numerical measure of the hardness of those which are compared with them. The result of the application of this fixed measurement and nomenclature of external characters will appear in the history of classification, to which we now proceed. 339. Systematic Mineralogy. Chapter 8. Attempts at the classification of minerals. Sect 1. Proper object of classification. The fixity of the crystalline and other physical properties of minerals is turned to account by being made the means of classifying such objects. To use the language of Aristotle, classification is the architectonic science, to which crystallography and the doctrine of external characters are subordinate and ministerial, as the art of the bricklayer and carpenter are to that of the architect. But classification itself is useful only as subservient to an ulterior science, which shall furnish us with knowledge concerning things so classified. To classify is to divide and to name, and the value of the divisions which we thus make, and of the names which we give them, is this, that they render exact knowledge and general propositions possible. Now the knowledge which we principally seek concerning minerals is a knowledge of their chemical composition. The general propositions to which we hope to be led are such as assert relations between their intimate constitution and their external attributes. Thus our mineralogical classification must always have an eye turned towards chemistry. We cannot get rid of the fundamental conviction that the elementary composition of bodies, since it fixes their essence, must determine their properties. Hence all mineralogical arrangements, whether they profess it or not, must be in effect chemical. They must have it for their object to bring into view a set of relations, which, whatever else they may be, are at least chemical relations. We may begin with the outside, but it is only in order to reach the inner, 340 structure. We may classify without reference to chemistry, but if we do so, it is only that we may assert chemical propositions with reference to our classification. But as we have already attempted to show, we not only may, but we must classify, by other than chemical characters, in order to be able to make our classification the basis of chemical knowledge. In order to assert chemical truths concerning bodies, we must have the bodies known by some tests not chemical. The chemist cannot assert that a ragonite does or does not contain strontia, except the mineralogist can tell him whether any given specimen is or is not a ragonite. If chemistry be called upon to supply the definitions as well as the doctrines of mineralogy, the science can only consist of identical propositions. Yet chemistry has been much employed in mineralogical classifications, and it is generally believed with advantage to the science. How is this consistent with what has been said? To this the answer is that when this has been done with advantage, the authority of external characters, as well as of chemical constitution, has really been brought into play. We have two sets of properties to compare, chemical and physical. To exhibit the connection of these is the object of scientific mineralogy. And though this connection would be most distinctly asserted if we could keep the two sets of properties distinct, yet it may be brought into view in a great degree, by classifications in which both are referred to as guides. Since the governing principle of the attempts at classification is the conviction that the chemical constitution and the physical properties have a definite relation to each other, we appear entitled to use both kinds of evidence, in proportion as we can best obtain each. And then the general consistency and convenience of our system will be the security for its containing substantial knowledge, though this be not presented in a rigorously logical or systematic form. Such mixed systems of classification, resting partly on chemical and partly on physical characters, naturally appeared as the earliest attempts in this way, before the two members of the subject had been clearly separated in men's minds. And these systems, therefore, we must first give an account of. Sect 2. Mixed systems of classification. Early systems. The first attempts at classifying minerals went upon the ground of those differences of general aspect which had been 341 recognized in the formation of common language, as earths, stones, metals. But such arrangements were manifestly vague and confused, and when chemistry had advanced to power and honor, her aid was naturally called in to introduce a better order. Iron and bromel were, as far as I know, says Cronstedt, the first who founded any mineral system upon chemical principles. To them we owe the three known divisions of the most simple mineral bodies, viz., the calcary, vitrescence, and apyry. But Cronstedt's own essay towards A System of Mineralogy, published in Swedish in 1758, had perhaps more influence than any other upon succeeding systems. In this, the distinction of earths and stones, and also of vitrescent and non-vitrescent earths, apyry, is rejected. The earths are classed as calcareous, silicious, argillaceous, and the like. Again, calcareous earth is pure calc-spar, or united with acid of vitriol gypsum, or united with the muriatic add sal ammoniac, and the like. It is easy to see that this is the method, which, in its general principle, has been continued to our own time. In such methods, it is supposed that we can recognize the substance by its general appearance, and on this assumption, its place in the system conveys to us chemical knowledge concerning it. But as the other branches of natural history, and especially botany, assumed a systematic form, many mineralogists became dissatisfied with this casual and superficial mode of taking account of external characters. They became convinced that in mineralogy, as in other sciences, classification must have its system and its rules. The views which Werner ascribes to his teacher, Pabst van Ohain, show the rise of those opinions which led through Werner to Mohs. He was of opinion that a natural mineral system must be constructed by chemical determinations and external characters at the same time, methodus mixta. But that along with this, mineralogists ought also to construct and employ what he called an artificial system, which might serve us as a guide, loco indicis, how to introduce newly discovered fossils into the system, and how to find easily and quickly those already known and introduced. Such an artificial system, containing not the grounds of classification, but marks for recognition, was afterwards attempted by Mohs, and termed by him the characteristic of his system. Werner's system, but, in the meantime, Werner's classification had an extensive reign, and this was still a mixed system. Werner himself, indeed, never published a system of mineralogy. We might, 342, almost imagine, Cuvier says, that when he had produced his nomenclature of external characters, he was affrighted with his own creation, and that the reason of his writing so little after his first essay was to avoid the shackles which he had imposed upon others. His system was, indeed, made known both in and out of Germany by his pupils, but in consequence of Werner's unwillingness to give it on his own authority, it assumed, in its published forms, the appearance of an extorted secret imperfectly told. A notice of the mineralogical cabinet of mine director Pabst van Ohain was, in 1792, published by Karsten and Hoffmann under Werner's direction, and conveyed, by example, his views of mineralogical arrangement. And in 1816, his doctrine of classification was surreptitiously copied from his manuscript and published in a German journal termed the Hesperus. But it was only in 1817, after his death, that there appeared Werner's last mineral system, edited from his papers by Breithaupt and Kohler. And by this time, as we shall soon see, other systems were coming forwards on the stage. A very slight notice of Werner's arrangement will suffice to show that it was, as we have termed it, a mixed system. He makes 4 great classes of fossils: earthy, saline, combustible, metallic. The earthy fossils are in 8 genera: diamond, zircon, silica, alumina, talc, lime, baryta, halites. It is clear that these genera are in the main chemical, for chemistry alone can definitely distinguish the different earths which characterize them. Yet the Wernerian arrangement supposed the distinctions to be practically made by reference to those external characters, which the teacher himself could employ with such surpassing skill. And though it cannot be doubted that the chemical views which prevailed around him had a latent influence on his classification in some cases, he resolutely refused to bend his system to the authority of chemistry. Thus, when he was blamed for having, in opposition to the chemists, placed diamond among the earthy fossils, he persisted in declaring that, mineralogically considered, it was a stone and could not be treated as anything else. This was an indication to that tendency, which, under his successor, led to a complete separation of the two grounds of classification. But before we proceed to this, we must notice what was doing at this period in other parts of Europe. Hoy's system, though Werner, on his own principles, ought to 343, have been the first person to see the immense value of the most marked of external characters, crystalline form. He did not, in fact, attach much importance to it. Perhaps he was in some measure fascinated by a fondness for those characters which he had himself systematized, and the study of which did not direct him to look for geometrical relations. However this may be, the glory of giving to crystallography its just importance in mineralogy is due to France, and the treatise of Hoy, published in 1801, is the basis of the best succeeding works of mineralogy. In this work, the arrangement is professedly chemical, and the classification thus established is employed as the means of enunciating crystallographic and other properties. The principal object of this treatise, says the author, is the exposition and development of a method founded on certain principles, which may serve as a framework for all the knowledge which mineralogy can supply, aided by the different sciences which can join hands with her and march on the same line. It is worthy of notice, as characteristic of this period of mixed systems, that the classification of Hoy, though founded on principles so different from the Wernerian ones, deviates little from it in the general character of the divisions. Thus, the first order of the first class of Hoy is acidiferous earthy substances. The first genus is lime. The species are carbonate of lime, phosphate of lime, fluate of lime, sulfate of lime, and so on. Other systems such mixed methods were introduced also into this country, and have prevailed, we may say, up to the present time. The Mineralogy of William Phillips, which was published in 1824, and which was an extraordinary treasure of crystallographic facts, was arranged by such a mixed system. That is, by a system professedly chemical, but inasmuch as a rigid chemical system is impossible, and the assumption of such a one leads into glaring absurdities, the system was, in this and other attempts of the same kind, corrected by the most arbitrary and lax application of other considerations. It is a curious example of the difference of national intellectual character, that the manifest inconsistencies of the prevalent systems, which led in Germany, as we shall see, to bold and sweeping attempts at reform, produced in England a sort of contemptuous despair with regard to systems in general, a belief that no system could be consistent or useful, and a persuasion that the only valuable knowledge is the accumulation of particular facts. This is not the place to 344 explain how erroneous and unphilosophical such an opinion is. But we may notice that while such a temper prevails among us, our place in this science can never be found in advance of that position which we are now considering as exemplified in the period of Werner and Hoy. So long as we entertain such views respecting the objects of mineralogy, we can have no share in the fortunes of the succeeding period of its history, to which I now proceed. Chapter 9. Attempts at the reform of mineralogical system separation of the chemical and natural history methods. Sect 1. Natural history system of Mohs. The chemical principle of classification, if pursued at random, as in the cases just spoken of, leads to results at which a philosophical spirit revolts. It separates widely substances which are not distinguishable, joins together bodies the most dissimilar, and in hardly any instance does it bring any truth into view. The vices of classifications like that of Hoy could not long be concealed, but even before time had exposed the weakness of his system, Hoy himself had pointed out, clearly and without reserve, that a chemical system is only one side of the subject, and supposes, as its counterpart, a science of external characters. In the meantime, the Wernerians were becoming more and more in love with the form which they had given to such a science. Indeed, the expertness which Werner and his scholars acquired in the use of external characters justified some partiality for them. It is related of him that, by looking at a piece of iron ore and poising it in his hand, he was able to tell, almost precisely, the proportion of pure metal which it contained. And in the last year of his life, he had marked out, as the employment of the ensuing winter, the study of the system of Berzelius, with a view to find out the laws of combination as disclosed by external characters. In the same spirit, his pupil, 345, Breithaupt attempted to discover the ingredients of minerals by their peculiarities of crystallization. The persuasion that there must be some connection between composition and properties transformed itself, in their minds, into a belief that they could seize the nature of the connection by a sort of instinct. This opinion of the independency of the science of external characters and of its sufficiency for its own object at last assumed its complete form in the bold attempt to construct a system which should borrow nothing from chemistry. This attempt was made by Frederick Mohs, who had been the pupil of Werner, and was afterwards his successor in the school of Freiburg, and who, by the acute and methodical character of his intellect, and by his intimate knowledge of minerals, was worthy of his predecessor. Rejecting altogether all divisions of which the import was chemical, Mohs turned for guidance, or at least for the light of analogy, to botany. His object was to construct a natural system of mineralogy. What the conditions and advantages of a natural system of any province of nature are, we must delay to explain till we have before us, in botany, a more luminous example of such a scheme. But further, in mineralogy, as in botany, besides the natural system, by which we form our classes, it is necessary to have an artificial system by which we recognize them, a principle which, we have seen, had already taken root in the school of Freiburg. Such an artificial system Mohs produced in his Characteristic of the Mineral Kingdom, which was published at Dresden in 1820, and which, though extending only to a few pages, excited a strong interest in Germany, where men's minds were prepared to interpret the full import of such a work. Some of the traits of such a characteristic had, indeed, been previously drawn by others, as for example, by Hoy, who notices that each of his classes has peculiar characters. For instance, his first class, acidiferous substances, alone possesses these combinations of properties: division into a regular octahedron without being able to scratch glass, specific gravity above 3.5 without being able to scratch glass. The extension of such characters into a scheme which should exhaust the whole mineral kingdom was the undertaking of Mohs. Such a collection of marks of classes implied a classification previously established, and accordingly, Mohs had created his own mineral system. His aim was to construct it, as we shall hereafter see that other natural systems are constructed, by taking into account all the 346 resemblances and differences of the objects classified. It is obvious that to execute such a work implied a most intimate and universal acquaintance with minerals, a power of combining in one vivid survey the whole mineral kingdom. To illustrate the spirit in which Professor Mohs performed his task, I hope I may be allowed to refer to my own intercourse with him. At an early period of my mineralogical studies, when the very conception of a natural system was new to me, he, with great kindliness of temper, allowed me habitually to propose to him the scruples which arose in my mind, before I could admit principles which appeared to me then so vague and indefinite, and answered my objections with great patience and most instructive clearness. Among other difficulties, I one day propounded to him this: "You have published a treatise on mineralogy, in which you have described all the important properties of all known minerals. On your principles, then, it ought to be possible, merely by knowing the descriptions in your book, and without seeing any minerals, to construct a natural system. And this natural system ought to turn out identical with that which you have produced, by so careful an examination of the minerals themselves." He pondered a moment, and then he answered, "It is true, but what an enormous imagination, Einbildungskraft, power of inward imagining, a man must have for such a work. Vividness of conception of sensible properties, and the steady intuition, Anschauung of objects, were deemed by him, and by the Wernerian school in general, to be the most essential conditions of complete knowledge." It is not necessary to describe Mohs' system in detail. It may sufficiently indicate its form to state that the following substances, such as I before gave as examples of other arrangements, calcspar, gypsum, fluorspar, apatite, heavy spar, are by Mohs termed respectively rhombohedral lime haloid, gyps haloid, octahedral fluor haloid, rhombohedral fluor haloid, prismatic hal barite. These substances are thus referred to the orders haloid and barite, to genera lime haloid, fluor haloid, hal barite, and the species is an additional particularization. Mohs not only aimed at framing such a system, but was also ambitious of giving to all minerals names which should accord with the system. This design was too bold to succeed. It is true that a new nomenclature was much needed in mineralogy. It is true, too, that it was reasonable to expect, from an improved classification, an improved nomenclature, such as had been so happily obtained in botany by the 347 Reform of Linnaeus. But besides the defects of Moses' system, he had not prepared his verbal novelties with the temperance and skill of the great botanical reformer. He called upon mineralogists to change the name of almost every mineral with which they were acquainted, and the proposed appellations were mostly of a cumbrous form, as the above example may serve to show. Such names could have obtained general currency only after a general and complete acceptance of the system, and the system did not possess, in a sufficient degree, that evidence which alone could gain it a home in the belief of philosophers the coincidence of its results with those of chemistry. But before I speak finally of the fortunes of the natural history system, I will say something of the other attempt which was made about the same time to introduce a reform into mineralogy from the opposite extremity of the science. Sect 2, Chemical System of Berzelius and others. If the students of external characters were satisfied of the independence of their method, the chemical analysts were naturally no less confident of the legitimate supremacy of their principles. And when the beginning of the present century had been distinguished by the establishment of the theory of definite proportions, and by discoveries which pointed to the electrochemical theory, it could not appear presumption to suppose that the classification of bodies, so far as it depended on chemistry, might be presented in a form more complete and scientific than at any previous time. The attempt to do this was made by the great Swedish chemist Jacob Berzelius. In 1816, he published his essay to establish a purely scientific system of mineralogy by means of the application of the electrochemical theory and the chemical doctrine of definite proportions. It is manifest that, for minerals which are constituted by the law of definite proportions, this constitution must be a most essential part of their character. The electrochemical theory was called in aid, in addition to the composition, because, distinguishing the elements of all compounds as electropositive and electronegative, and giving to every element a place in a series, and a place defined by the degree of these relations, it seemed to afford a rigorous and complete principle of arrangement. Accordingly, Berzelius, in his first system, arranged minerals according to their electropositive element, and the elements according to their electropositive rank, 348, and supposed that he had thus removed all that was arbitrary and vague in the previous chemical systems of mineralogy. Though the attempt appeared so well justified by the state of chemical science, and was so plausible in its principle, it was not long before events showed that there was some fallacy in these specious appearances. In 1820, Mitscherlich discovered isomorphism. By that discovery, it appeared that bodies containing very different electropositive elements could not be distinguished from each other. It was impossible, therefore, to put them in distant portions of the classification, and thus the first system of Berzelius crumbled to pieces. But Berzelius did not so easily resign his project. With the most unhesitating confession of his first failure, but with undaunted courage, he again girded himself to the task of rebuilding his edifice. Defeated at the electropositive position, he now resolved to make a stand at the electronegative element. In 1824, he published in the Transactions of the Swedish Academy a memoir on the alterations in the chemical mineral system, which necessarily follow from the property exhibited by isomorphous bodies of replacing each other in given proportions. The alteration was, in fact, an inversion of the system, with an attempt still to preserve the electrochemical principle of arrangement. Thus, instead of arranging metallic minerals according to the metal, under iron, copper, and C, all the sulfurates were classed together, all the oxides together, all the sulfates together, and so in other respects. That such an order was a great improvement on the preceding one cannot be doubted, but we shall see, I think, that as a strict scientific system it was not successful. The discovery of isomorphism, however, naturally led to such attempts. Thus Gmelin also, in 1825, published a mineral system, which, like that of Berzelius, founded its leading distinctions on the electronegative, or, as it was sometimes termed, the formative element of bodies. and besides this, took account of the numbers of atoms or proportions which appear in the composition of the body, distinguishing, for instance, silicates as simple silicates, double silicates, and so on to quintuple silicate Pechstein and sextuple silicate Pearlstein. In like manner, Nordenskjöld devised a system resting on the same bases, taking into account also the crystalline form. In 1824, Budent published his Traité élémentaire de minéralogie, in which he professes to found his arrangement on the electronegative element and on Ampere's circular, 349, arrangement of elementary substances. Such schemes exhibit rather a play of the mere logical faculty, exercising itself on assumed principles, than any attempt at the real interpretation of nature. Other such pure chemical systems may have been published, but it is not necessary to accumulate instances. I proceed to consider their result. Sect 3. Failure of the attempts at systematic reform. It may appear presumptuous to speak of the failure of those whom, like Berzelius and Mohs, we acknowledge as our masters, at a period when, probably, they and some of their admirers still hold them to have succeeded in their attempt to construct a consistent system. But I conceive that my office as an historian requires me to exhibit the fortunes of this science in the most distinct form of which they admit, and that I cannot evade the duty of attempting to seize the true aspect of recent occurrences in the world of science. Hence, I venture to speak of the failure of both the attempts at framing a pure scientific system of mineralogy that founded on the chemical, and that founded on the natural history principle, because it is clear that they have not obtained that which alone we could, according to the views here presented, consider as success, a coincidence of each with the other. A chemical system of arrangement which should bring together, in all cases, the substances which come nearest each other in external properties, a natural history system, which should be found to arrange bodies in complete accordance with their chemical constitution. If such systems existed, they might, with justice, claim to have succeeded. Their agreement would be their verification. The interior and exterior system are the type and the antitype, and their entire correspondence would establish the mode of interpretation beyond doubt. But nothing less than this will satisfy the requisitions of science. And when, therefore, the chemical and the natural history system, though evidently, as I conceive, tending towards each other, are still far from coming together, it is impossible to allow that either method has been successful in regard to its proper object. But we may, I think, point out the fallacy of the principles, as well as the imperfection of the results of both of those methods. With regard to that of Berzelius, indeed, the history of the subject obviously betrays its unsoundness. The electropositive principle was, in a very short time after its adoption, proved and acknowledged to be utterly untenable. What security have we that the electronegative element is 350 more trustworthy? Was not the necessity of an entire change of system a proof that the ground, whatever that was, on which the electrochemical principle was adopted, was an unfounded assumption? And, in fact, do we not find that the same argument which was allowed to be fatal to the first system of Berzelius applies in exactly the same manner against the second? If the electropositive elements be often isomorphous, are not the electronegative elements sometimes isomorphous also? For instance, the arsenic and phosphoric acids. But to go further, what is the ground on which the electrochemical arrangement is adopted? Granted that the electrical relations of bodies are important, but how do we come to know that these relations have anything to do with mineralogy? How does it appear that on them, principally, depend those external properties which mineralogy must study? How does it appear that because sulfur is the electronegative part of one body, and an acid the electronegative part of another, these two elements similarly affect the compounds? How does it appear that there is any analogy whatever in their functions? We allow that the composition must, in some way, determine the classified place of the mineral, but why in this way? I do not dwell on the remark which Berzelius himself makes on Nordenskjöld's system, that it assumes a perfect knowledge of the composition in every case. Although, considering the usual discrepancies of analyses of minerals, this objection must make all pure chemical systems useless. But I may observe that mineralogists have not yet determined what characters are sufficiently affixed to determine a species of minerals. We have seen that the ancient notion of the composition of a species has been unsettled by the discovery of isomorphism. The tenet of the constancy of the angle is rendered doubtful by cases of plesiomorphism. The optical properties, which are so closely connected with the crystalline, are still so imperfectly known that they are subject to changes which appear capricious and arbitrary. Both the chemical and the optical mineralogists have constantly, of late, found occasion to separate species which had been united, and to bring together those which had been divided. Everything shows that, in this science, we have our classification still to begin. The detection of that fixity of characters, on which a right establishment of species must rest, is not yet complete, great as the progress is which we have made, by acquiring a knowledge of the laws of crystallization and of 351 definite chemical constitution. Our ignorance may surprise us, but it may diminish our surprise to recollect that the knowledge which we seek is that of the laws of the physical constitution of all bodies whatever. For to us, as mineralogists, all chemical compounds are minerals. The defect of the principle of the natural history classifiers may be thus stated. In studying the external characters of bodies, they take for granted that they can, without any other light, discover the relative value and importance of those characters. The grouping of species into a genus, of genera into an order, according to the method of this school, proceeds by no definite rules, but by a latent talent of appreciation, a sort of classifying instinct. But this course cannot reasonably be expected to lead to scientific truth, for it can hardly be hoped, by anyone who looks at the general course of science, that we shall discover the relation between external characters and chemical composition, otherwise than by tracing their association in cases where both are known. It is urged that in other classificatory sciences, in botany, for example, we obtain a natural classification from external characters without having recourse to any other source of knowledge. But this is not true in the sense here meant. In framing a natural system of botany, we have constantly before our eyes the principles of physiology, and we estimate the value of the characters of a plant by their bearing on its functions, by their place in its organization. In an unorganic body, the chemical constitution is the law of its being, and we shall never succeed in framing a science of such bodies but by studiously directing our efforts to the interpretation of that law. On these grounds, then, I conceive that the bold attempts of Mohs and of Berzelius to give new forms to mineralogy cannot be deemed successful in the manner in which their authors aspired to succeed. Neither of them can be marked as a permanent reformation of the science. I shall not inquire how far they have been accepted by men of science, for I conceive that their greatest effect has been to point out improvements which might be made in mineralogy without going the whole length either of the pure chemical or of the pure natural history system. Sect 4 returned to mixed systems with improvements. In spite of the efforts of the purists, mineralogists returned to mixed systems of classification, but these systems are much better than they were before such efforts were made. 352. The second system of Berzelius, though not tenable in its rigorous form, approaches far nearer than any previous system to a complete character, bringing together like substances in a large portion of its extent. The system of Mohs also, whether or not unconsciously swayed by chemical doctrines, forms orders which have a community of chemical character. Thus, the minerals of the order haloid are salts of oxides, and those of the order pyrites are sulfurates of metals. Thus the two methods appear to be converging to a common center, and though we are unable to follow either of them to this point of union, we may learn from both in what direction we are to look for it. If we regard the best of the pure systems hitherto devised as indications of the nature of that system, perfect both as a chemical and as a natural history system, to which a more complete condition of mineralogical knowledge may lead us, we may obtain even at present a tolerably good approximation to a complete classification. And such a one, if we recollect that it must be imperfect, and is to be held as provisional only, may be of no small value and use to us. The best of the mixed systems produced by this compromise again comes from Freiberg, and was published by Professor Naumann in 1828. Most of his orders have both a chemical character and great external resemblances. Thus his haloids, divided into unmetallic and metallic, and these again into hydrous and anhydrous, give good natural groups. The most difficult minerals to arrange in all systems are the silicious ones. These Naumann calls silicides and subdivides them into metallic, unmetallic, and amphoteric or mixed, and again into hydrous and anhydrous. Such a system is at least a good basis for future researches, and this is, as we have said, all that we can at present hope for. And when we recollect that the natural history principle of classification has begun, as we have already seen, to make its appearance in our treatises of chemistry, we cannot doubt that some progress is making towards the object which I have pointed out. But we know not yet how far we are from the end. The combination of chemical, crystallographical, physical, and optical properties into some lofty generalization is probably a triumph reserved for future and distant years. Conclusion: the history of mineralogy, both in its successes and by its failures, teaches us this lesson, that in the sciences of classification, the establishment of the fixity of characters and the discovery of such characters as are fixed are steps of the first importance in the progress of these sciences. The recollection of this maxim may aid us in 353, shaping our course through the history of other sciences of this kind, in which, from the extent of the subject and the mass of literature belonging to it, we might at first almost despair of casting the history into distinct epochs and periods. To the most prominent of such sciences, botany, I now proceed. 355, Book 16. Classificatory Sciences. History of Systematic Botany and Zoology. Vetum aspices qui rup sub altifata canet, foliusque notas et nomina mandat, qui cunc in foliis descripsit carmina virgo didrit in numerum ac antro seclusa relinquit, illa manent immorta locis nec ob ordine sedunt. Virgil. Aen. Roman 3, 443. Behold the Sibyl, her who weaves a long tangled, full, yet sweetly flowing song. Wondrous her skill. For leaf on leaf she frames unerring symbols and enduring names, and as her nicely measured line she binds, for leaf on leaf a fitting place she finds, their place once found, no more the leaves depart, but fixed rest, such is her magic art. 357, Introduction. We now arrive at that study which offers the most copious and complete example of the sciences of classification, I mean botany. And in this case, we have before us a branch of knowledge of which we may say, more properly than of any of the sciences which we have reviewed since astronomy, that it has been constantly advancing, more or less rapidly, from the infancy of the human race to the present day. One of the reasons of this resemblance in the fortunes of two studies so widely dissimilar is to be found in a simplicity of principle which they have in common. The ideas of likeness and difference, on which the knowledge of plants depends, are, like the ideas of space and time, which are the foundation of astronomy, readily apprehended with clearness and precision, even without any peculiar culture of the intellect. But another reason why, in the history of botany, as in that of astronomy, the progress of knowledge forms an unbroken line from the earliest times, is precisely the great difference of the kind of knowledge which has been attained in the two cases. In astronomy, the discovery of general truths began at an early period of civilization. In botany, it has hardly yet begun, and thus, in each of these departments of study, the lore of the ancient is homogeneous with that of the modern times, though in the one case it is science, in the other, the absence of science, which pervades all ages. The resemblance of the form of their history arises from the diversity of their materials. I shall not here dwell further upon this subject, but proceed to trace rapidly the progress of systematic botany, as the classificatory science is usually denominated, when it is requisite to distinguish between that and physiological botany. My own imperfect acquaintance with this study admonishes me not to venture into its details, further than my purpose absolutely requires. I trust that, by taking my views principally from writers who are generally allowed to possess the best insight into the science, I may be able to draw the larger features of its history with tolerable correctness, and if I succeed in this, I shall attain an object of great importance in my general scheme. 358. Chapter 1. Imaginary Knowledge of Plants. The apprehension of such differences and resemblances as those by which we group together and discriminate the various kinds of plants and animals, and the appropriation of words to mark and convey the resulting notions, must be presupposed, as essential to the very beginning of human knowledge. In whatever manner we imagine man to be placed on the earth by his Creator, these processes must be conceived to be, as our scriptures represent them, contemporaneous with the first exertion of reason and the first use of speech. If we were to indulge ourselves in framing a hypothetical account of the origin of language, we should probably assume as the first formed words those which depend on the visible likeness or unlikeness of objects, and should arrange as of subsequent formation those terms which imply, in the mind, acts of wider combination and higher abstraction. At any rate, it is certain that the names of the kinds of vegetables and animals are very abundant even in the most uncivilized stages of man's career. Thus, we are informed that the inhabitants of New Zealand have a distinct name of every tree and plant in their island, of which there are 600 or 700 or more different kinds. In the accounts of the rudest tribes, in the earliest legends, poetry, and literature of nations, pines and oaks, roses and violets, the olive and the vine, and the 1,000 other productions of the earth, have a place, and are spoken of in a manner which assumes that in such kinds of natural objects, permanent and infallible distinctions had been observed and universally recognized. For a long period, it was not suspected that any ambiguity or confusion could arise from the use of such terms, and when such inconveniences did occur, as even in early times they did, men were far from divining that the proper remedy was the construction of a science of classification. The loose and insecure terms of the language of common life retain their place in botany, long after their 359 defects were severely felt. For instance, the vague and unscientific distinction of vegetables into trees, shrubs, and herbs kept its ground till the time of Linnaeus. While it was thus imagined that the identification of a plant, by means of its name, might properly be trusted to the common uncultured faculties of the mind, and to what we may call the instinct of language, all the attention and study which were bestowed on such objects were naturally employed in learning and thinking upon such circumstances respecting them as were supplied by any of the common channels through which knowledge and opinion flow into men's minds. The reader need hardly be reminded that in the earlier periods of man's mental culture, he acquires those opinions on which he loves to dwell, not by the exercise of observation subordinate to reason, but far more by his fancy and his emotions, his love of the marvelous, his hopes and fears. It cannot surprise us, therefore, that the earliest lore concerning plants which we discover in the records of the past consists of mythological legends, marvelous relations, and extraordinary medicinal qualities. To the lively fancy of the Greeks, the narcissus, which bends its head over the stream, was originally a youth who in such an attitude became enamored of his own beauty. The hyacinth, on whose petals the notes of grief were traced, a I, recorded the sorrow of Apollo for the death of his favorite hyacinthus. The beautiful lotus of India, which floats with its splendid flower on the surface of the water, is the chosen seat of the goddess Lakshmi, the daughter of ocean. In Egypt, too, Osiris swam on a lotus leaf, and Harpocrates was cradled in one. The lotus eaters of Homer lost immediately their love of home. Everyone knows how easy it would be to accumulate such tales of wonder or religion. Note 2/16. Lilium Martigan. Ips suos gemitus foliis inscribit et ai flos habet in scriptum funestak littera ducta estavid. Those who attended to the effects of plants might discover in them some medicinal properties and might easily imagine more. And when the love of the marvelous was added to the hope of health, it is easy to believe that men would be very credulous. We need not dwell upon the examples of this. In Pliny's introduction to that book of his 360, Natural History, which treats of the medicinal virtues of plants, he says, "Antiquity was so much struck with the properties of herbs that it affirmed things incredible." Xanthus, the historian, says that a man killed by a dragon will be restored to life by an herb which he calls balin, and that Thilo, when killed by a dragon, was recovered by the same plant. Democritus asserted, and Theophrastus believed, that there was an herb, at the touch of which the wedge which the woodman had driven into a tree would leap out again. Though we cannot credit these stories, most persons believe that almost anything might be affected by means of herbs if their virtues were fully known. How far from a reasonable estimate of the reality of such virtues were the persons who entertained this belief, we may judge from the many superstitious observances which they associated with the gathering and using of medicinal plants. Theophrastus speaks of these. The drug sellers and the rhizotomists, root cutters, tell us, he says, some things which may be true, but other things which are merely solemn quackery. Thus they direct us to gather some plants, standing from the wind and with our bodies anointed, some by night, some by day, some before the sun falls on them. So far there may be something in their rules, but others are too fantastical and far-fetched. It is perhaps not absurd to use a prayer in plucking a plant, but they go further than this. We are to draw a sword 3 times round the mandragora, and to cut it looking to the west again, to dance round it, and to use obscene language, as they say those who so come in should utter blasphemies. Again, we are to draw a line round the black hellebore, standing to the east and praying, and to avoid an eagle either on the right or on the left. For say they, if an eagle be near, the cutter will die in a year. This extract may serve to show the extent to which these imaginations were prevalent, and the manner in which they were looked upon by Theophrastus, our first great botanical author. And we may now consider that we have given sufficient attention to these fables and superstitions, which have no place in the history of the progress of real knowledge, except to show the strange chaos of wild fancies and legends out of which it had to emerge. We proceed to trace the history of the knowledge of plants. 361. Chapter 2. Unsystematic knowledge of plants. A step was made towards the formation of the science of plants, although undoubtedly a slight one, as soon as men began to collect information concerning them and their properties, from a love and reverence for knowledge, independent of the passion for the marvelous and the impulse of practical utility. This step was very early made. The wisdom of Solomon and the admiration which was bestowed upon it prove, even at that period, such a working of the speculative faculty, and we are told that among other evidences of his being wiser than all men, he spake of trees, from the cedar tree that is in Lebanon even unto the hyssop that springeth out of the wall. The father of history, Herodotus, shows us that a taste for natural history had in his time found a place in the minds of the Greeks. In speaking of the luxuriant vegetation of the Babylonian plain, he is so far from desiring to astonish merely, that he says, "The blades of wheat and barley are full 4 fingers wide. But as to the size of the trees which grow from millet and sesame, though I could mention it, I will not, knowing well that those who have not been in that country will hardly believe what I have said already." He then proceeds to describe some remarkable circumstances respecting the fertilization of the date palms in Assyria. This curious and active spirit of the Greeks led rapidly, as we have seen in other instances, to attempts at collecting and systematizing knowledge on almost every subject. And in this, as in almost every other department, Aristotle may be fixed upon as the representative of the highest stage of knowledge and system which they ever attained. The vegetable kingdom, like every other province of nature, was one of the fields of the labors of this universal philosopher. But though his other works on natural history have come down to us, and are a most valuable monument of the state of such knowledge in his time, his treatise on plants is lost. The book De Plantis, 362, which appears with his name, is an imposture of the Middle Ages, full of errors and absurdities. His disciple, friend, and successor, Theophrastus of Erissos, is, as we have said already, the first great writer on botany whose works we possess. And, as may be said in most cases of the first great writer, he offers to us a richer store of genuine knowledge and good sense than all his successors. But we find in him that the Greeks of his time, who aspired, as we have said, to collect and systematize a body of information on every subject, failed in one half of their object as far as related to the vegetable world. Their attempts at a systematic distribution of plants were altogether futile. Although Aristotle's divisions of the animal kingdom are, even at this day, looked upon with admiration by the best naturalists, the arrangements and comparisons of plants which were contrived by Theophrastus and his successors have not left the slightest trace in the modern form of the science, and therefore, according to our plan, are of no importance in our history. And thus we can treat all the miscellaneous information concerning vegetables which was accumulated by the whole of this school of writers, in no other way than as something antecedent to the first progress towards systematic knowledge. The information thus collected by the unsystematic writers is of various kinds, and relates to the economical and medicinal uses of plants, their habits, mode of cultivation, and many other circumstances. It frequently includes some description, but this is always extremely imperfect because the essential conditions of description had not been discovered. Of works composed of materials so heterogeneous, it can be of little use to produce specimens, but I may quote a few words from Theophrastus, which may serve to connect him with the future history of the science, as bearing upon one of the many problems respecting the identification of ancient and modern plants. It has been made a question whether the following description does not refer to the potato. He is speaking of the differences of roots. Some roots, he says, are still different from those which have been described, as that of the arachidna plant, for this bears fruit underground as well as above. The fleshy part sends one thick root deep into the ground, but the others, which bear the fruit, are more slender, 363, and higher up and ramified. It loves a sandy soil and has no leaf whatever. The books of Aristotle and Theophrastus soon took the place of the Book of Nature in the attention of the degenerate philosophers who succeeded them. A story is told by Strabo concerning the fate of the works of these great naturalists. In the case of the wars and changes which occurred among the successors of Alexander, the heirs of Theophrastus tried to secure to themselves his books, and those of his master, by burying them in the ground. There the manuscripts suffered much from damp and worms, till Apollonican, a book collector of those days, purchased them, and attempted, in his own way, to supply what time had obliterated. When Sylla marched the Roman troops into Athens, he took possession of the library of Apollonican, and the works which it contained were soon circulated among the learned of Rome and Alexandria, who were thus enabled to Aristotelize on botany as on other subjects. The library collected by the Italic kings of Pergamus and the Alexandrian Museum, founded and supported by the Ptolemies of Egypt, rather fostered the commentatorial spirit than promoted the increase of any.